With the industries moving towards containerization, pretty much every big organization has moved out of their traditional approach of using virtual machines and has started using containers for deployment. Kubernetes, being an undisputed market leader, is an open source container orchestration tool. This is definitely one of the most sought tools leading to the future, as many hypergrowth organizations are looking for professionals with in depth knowledge on Kubernetes. According to ZipRecruiter, jobs where Kubernetes experience is factored draw an average salary of $147,000 across the industry. This proves that if you are someone looking forward to building your career in this domain, then it is definitely the golden time for you. Hi all, I welcome you to this full course by Edureka, and today we are going to talk about one of the most sought tools, Kubernetes. And what follows is hopefully everything you need to know how to get started with Kubernetes. But before we begin today's session, let's take a look at our agenda for today. In the first module, there'll be an introduction to Docker and Kubernetes. Here we will understand what is Docker, what is Kubernetes, and we'll also discuss some of the Kubernetes components. In the second module, there'll be a comparison between Kubernetes and Docker. Here we will understand how Kubernetes works with Docker and the major differences between them. Moving on to the third module, we have CKA certification. So here we'll understand what is Certified Kubernetes Administrator and how to prepare for the CKA certification. In the fourth module, we'll understand how to do container orchestration. Here we will understand container orchestration in detail and talk about container orchestration with Kubernetes. In the fifth module, we'll talk about most prominent Kubernetes commands. Here we will understand the command line interface of Kubernetes, that is kubectl, and some of its commands. In the sixth module, that is networking in Kubernetes, we will learn about Kubernetes networking and some of its components. In the seventh module, we will learn how to create YAML files in Kubernetes. We will understand what is YAML and how YAML is used in Kubernetes. In the eighth module, we'll understand about Kubernetes deployments. Here there'll be a detailed explanation of Kubernetes deployments, and there'll also be a demonstration on how to create deployments in Kubernetes. In the ninth module, we'll talk about various Kubernetes controllers and services. Here we will understand controller and services and how to access Kubernetes services. In the 10th module, we will talk about Kubernetes ingress. Here we will understand Kubernetes ingress in detail and learn how to create an ingress in Kubernetes. Moving on to the 11th module, here we'll be talking about Kubernetes stateful sets. Here we will compare stateful sets with deployments and learn how to create stateful sets in Kubernetes. Moving ahead, we'll talk about Kubernetes storage. Here we will talk about the various storage solutions that are available in Kubernetes and also discuss some of the best practices for Kubernetes storage. Moving ahead, we will also talk about the Kubernetes monitoring, which is a very important concept in Kubernetes. Here we will discuss some of the most prominent monitoring tools of Kubernetes, that is Prometheus and Grafana. In the 14th module, we'll be deploying Kubernetes with the help of Minikube, AWS EKS, and finally AKS. In the 15th module, we'll be implementing an end-to-end project on Kubernetes. And finally, we'll conclude this session by discussing some of the most important interview questions for Kubernetes. With this, I come to the end of my agenda. Also, kindly take up this time to go ahead and subscribe to us, and do not forget to hit that bell icon to never miss an update from the Edureka YouTube channel. Also, to learn more about Kubernetes, do not forget to check out our certification training, the link to which is given in the description box below. So without much ado, let's get started. Kubernetes uses Linux container technologies to provide isolation of running applications. So before we dig into Kubernetes itself, we need to be familiar with the basics of containers to understand what Kubernetes does itself and what it offloads to container technologies like Docker. I'm sure you must know that different software components running on the same machine will definitely require different, possibly conflicting versions of dependent libraries or have other different environment requirements in general. Now, when an application is composed of only smaller numbers of large components, it is completely acceptable to give a dedicated virtual machine to each component and isolate their environments by providing each of them with their own operating system instance. But when these components, ERP, now imagine a situation when these components start getting smaller and their numbers start to grow. You cannot give each of them their own virtual machine if you don't want to waste hardware resources and keep your hardware costs really low. But it is not only about wasting hardware resources, because each VM usually needs to be configured and managed individually. Rising number of VMs also lead to wasting human resources because they increase the system administrator's workload considerably. Now, instead of using virtual machines to isolate the environments of each microservice, developers are turning to Linux container technologies. So, what they really do is they allow you to run multiple services on the same host machine while not only exposing a different environment to each of them, but also isolating them from each other, similarly to VMs, but with much less overhead. Now, containers are amazing if you're working and scaling up applications up to 100 or 200 or in a very large number. A process that is running in a container runs inside the host's operating system like all the processes, but the process in the container is still loaded from other processes. Now, to the process itself, it looks like it's the only one running on the machine and in its operating system. So now comparing the container to the virtual machine, containers are much more lightweight that allows you to run higher numbers of software components on the same hardware, mainly because each virtual machine needs to run its own set of system processes, which requires additional compute resources in addition to those consumed by the component's own process. A container, on the other hand, is nothing more than a single isolated process running in the host operating system. What it really does is it consumes only the resources that the application consumes and without the overhead of any additional process. So you're not wasting any more hardware. Now, because of the overhead of VMs, you often really end up grouping multiple applications into each VM because you do not have enough resources to dedicate a whole virtual machine to each application. So when using containers, you can have one container for each application, as you can see in the figure. The end result is that you can fit much more applications on the same bare metal machine. Now that we've discussed the differences between virtual machines and containers, and we have also understood that containers are simply a form of OS virtualization, which allow us to run higher numbers of software components on the same hardware with less overhead, let's move ahead and talk about Docker. By this point, you must be wondering that how exactly containers can isolate processes if they're running on the same operating system, right? So two mechanisms really make this possible. The first one is the Linux namespaces, which makes sure each process sees its own personal view of the system. The second one is Linux control graphs or C groups, which limit the amount of resources the process can consume, like, for example, CPU, memory, network bandwidth, and so on. Now, by default, each system initially has one single namespace. All system resources such as file system, process IDs, user IDs, etc. belong to the single namespace. But you can definitely create additional namespaces and organize resources across them. The other half of container isolation deals with limiting the amount of system resources a container can consume. And as I've already mentioned, this is achieved with the help of C groups, that is a Linux kernel feature that limits the resource usage of a process. Okay, a process definitely cannot use more than the configured amount of CPU, memory, network bandwidth, and so on. So this way, processes cannot hog resources reserved for other processes, which is similar to when each process runs on a separate machine. While container technologies have been around for a really, really long time, they have become more widely known with the rise of the Docker container platform. Docker was the first container system that made containers easily portable across various machines. It simplified the process of packaging up not only the application, but also its libraries and other dependencies, even the whole operating system, file system, into a much simpler portable package that can be used to provision the application to any other machine running Docker. So when you run an application package with Docker, it sees the exact file system contents that you have bundled it with. It sees the same files whether it's running on your development machine or a production machine, even if the production server is running on a completely different Linux OS. The application definitely won't see anything from the server it is running on. So it doesn't really matter if the server has a completely different set of install libraries compared to your development machine. Now, let me explain this with an example. Okay, if you package your application with the files of the whole Red Hat Enterprise Linux operating system, the application will believe it is running inside this Red Hat Enterprise Linux OS. So both when you run it on your development computer that runs on Fedora and when you run it on a server running Debian or some other Linux distribution, only the kernel may be different. This is similar to creating a virtual image by installing an operating system into a VM, installing the app inside it, and then distributing the whole VM image around and running it. Docker achieves the same effect, but instead of using VMs to achieve application isolation, it simply uses Linux container technologies that we've already talked about. And here, instead of using big monolithic VM images, it uses container images, which are usually very small. Okay. And the big difference between Docker based container images and VM images is that container images are composed of layers, which can be shared and reused across multiple images. This means only certain layers of an image need to be downloaded if the other layers were already downloaded previously when running a different container image that also contains the same layers. So Docker is simply a platform for packaging, distributing, and running applications. It allows you to package your application together with its entire environment. Now that we've understood what is Docker and how it really works, let's talk about some of its concepts, okay? Docker is a platform for packaging, distributing, and running applications. And as we've already mentioned, it allows you to package your application together with its whole environment. And this can be either a few libraries that the application requires, or even all the files that are usually available on the file system of an installed OS. Docker really makes it possible to transfer this package to a central repository from which it can then be transferred to any computer running Docker and executed there. So the three main concepts in Docker are images, registries, and containers. So firstly, let us talk about images. A Docker-based container image is something you package your application and environment into. It's as simple as that, okay? It contains the file system that will be available to the application and other metadata, such as the path to the executable that should be executed when the image is run. The second important concept is registries. Now, a Docker registry is simply a repository that stores your Docker images and facilitates easy sharing of those images between different people and computers. You must be wondering what a repository means, right? So you can think of repository as a storage place for safekeeping, or if there's some information or data that must be stored. All of this can be stored within a repository, and Docker registry is a repository. Okay. So when you build your image, you can either run it on your computer you've built it on, or you can push or upload the image to a registry and then pull, that is, download it on another computer and run it there. Certain registries are public, allowing anyone to pull images from it, while some are private, only accessible to certain people or machines. The next concept is containers. A Docker based container is simply a regular Linux container created from a Docker based container image. A running container is a process running on the host running Docker, but it is completely isolated from both the host and all other processes running on it. The process is also resource constrained, meaning it can only access and use the amount of resources like CPU, RAM, and so on that are allocated to it. So before we move ahead to the introduction of Kubernetes, let me explain you how all of these concepts are correlated, okay? And let me explain this with an example. So firstly, imagine the developer tells Docker to build and push image, okay? So what he firstly does is he builds the image and then pushes it to the registry. The image is thus available to anyone who can access that registry. Then what they can do is they can pull the image to any other machine running Docker and then finally run the image. Docker, what it does is it creates an isolated container based on the image and runs the binary executable specified as part of that image. So all of these are related to each other, images, registries, and containers, and are definitely one of the most important concepts in Docker. Okay, so now let's move ahead and let's understand what is Kubernetes. So you can imagine as the number of deployable application components in our system grows, it becomes really hard to manage them all. Google was probably the first company that realized it needed a much better way of deploying and managing their software components and their infrastructure to scale globally. It is also, repeat, it is one of only a few companies in the world that runs hundreds of thousands of servers and has had to deal with managing deployments on a very massive scale. So, this has forced them to develop solutions for making the development and deployment of thousands of software components manageable and cost efficient. So, through the years, Google developed an internal system called Borg, which was later called as Omega, that helped both application developers and system administrators manage those thousands of applications and servers. Now, in addition to simplifying the development and management, it also helped them achieve a much higher utilization of their infrastructure, which is really important when your organization is that large. Now, when you run hundreds of thousands of machines, even tiny improvements in utilization mean savings in millions of dollars. So the incentives for developing such a system are very clear. After having kept Borg and Omega secret for a whole decade, in 2014, Google introduced Kubernetes, an open source system based on experience gained through Borg, Omega, and other internal Google systems. Kubernetes is simply an open source software system that allows you to easily deploy and manage containerized applications on top of it. So it relies on the features of Linux containers to run heterogeneous applications without having to know any internal details of these applications and without having to manually deploy these applications on each host. Because these applications run in containers, they do not affect other applications running on the same server, which is extremely critical when you run applications for completely different organizations on the same hardware. This is of paramount importance for cloud providers because they strive for the best possible utilization of their hardware while still having to maintain complete isolation of hosted applications. Kubernetes enables you to run your software applications on thousands of computer nodes as if all these nodes were a single enormous computer. It abstracts away the underlying infrastructure and by doing so simplifies development, deployment, and management for both development and the operations teams. Deploying applications through Kubernetes is always the same, whether your cluster contains only a couple of nodes or thousands of them. The size of the cluster makes no difference at all. Additional cluster nodes simply represent an additional amount of resources available to deployed applications. So let us understand the core of what Kubernetes really does. So this is the simplest possible view of a Kubernetes system, okay? The system is firstly composed of a master node and any number of worker nodes. When the developer submits a list of applications to the master, Kubernetes deploys them to the cluster of worker nodes. So what node a component lands on doesn't and shouldn't matter, neither to the developer nor to the system administrator. The developer can specify that certain applications must run together and Kubernetes will deploy them on the same worker node. Others will be spread around the cluster, but they can talk to each other in the same way, regardless of where they are deployed. So, Kubernetes can be thought of as an operating system for the cluster. It relieves application developers from having to implement certain infrastructure related services into the applications. Instead, they rely on Kubernetes to provide these services. This includes things such as service discovery, scaling, load balancing, self healing, and even leader election. Application developers can therefore focus on implementing the actual features of the applications and not waste time figuring out how to integrate them with the infrastructure. On the other hand, Kubernetes will also run your containerized application somewhere in the cluster, provide information to its components on how to find each other, and keep all of them running. Because your application doesn't care which node it's running on, Kubernetes can relocate the application at any time, and by mixing and matching applications, it achieves a far better resource utilization than is possible with manual scheduling. So as you can see that Kubernetes exposes the whole data center as a single deployment platform. So now let's talk about some of the most important Kubernetes components. So Kubernetes includes two major players. The first one is masters and the second one is nodes. The master is basically the heart of Kubernetes. It controls and schedules all of the activities in the cluster. Nodes, on the other hand, are the workers that run our containers. So the master includes the, repeat, So the master, as you can see in the image, includes the API server, control manager, scheduler, and etcd. All components can run on different hosts with clustering. However, it can also run on the same node. Firstly, we will talk about API server. The API server, what it really does is it provides an HTTP or HTTPS server, which provides a RESTful API for the components in the Kubernetes master. For example, we could use get to get the resource status or post to create a new resource. We can also watch for updates for resources. The API server stores the object information in etcd, which is Kubernetes backend data resource. So now let's move ahead and talk about control manager, also known as kube control manager. Okay, now the control manager is a set of control loops that watch the changes in the API server and ensure the cluster is in its desired state. Let me explain this with an example. Now the deployment controller ensures that the whole deployment is run on the desired amount of containers, whereas the node controller responds and evicts the pod when the nodes go down. The endpoint controller, on the other hand, is used to create a relationship between services and pods. The service account and the token controller are used to create a default account and API access tokens. Now that we know what is controller manager, the next subcomponent of the master component is the etcd. Now, etcd is an open source distributed key value store where Kubernetes stores all of the RESTful API objects. etcd is responsible for storing and replicating data. The next and the last subcomponent is the scheduler or kube scheduler. Now, the scheduler determines which nodes are suitable candidates for pods to run on. It uses not only resource capacity and the balance of the resource utilization on the node, but also node affinity, times, and toleration. Now that we've discussed the master subcomponents, let's go ahead and talk about node components. Now, node components are provisioned and run on every node, which report the runtime status of the pod to the master. Firstly, we will talk about kubelet. So kubelet is a major process in the nodes. It reports node activities back to Kube API server periodically, including pod health, node health, and liveliness probe. As the diagram shows, it runs containers via container runtimes such as Docker. The next subcomponent in the node components is the proxy or kube proxy. Now, the proxy handles the routing between a pod load balancer, which is also known as service, and the pods. It also provides routing from external internet to services. There are basically three proxy modes, that is user space, IP tables, and IPVS. I'll be talking about all of these. The first one is the user space mode, which creates a large overhead by switching the kernel space and user space. On the other hand, we have the IP tables mode, which is the latest default proxy mode. It changes the IP table's network address translation in Linux to achieve routing TCP and UDP packets across all the containers. IP virtual servers, that is IPVS, was general available in Kubernetes 1.11 and is used to address performance degradations when running more than 1,000 servers in a cluster. So basically, it runs on a host and acts as a load balancer, forwarding the real connection to real servers. IPVS mode will fall back to IPv tables in some scenarios. The last component is Docker. As we've already discussed, Docker is a container runtime implementation, and Kubernetes uses Docker as a default container engine, and it also supports other runtimes such as RKT and runc. So let us understand how the node and the master components really interact with each other. The client uses kubectl, which is a command line interface to send requests to the API server. The API server, on the other hand, is a hub between the master components, will respond to the client requests and push and pull the object information from etcd. Now, if a new task is created, such as run pods, the scheduler will determine which node should be assigned to do that task. The controller manager monitors the running tasks and responds if any undesired state occurs. The API server fetches the logs from pods via the kubelet. Finally, the API server fetches the logs from pods via the kubelet. Now that we know the components of Kubernetes and we've discussed how they interact with each other, let's move on to the next part of this session and talk about Kubernetes benefits. Now, if you have Kubernetes deployed on all your servers, the operation teams do not really need to deal with deploying your applications anymore. Because a containerized application already contains all it needs to run, the system administrators don't really need to install anything to deploy and run the application. Now, on any node where Kubernetes is deployed, Kubernetes can run the application immediately without any help from the system administrators. This brings to the first benefit of Kubernetes, that is simplifying application deployment. Because Kubernetes exposes all its worker nodes as a single deployment platform, we had already seen this in the previous part of the session, application developers can start deploying applications on their own and do not really need to know anything about the servers that make up the cluster. In essence, all the nodes are now a single bunch of computational resources that are really waiting for applications to consume them. A developer does not really usually care what kind of server the application is running on, as long as the server can provide the application with adequate system resources. Certain cases do exist where the developer does care what kind of hardware the application should run on. Now, if the nodes are heterogeneous, you will find cases when you want certain applications to run on nodes with certain capabilities and run other applications on others. Let me explain this with an example, okay? Now, if one of your applications may require being run on a system with SSDs instead of HDDs, while other applications run fine on HDDs. In such cases, you obviously want to ensure that particular app is always scheduled to a node with an SSD. Now, without using Kubernetes, the system administrator would select one specific node that has an SSD and deploy the application there. Now, let's consider a scenario where you're using Kubernetes. Instead of selecting a specific node where your application should be run, it is more appropriate to tell Kubernetes to only choose among nodes with an SSD. So, this is the first benefit. It simplifies application deployment. The second benefit is that it helps in achieving better utilization of hardware. By setting up Kubernetes on your servers and using it to run your applications instead of running them manually, you have decoupled your application from the infrastructure. When you tell Kubernetes to run your application, you're letting it choose the most appropriate node to run your application on based on the description of the application's resource requirements and the available resources on each of these nodes. Now, by using containers and not typing the application down to a specific node in your cluster, you're really allowing the application to freely move around the cluster at any point of time. So the different application components running on the cluster can be mixed and matched to be packed tightly onto the cluster nodes. This ensures the node's hardware resources are utilized as best as possible. The ability to move applications around the cluster at any time allows Kubernetes to utilize the infrastructure much better than you can achieve manually. Humans aren't great at finding optimal combinations, we all know that, especially when the number of all possible options is extremely huge, such as when you have many application components and many server nodes they can be deployed on. Computers can obviously perform this work much better and faster than humans. Now, the third benefit of Kubernetes is health checking and self healing. Having a system that allows moving an application across the cluster at any time is also valuable in the event of server failures. As your cluster size increases, you will deal with failing computer components even more frequently. Kubernetes monitors your application components and the nodes they run on and automatically reschedules them to other nodes in the event of a node failure. This frees the operations team from having to migrate app components manually and allows the team to immediately focus on fixing the node itself and returning it to the pool of available hardware resources instead of focusing on relocating the application. Now, if your infrastructure has enough spare resources to allow normal system operation even without the failed node, the operation teams doesn't even need to react to the failure immediately, such as at 3 a.m. in the morning. They can sleep tight and deal with the fail node during the regular work hours. Now, this brings us to the last benefit of Kubernetes, that is automatic scaling. Using Kubernetes to manage your deployed applications also means the ops team do not really need to constantly monitor the load of individual applications to react to sudden load spikes. As previously mentioned, Kubernetes can be told to monitor the resources used by each application and to keep adjusting the number of running instances of each application. If Kubernetes is running on cloud infrastructure, where adding additional nodes is as easy as requesting them through the cloud provider's API, Kubernetes can even automatically scale the whole cluster size up or down based on the needs of the deployed applications. Now that we have discussed the benefits of Kubernetes and how you can utilize it to the maximum, let us move ahead to the next part of the session and prepare the Docker Kubernetes environment. So, firstly, we will have to have a system running Ubuntu 18.04 or Ubuntu 20.04. Currently, I'm working on a Linux VM that is Ubuntu 18.04. You will also have to have a user account with privileges. So, what I'm going to do now is I'm just going to open my terminal. Now, before we, install whatever requirements that we'll need, we are also going to execute some basic commands. So before installing any software, what you need to do is you need to update and also upgrade the system if necessary that you are working on. To do so, you can just run the apt get command. Okay, once you have successfully updated your system, what we're going to do now is we're going to make sure to install or check whether you already have the required packages, that is curl package and also the transport HTTPS package. Okay, so for this, what I'm going to do is I'm just going to execute the command apt get install curl. Okay, and this will install curl for me. So since I already have the newest version, nothing has been, upgraded or installed or removed. Okay. Now, next, what we're going to do is we are going to execute the apt get command to install transport HTTPS. So even the apt transport HTTPS is already the newest version. So I don't have anything that is going to upgrade or install or even remove. So if you don't have curl or if you don't have apt transport HTTPS, then it is going to go ahead and install all of these for you. And it's going to take some time, obviously. So you'll have to be patient. Now I'm just simply going to clear my screen. The next step is to install VirtualBox Hypervisor. So if I haven't mentioned this already, you will need a virtual machine in which you can set up your node clusters. Okay. That is, you can set up your single node cluster with Minikube, or you can create your own clusters and scale them up. For this, it is really, really important that you have a virtual machine that is already set up in your VM or any of your Linux machine. So what we're going to do is we are going to install VirtualBox on Ubuntu. So for this, we're just going to execute the command apt install VirtualBox ext pack. And you can already see that VirtualBox is already the newest version and it is already installed in our VM. So if you're installing VirtualBox for the first time, you'll just be prompted with another window that says, do you want to continue this installation process? You can just confirm it by clicking Y and hitting enter. Then you'll be prompted with another window with the license agreement on the screen. So you can just press tab that is present on your keyboard and then enter to continue. Okay, the installer will then ask you to agree with the terms of the VirtualBox PUEL license by selecting yes. And once that is done, you can just wait for the installation to complete and then move on to the next step. Now, what we're going to do is we are going to be installing two tools. One is Minikube and the other one is kubectl. For this, I'm just going to open my web browser and we'll check out the various commands that we can use to install Minikube and kubectl. So if I haven't mentioned already, kubectl is the command line interface that will allow you to make changes, access, and really access Kubernetes as a whole. So what we're going to do is I'm just going to look for install kubectl Minikube. If you scroll down, you can see there's an option that says install tools Kubernetes. And this is your official website from where you could download all of the tools. So I'm just going to click that and this will immediately redirect me to a page that will allow me to install kubectl on Linux, Mac OS, and on Windows. So if you are working on Mac OS or Windows, this is the right option for you. But if you're working on Linux, like I am, I can just click on install kubectl on Linux. And if you scroll down, you can also install Minikube. Okay. So Minikube is just a tool that really lets you run Kubernetes locally. It just runs a single node Kubernetes cluster on your PC so that you can try out Kubernetes or for daily development work as well. But no one really uses, Minikube for local development, then it's not really suggested to work on Minikube if you're actually, using it for your daily development work. So I'm just going to click on this View Minikube Get Started guide. So before we, install Minikube, what we're going to do is we're going to set up kubectl. Okay. So for this, I'm just going to switch to this page and I'm going to quickly scroll down. There are three ways that you can install kubectl on Linux. The first one is kubectl binary with curl on Linux. The second one is by using native package management. The third one is by using other package management. So I would suggest you to install kubectl binary with curl on Linux, and you can execute all of these commands, right? You can execute the step number one, that is to download the latest release with the command. And if you want to download a specific version, you can simply replace the command with the portion of the command with the specified version. Okay. And there's also an example as how you could do that. So if you don't want to, if you just want to download the latest version, you can execute the first command. Then you can validate the binary. Okay, you can just download the kubectl checksum file and then validate it. If it is valid, the output will say okay. If it hasn't, then it says kubectl has been failed. Then you can just figure out where you have made the mistake. So moving on, then you can install kubectl, right? So this is the location as to where kubectl will install. And finally, you can just test to ensure the version you have installed is up to date. That's what I'm going to do. I'm going to copy this. Since I have already kubectl installed in my VM, I'm just going to check the version. You can see the client version, you can see the Git version, you can see the build date, you can see the Go version. All of the information is given here. So now what I'm going to do is I'm going to switch back and I'm going to switch the tab to Minikube Start. So as I've already mentioned, Minikube is just local Kubernetes, right? It's focused on making it easy to learn and develop for Kubernetes. All you will need is Docker, a container, or a virtual machine environment, and Kubernetes is a single command away. So there are some prerequisites, right? You'll have to have 2 CPUs or more. You have to have 2 GB of free memory. You'll need to have 20 GB of free disk space. You'll need internet connection. You'll need a container or virtual machine manager such as Docker, Hyper-V, HyperKit, all of that, VirtualBox, etc. So we have successfully downloaded VirtualBox, right? But we haven't downloaded Docker. So I'm just going to open a tab. I'm just going to click on Docker. So this will redirect me to my official website of Docker. So I'm just going to click on that. So once that is done, I'm just going to click on this option that is available on the right hand corner that says Get Started. So this will allow you to set up Docker, right? So there are 3 different types of Dockers. Okay, there's Docker Desktop, there's Docker Hub, there's Play with Docker, which is basically a cloud-based Docker environment, whereas Docker Hub is a cloud-based application registry. So it is like, GitHub, where you can share your development results and also share what you've been working on and collaborate with your team online. Whereas Docker Desktop really allows you to, work locally and work for yourself, right? Just create a local environment and do what you have to do. So what we're going to do now is we're just going to download what we need. You can download for Mac Intel chip, you can download for Mac Apple chip, you can download for Windows, you can view the Linux engine. So I'm just going to click on that. So once that is done, you can just pick on the community that you're working on, whether it's Fedora, CentOS, or Azure, Ubuntu. So since we are working on Ubuntu, you can just click on, Ubuntu community. So once this is done, you can read a description, you can see the reviews, and you can also see the resources. So once you click on the resources, you can see the detailed installation instructions. And this will allow you to install Docker engine on Ubuntu. So there are some OS requirements. You can also uninstall the older versions. And finally, you can just install Docker. So now to set up Docker, all you have to do is follow these instructions. You have different ways of installing Docker. You can choose the one which will allow you to install Docker using the repository. So firstly, you will have to set up the Docker. And once that is done, then you will have to add the Docker's official GPJ key. And then all you have to do is you will have to use the command to set up the stable repository, okay? And you have to check the architecture of your Linux machine, okay? Whether it is ARM64 or it is AMD64. So based on the architecture of your Linux machine, then you just choose the final command to set up the repository and you can execute it in your terminal, okay? Once that is done, you will compulsorily have to install the Docker engine using the install docker c docker cli containeride.io. And if you have a specific version that you'd like to install, you can just do that too. And if you just don't want to, then you can just skip the step. And finally, you can just verify if the Docker engine has been successfully installed in your Linux machine by executing the run command. Okay, so that's what we're going to do. So I'm just going to check if Docker has been installed. And you can see that it says hello from Docker. So all of the information, a brief, summary of what you can do with the help of Docker is given below. So you know that Docker is up and running. So that's great. Now that we have installed Docker, let's switch back to Minikube. So all of my requirements have been successfully satisfied. So now what I'm going to do is I'm simply going to install Minikube. For this, I'm just going to, click on the operating system, the architecture type, and then the installer type. Okay. Once that is done, you can just copy this command that is here. So if it is a Debian package that you want to install, then you can click on that. If you want an RPM package, you can click on that, and whatever is well suited for you, just pick on that and install it. Okay, execute these commands on your Linux terminal and get them installed. And once that is finally done, you're just going to execute the command sudo minikube start. Okay, but before we start our default minikube cluster, let's experiment with Docker a bit, right? So what we're going to do is, using the run command, you can run many images that you'd like to. Okay, so we just ran hello world. You can also run busybox. Okay, and print hello world. So if you're unfamiliar with busybox, that's okay. It is basically a single executable that really combines many of the standard Unix command line tools such as echo, ls, gzip, and so on. So also, instead of the busybox image, you can use any other full-fledged OS container image such as Fedora, Ubuntu, or other similar images, as long as it includes the echo executable. You can see that we have successfully executed the hello world command. Okay. You can also create a Docker file for the image. You can build the container image. There's a lot of things that can really happen. I'm just going to clear the screen. Now what I'm going to do is I'm going to start my Minikube cluster, which is the default Kubernetes cluster. So it's going to take some time to start the cluster. So once it's done, we'll get back to the next part. Now you can see that kubectl is now configured to use the Minikube cluster, which is again the default cluster of Kubernetes. And also there is a default namespace that has been created. So now I'm going to clear the screen. So now what I'm going to do is I am going to use the kubectl pod command, and I'm going to use the A flag to display all of the namespaces that have been created in Kubernetes. As you can see, all of the output, you have default namespaces, you have Ingress, Nginx, you have Kube System, Prometheus. All of these are namespaces that have been created, and they have a particular name. They have the status when it restarts, whether it's ready. So the status, as you can see, some of them are running, some of them are an error, some of them are completed. All of the information regarding these namespaces are given here. Now I'm just going to execute the Minikube dashboard command. So this will activate the dashboard for Kubernetes. So once that's executed, you can access the URL via a web browser. So now the dashboard is enabled, and you can see that the proxy has been launched. Now this URL, what you can do with it is you can open it in a web browser. So as you can see, the deployments, workload status, you can see on the left-hand side the workload, services, config and storage, clusters, custom resource definition, settings, and about. So you can access to any of these, and you can see the status. You can literally monitor your entire cluster based on this dashboard. And if you scroll down, you can see there's deployments, there's pods, the deployments that have been created in the past, and also the pods that you have created in the past before. If you keep scrolling down, you have stateful sets, ingresses, you have the services that are currently created and have been running, persistent volumes, secret storage classes, all of the services that Kubernetes really offers to you. So I'm just going to switch back to my terminal and I'm just going to clear the screen. Once that is done, what I'm going to do is, so I'm just going to use the docker pull Ubuntu command, and this will pull the Ubuntu image from Docker. So as you can see that the Docker is going to pull the image Ubuntu from library Ubuntu. Now I'm going to use the run command -it-d to run Ubuntu successfully. You can see that Ubuntu has been containerized and run successfully in the container with the container ID D8, 3D047, so on. Just going to use the docker ps command and just get the information of all the containers. Use the A flag for more information. I'm going to clear the screen and I'm going to execute the docker images command, which will give me an overview of what all images are running in Docker. And you can see that the Ubuntu image has been created just 4 days ago, and it is the latest image that has been pulled from the Docker website. And that's the latest image that has been pulled from the Docker website. I'm going to clear the screen. So with this, we come to the end of this session. Let's move on to the next part of the session of Kubernetes and Docker. So now let's discuss a case study on how Pinterest really used Docker and Kubernetes together and faced the challenges that they faced. So after almost 8 years in existence, Pinterest had grown into 1,000 microservices and multiple layers of infrastructure and diverse setup tools and platforms. Back in 2016, the company launched a roadmap towards a new compute platform led by the vision of creating the fastest path from an idea to production without really making engineers worry about the underlying infrastructure. So, this was the challenge that they faced back in 2016 when the company was at its boom. So once they faced this challenge, they had to find a solution. The first phase involved moving services to Docker containers. Now, once these services went into production in early 2017, the team began looking at orchestration to help create efficiencies and manage them in a decentralized way. After an evaluation of various solutions, Pinterest went with Kubernetes. Now, by moving to Kubernetes, the whole team was able to build on demand scaling and new failover policies in addition to simplifying the overall deployment and management of a complicated piece of infrastructure such as Jenkins. They not only saw reduced build times but also huge efficiency wins. For instance, the team reclaimed over 80% of capacity during non peak hours. As a result, the Jenkins Kubernetes cluster now uses 30% less instance hours per day when compared to the previous static cluster. So by this, we understand that Kubernetes and Docker can work hand in hand. So there is a relationship between Kubernetes and Docker. We're going to discuss them now. So if Docker is containers and Kubernetes is container orchestration, why would anyone ask, should I use Docker or Kubernetes? Now, in reality, the two tools are actually complementary to each other and help build cloud native or microservice architectures. Docker is mostly used during the first days of a containerized application. It really actually helps build and deploy the application's container or containers. In cases where the application's architecture is very simple, Docker can address the basic needs of the application's lifecycle management. Now, if the case or the scenario where the application is broken down into multiple microservices, with each of these services having their own lifecycle and operational needs, Kubernetes comes into the picture. It is not only used to create the application containers, it actually needs a container platform to run, and Docker being the most popular one, it runs on that. Kubernetes integrates with a large toolset built for and around containers and uses it in its own operations. Containers created with Docker or any of its alternatives can be managed, scaled, and moved by Kubernetes, which also ensures failover management and health maintenance of the system. As you can see in the diagram, the container lifecycle has been explained. You can see that in the Docker, There is the build and deployment of the application that has been successfully done. Once the Docker has been successfully deployed, then Kubernetes takes the responsibility to monitor and scale the application. There are great benefits to using Kubernetes with Docker. Firstly, the applications are easier to maintain as they are broken down into smaller parts. Also, these parts run on an infrastructure that is much more robust, and the applications are more highly available. Here, applications are able to handle more load on demand, improving the user experience and reducing resource waste. As applications become more scalable, there is no need to pre-allocate resources in anticipation of load peak times. Now, here both Docker and Kubernetes are backed by strong open source communities and are part of the Cloud Native Computing Foundation, a Linux Foundation project aiming to advance container technologies and align the industry around specific standards. Now that we understand that Docker and Kubernetes have a really great relationship together, let's move ahead and address the main topic of today's session, that is Kubernetes versus Docker. Firstly, we will compare them in terms of setup and installation. As you can see on the screen, Kubernetes really requires a series of many manual steps to set up the master and worker node components in a cluster of nodes. It's really hard and complicated to install Kubernetes. But on the other hand, that is installing Docker is a matter of one-liner commands on Linux platforms like Ubuntu and CentOS. So compared to Kubernetes, Docker is much more easy to install and set up. Moving on to the next difference, that is logging. Kubernetes provides no native storage solution for log data, whereas logging driver plugins are available in Docker 17.05 and much higher. So in terms of monitoring Kubernetes applications, you can use various open source tools like Prometheus, Grafana, InfluxDB, etc. Docker, on the other hand, also has tools like Prometheus, Docker API, etc. for monitoring purposes. Kubernetes supports up to 5,000 nodes, whereas Docker supports only up to 2,000 nodes. And in terms of compatibility, Kubernetes is more comprehensive and highly customizable, whereas Docker is less extensive and customizable. So for all of y'all who don't know what load balancing is, it is an efficient distribution of network or application traffic across multiple servers in a server farm. So usually each load balancer sits between client devices and backend servers, receiving and then distributing incoming requests to any available server capable of fulfilling them. As you can see in Kubernetes, you must manually configure your load balancing settings, whereas in Docker, it does auto load balancing. That is, it is automated. Now, there are various companies that use Kubernetes and Docker. Companies like Google, Shopify, Udemy, Slack, Robinhood, Delivery Hero, Stackshare, Nubank, etc. use Kubernetes every day. On the other hand, various companies like Twitter, Business Insider, Spotify, PayPal, eBay, Oxford University Press, the New York Times, New Relic, all of these companies and organizations make use of Docker. Now that we've compared Kubernetes and Docker, let us understand in what situation to use Kubernetes and Docker. So what are the choices when it comes to Kubernetes and Docker? What happens if you do choose to use only one and not the other? So there are three scenarios that I'll be addressing. The first one is Docker without Kubernetes. The second one is Kubernetes without Docker. And the third one is Kubernetes with Docker. We've already discussed the benefits of using Kubernetes with Docker, but we'll just brief up that again. So firstly, let's understand the scenario where Docker can be used without Kubernetes. Docker by itself will allow you to build container images, manage them in a registry, run containers, and communicate with them, and eventually put them together in a multi-container application using Docker Compose. So is Docker all that you need? Now, when it comes to producing and managing container images and putting containers into operation at the runtime level, the answer for the most part is definitely yes. It has become the industry standard for creating containers and getting them off the ground. Now, under Docker's current developer-centric definition of its mission, however, it has moved away from earlier attempts to go beyond its core functions. It is no longer attempting to compete with Kubernetes and other companies at the infrastructure or orchestration level. Now let's talk about the second scenario. Kubernetes does not include functionality for creating or managing container images, and it does not by itself run containers. It really needs to work with an external container source and runtime. It is, however, capable of using containers from a variety of sources, and it is compatible with runtimes other than Docker, so it is not inherently dependent on Docker and Docker alone. What Kubernetes does is it provides a rich and a very flexible and powerful framework for defining applications and orchestrating containers at scale. It is very well designed for key enterprise level tasks such as automated scaling, maintaining high availability, and operating in a multi platform environment. It also has a large community of users and developers with a corresponding large number of add ons and support tools. So, finally, in the third scenario, what is the best choice? This is a tricky question, and the answer is most obvious, that is, use both. The truth here is that although Kubernetes can use other container sources and runtimes, it is designed to work well with Docker, and much of Kubernetes documentation was very well written with Docker in mind. The most basic Kubernetes use case is Kubernetes plus Docker, and Kubernetes includes Docker centric tools such as Compose, which converts Docker Compose commands and settings so that can be used by Kubernetes. For its part, Docker has embraced Kubernetes and has in fact offered its very own integrated Kubernetes distribution. So the bottom line is that Kubernetes and Docker are both industry standards in their respective core areas of expertise, and together they provide a well integrated platform for container management, deployment, and orchestration at scale. It was never really a question of Kubernetes versus Docker. It was always Kubernetes and Docker, and today this is even more true.
Kubernetes Certified Associate Certification. You see, CKA or Certified Kubernetes Associated was created by Linux Foundation and Cloud Native Computing Foundation as a part of their ongoing effort to help develop the Kubernetes ecosystem. You see, this is an online-based exam which uses performance-based tests that requires you to solve multiple tasks from a command line running Kubernetes. So now you might be wondering, what is the importance of this Kubernetes certification, right? So what I'm trying to say is, like, what does the certification demonstrate? Well, you see, certified Kubernetes administrator has to demonstrate the ability to basically install as well as configure and manage the production gated Kubernetes cluster. They'll also have to understand the key concepts such as Kubernetes networking, storage, security, maintenance, logging and monitoring, application life, troubleshooting, API object primitives, and many other things. Alright, so let us now understand the benefits of the CKA certification exam. Okay, so now you might be wondering about the reasons to put so much of effort in order to get certified Kubernetes administrator exam preparation. Well, there are a lot of objectives to cover, and you should know that the certification has the benefits to gain confidence. And here are some of the major concepts or major benefits that you can achieve after being certified. First of all, CKA certification helps you make your resume unique from the rest of the pack. Companies are relying more and more on Kubernetes, thereby giving you a unique opportunity to outperform your competition. The top certifications such as CKA bring an exceptional promise for a rise in your recommendation. The companies are willing to pay more to certified Kubernetes professionals because the certification validates the ability of the candidates to address all the professional responsibilities and requirements to perform them exclusively. Passing the certification exam is rewarding experience that can contribute to personal growth in a long-term view. And the most important of all, going through a comprehensive certified Kubernetes exam preparation will make you diversify your knowledge and skills on this particular orchestration tool. Alright, so let me now share some of the tips and tricks that others have recommended while preparing for this certification exam. Alright, so start off by understanding the Kubernetes documentation portal. You can access K8s documentation during the exam for reference. And you can create a bookmark folder to access them directly during the examination. Make sure you're comfortable with official documentation, as you're allowed to bookmark documented pages in your browser and use them during your examination. But do not access any website during the examination, as only one extra tab rather than your exam tab is allowed. Attempt the questions which gives you more weightage, alright? And then try to make sure you implement more of a command line usage rather than creating a YML file manually, as this would consume a lot of time during your examination.
So need for Kubernetes, guys. Kubernetes word, it's very much inspired from like how shipping company works. Okay, basically on the dockyards you can see multiple containers are there. Okay, so initially when the industry was started, shipping industry was started, I mean, for the goods to be transported from one place to another place, they were looking for some mechanism like how we can transport the goods. Okay, and if different type of businesses are going on, okay, so how we can package them so that they will not be exchanged, or they will not be a kind of inter-exchange from one goods company to another goods company. That is the reason we have got containers concept in the market. If I will translate container concept with what we have in the industry, IT industry. So in traditional container world, we were actually packaging all the dependency of particular goods company or goods type. Same way here, I mean, when we deploy containers in IT industry, we package the dependencies of the same flavor. For example, there is Ubuntu operating system is there. On top of that, you will have XYZ components are there, configuration layer, deployment layer. So we are packaging everything basically. Okay. And these containers should be faster, reliable, efficient, lightweight, and scalable so that they can easily be transpolated from one place to another place. Okay. And they can be isolated from the host. I mean, host could be anything. Let's say your host is Ubuntu machine. On top of that, you want CentOS container, but not easily scalable. Yeah, so we have containers which can be isolated from kind of one OS to another OS. But the problem comes when you have multiple containers are there, scalability is the issue. Okay, like when you are having multiple containers, when their containers are getting scaled up, then how to do orchestration for that containers per matter. Okay, containers keep on increasing. Now, problem with scaling up the containers, a lot of problems are there. Okay, the problems are containers could not communicate to each other. Like when you have multiple containers are there. Okay, two, three problem comes when the request come for any application, how your request will go to the particular container. Okay, and let's say if you have a front end containers are there, back end containers are there, how they will talk to each other. Container has to be deployed appropriately, and containers had to be managed carefully. Auto scaling was not possible. Distributed traffic was still a challenging. So again, you have a OSS. I mean, you have a load balancer layer is there. How containers will be, distributing the traffic. Okay. So all these problems are there in net. What happens is when you have multiple containers are there, these problems comes. Okay, and that we have to overcome with any of the two. Now, when you have such problems are there, okay, you should make sure that you should use any orchestration tool. So for that reason, we have one of the orchestration tools are there, a container management tool. So there are a lot of container management tools are there in the market. Apart from Kubernetes, what other container management tools are there in the market? Apart from Kubernetes, not Kubernetes I'm talking. Apache Mesos is there, and we have Docker Swarm is there, right? These two flavors were there in the industry for quite long. Now for Kubernetes, multiple flavors has come. So what is needed? A container management tool, Kubernetes. Okay, so what is a Kubernetes? Kubernetes is an open source container management tool which comes a container deployment, container scaling, and container load balancing. Okay, and it works very fine with public clouds, on premises, hybrid. So now container has huge flavors are there, guys. Whatever you can think of, that sort of flavors are there. So if I talk about container world, okay, so as the slides explain, when you have one container is there, okay, single container is there, it's easy to manage. Okay, when you have multiple containers are there, C1 container, C2 container, C3 container, C4 container, C5 container, okay, C6 container. That time we need a lot of orchestration and we need container management tool. So guys, when we talk about the container management tool, what is the basic tool which is being used in the industry, which you can install on premises, which you can install on cloud, anywhere you can install. Okay, so we have kubeadm is there. Okay, kubeadm is there, which is being used, which is the on premises. I mean, which you can use it anywhere you can use it. Okay, Now, over the period of time, guys, a lot of new flavors has come of Kubernetes just to save your time. I mean, Kubernetes setup is little tedious task. Okay, so a lot of flavors has come. What are the flavors are there which has come apart from KubeADM in the market? So yeah, Minikube is one of the flavor. Minikube is one of the flavor. Afterwards, we have, which is the flavor for AWS, guys? EKS, right? Elastic Kubernetes Services. What is the flavor for Azure? It's AKS. What is the flavor of Google is there? GKE is there, right? Apart from that, guys, I mean, we have 5 flavors, 1, 2, 3, 4, 5. Apart from that, if you do little research, you will get to know one more ways are there to install the Kubernetes. So what happens is if you want to install Kubernetes master and a slave, so Kubernetes image itself has come. Okay, if you get chance, you can do this reading. Kind image, okay, images has come. So readily available images are there. Kind is one of the flavors. So 1, 2, 3, 4, 5, 6 flavors are there in the market readily available, and multiple frameworks are there who are highly or heavily using this Kubernetes. One is the OpenShift. OpenShift is also using complete Kubernetes flavor. Apart from that, guys, if you read little more, Cloud Foundry, they are also very much getting dependent on containers world, containers and Kubernetes world. Okay, Cloud Foundry is also there. Now, a lot of new inventions has happened in last 2 years. For the containers installations, we have Helm charts, which has come into the pictures. For monitoring purposes, we have different dashboards has come into the market. For example, Rancher is the dashboard. And for container-based deployments, we have one more tool which can be used for the CI tool also. Spinnaker is also come into the market. Spinnaker has also come into the market. So if you see, a lot of things are there, a lot of inventions are there which are happening into the containers world. The reason I'm highlighting all these things are that you should not be very much dependent on what is happening now. You should be knowing what would be happening down the line after 1 year and where industry is heading. So guys, a lot of new features are coming. So I mean, today we will focus more on the KubeADM, but if you get chance, explore these options. Okay, this is not the ending of Kubernetes. Kubernetes is much more what even I can think of. Many things are there which I know till here, but when you do the research, you will get to know so many other products are also there, which are highly getting reliable on Kubernetes. Fine. So guys, this information you will not get on internet. This is my own research, but yeah, definitely it will be useful for you. Okay. So as I told, don't stick with this guy. This is not the end of the world. This is just starting of the world. So Kubernetes product, it's written in the Go language, huge community is there, and later it's donated to CNCF. Okay. So CNCF is the organization nowadays who's maintaining entire Google, this Kubernetes products. So what is getting deployed in the Kubernetes? Is it a container or something else? It's a pods, right? It's pods. The difference between Docker containers and the pods contains containers, right? Pods contains container. Pods are nothing but they are the combination of multiple containers. For example, in Kubernetes cluster, instead of containers, pods are getting deployed. Pod can have multiple container. Okay. So why multiple containers are there? One container may be called sidecar container. Okay. One container is a main container. So sometimes what happens is, I mean, if you want some dependencies to be downloaded before your main container is getting invoked, you can use this sidecar container. So this pod is a combination of multiple containers. You can keep it one container, you can keep it multiple container, all depends upon your wish. So before I'll go and explain what is the difference between swarms and Kubernetes, okay, let me walk you through the concepts of the Kubernetes. Okay, so when you have single machine cluster is there, you can go with Minikube. When you have multi-machine cluster is there, you can go with KubeADM. And how the architecture of Kubernetes works is you will have a master is there, you have a slave node is there, and you will have all the places container runtime is there. So if you go to, this is a single machine cluster. If you go to multi-machine cluster also, architecture would remain same. You will have one master will be there and one node will be there. So you can visualize from here. You will have your master will be here and you will have your nodes will be here. And in your nodes, you will have your pods running. Okay, you will have your pods running. Now, what is a pod? Pod is nothing but it's a logical grouping of your containers. Okay, you can have multiple containers at the same time. You can have different containers at the same time. All depends upon you, how you want to utilize your pods. But your entire pod will have same IP address. So this is your Kubernetes master is there, and this is your Kubernetes slaves are there. Sometimes we are calling it as a slaves, sometimes we are calling it as a nodes also. And when when Kubernetes were getting launched initially, we used to call them minions also. So now the correct word is nodes. Yeah, that's what we are calling it as a cluster. When you have master is there and you will have nodes are there. So on the master, you will have multiple components are there. On the nodes also, you will have multiple components are there. When you'll be installing this kind of Kubernetes product, you'll see one by one, each and every component is getting installed. So this is what your cluster look like, but what each and every component does. So this is more clear architecture. Single node cluster means many VMs, no one VM, and in that VM only we will have master is there, we will have slave is there. But that's there for very small scale applications. Okay. Yeah. So this is the correct architecture, guys. This is a very extended architecture. Okay. In your Kubernetes master, you will have multiple components are there, and in your slaves, you will have multiple components are there. So let me tell you importance of these components. So guys, which component is there which is communicating from master to slave, which is talking to slave and master both? API, right? So API server is the guy who is responsible to talk to each other. So there is a command is there, kubectl. When you type the kubectl, actually this command will be going and talking to API server. So it's nothing but it's a combination of multiple REST APIs, which talks to the slave, which talks to the master. So whatever service you will be creating, node port service and multiple services are there, that will be IP of your cluster. Okay, guys. So here, if you come, so apps server, this is the guy who's communicating to master and slave. If this guy master gets destroyed because of any reason or demolished because of any reason, do you think we can restore this entire cluster? Yeah, etcd has the current state, so you have to preserve etcd, right? Right. So guys, your etcd, this guy etcd, he has the metadata of your cluster. So there is a concept is there called multi-master node, MMN. Okay, you can do some reading on the internet. When you want to go for fault tolerance, you can go with multi-master node concept, multi-master node. So if you want to preserve your data, a metadata of your cluster, then you should preserve your etcd. So guys, how many of you heard about secondary name node in Hadoop? Have you heard about secondary name node of the Hadoop? So secondary name node also preserve the data of etcd. Etcd will be getting destroyed if master destroys. But since we are taking a backup of the etcd, if master destroy also, we can recover everything from etcd. It's like when your plane crashes, your metadata of the plane is there in the black box. With that, you can retrieve why it was crashed, all the important information you can retrieve from there. So it's your black box, kind of a black box. Not exactly, but kind of a black box. Now guys, we will make sure that whatever pods are assigned, they should run on the particular node only. So that will be managed by a guy called Kubelet. Kubelet is nothing but this is a local agent is there, which will make sure that your pods are running inside your node, right? Now for each machine to access, there is a networking component is there. We are calling it as a kubeproxy. So kubeproxy is a different for each and every node machine. But how two node machines will talk to each other or two node pods will talk to each other, for that we have something called plugin networks are there, or CNIs are there, content network interfaces. Content network interfaces. So there are multiple type of content network interfaces are there. Okay, so CNIs are responsible, these plugin networks, to talk two machines to each other. Container network interfaces, CNIs. Now who controls this entire cluster? It will be controlled by controller manager. There are 4 or 5 type of controller managers are there. They control the cluster. Now who schedule the pods to be started on a particular node? That will be done by scheduler. This is the Kubernetes master is there. This is Kubernetes slaves are there. This is the API server that expose the Kubernetes APIs. We have controller manager is there, which is responsible to control the cluster. We have scheduler is there. This guy schedules the pods to be created on the particular node. Kubelets are there, which are nothing but the agent, which makes sure that your pods are running on a particular machine itself or node itself. You will have kube proxies are there. This is their local proxies for each and every host. We have something called plugin networks are there, which are nothing but making sure that how pods will talk to each other. We have etcd is there, which is nothing but the metadata of the cluster. Now, different type of controller managers are there. Node controller, responsible for noticing and responding when any nodes goes down. So if any node goes down, this guy is responsible to let the cluster know. Replication controller, how many replicas should be started, like 4 5 of a pod, that will be taken care by this guy. There's something called endpoint or services, which I just told, which is the IP address of your cluster. Okay, that will be managed by this endpoint controller. There is something called security or RBAC accesses token controllers that will be taken care by service account and token controllers. So get pod summary. Pod is like a host. Containers in the pod share the same IP and port space. Pods are not durable. Pods management are done through API. Pods are very low level primitive, necessary to know but not commonly used directly. I mean, you should just know if you're creating a pod. I mean, not heavily used. Labels, I mean, you can apply key value, client can attach key value paid to object in the system. These become the labels. So let's say out of 100 nodes, if you want to label few of the nodes, you can label them, and selectors will select your items or the pods as per the labels applied. So this is more deeper concept. Controllers, they're used to manage the container, this entire cluster. So as we just saw, there are 4 type of controllers are there: node controller, replication controller, endpoint controllers, and token controllers. Services are there. Services are nothing but this is the kind of a load balancer for you. So someone was just asking what is the IP address of my cluster. So your services, 4 type of services are there: node port, cluster port, 3 type of, sorry. So they'll be used to create a service for you. So far guys, this is very clear what is Kubernetes, what is in and out of the Kubernetes. We understood the architecture also. A few more points. So these are some features are there. I mean, service discovery and load balancing, I just told. Self-healing, if any pod goes down, any node goes down, okay, self-healing. Horizontal scaling, HPA. Okay, if let's say your throughput is getting increased, you can go with HPA. Secret and configuration management. Again, your RBAC policies are there, and we have something called config maps are there. So sometime if you want to encrypt your passwords credentials, you can go with this. Automatic rollbacks and rollouts. Okay, so we have something called rolling updates are there. When you are deploying your cluster with some of the pods, it will never allow your cluster to go down. I mean, there will be no downtime. So there are different type of deployment techniques are there, like A and B technique is there, canary deployment is there, multiple type of techniques are there. Storage orchestration, there is something called persistent volumes are there, PVCs are there, which will help you to persist the state of the container logs and something. Batch execution, if you want to run a number of containers together, batch execution. So these are couple of features are there. So what is Kubernetes and what is not? So Kubernetes is not to be compared with Docker. It's an orchestration of the Docker for application with the simple architecture, for containerizing app. So this is not for containerizing app. This is for maintaining your containers. Let's say Jenkins is a tool. Can I containerize it with the help of Kubernetes, guys? No, for that we need containers only, right? Yeah, okay. So to be compared with Docker, no, this is nose. And what is actually Kubernetes is, it's a robust and reliable best solution for scaling up container backed by huge community, a container orchestration platform. So guys, I told that now it's been donated to one of the community. What was the community name? CNCF, right? Now I will show you how to create one cluster. So installation of Kubernetes is complicated and time consuming. Yeah, but nowadays it's not complicated and time consuming. Yeah, cloud, now cloud flavors has come, AKS, EKS, GKE, right? And I told you that nowadays Kubernetes has come with the image also. What was the image product? Guys, what was the product I was telling that now Kubernetes has come with their images itself? Kind, right? Kind has come. So this is a contradictory statement. Easy and fast, let it be. GUI available, GUI not available. Yes, Kubernetes has a GUI available. Kubernetes has its own dashboard available. You can use external dashboard also. Scaling up is slow as compared to Swarm, but guarantees stronger cluster state. So, I mean, scalability, I feel it's good in both the places, but Kubernetes has more kind of reliable components are there. It doesn't easily crash automatically. Load balancing requires manual service configuration. Yeah, previous provides built-in load balancing techniques. So this feature I'm not aware of, but yeah, here we know that services concepts are there, and there is something called ingress controller is there if you want to write some redirection rules. Updates, rollbacks, process scheduling to maintain service while updating, progressive updates and service health monitoring throughout the update. Data volumes only shared with containers in the same pod can be shared to any other containers. Yeah, so what happens is it can be shared to in the same pod, and that's why we have sidecar container is there to collect that information and pass on to any other place. Okay, so there is a product is there called EFK, Elasticsearch, FluentTD, and Kibana. EFK. So what it does is the sidecar container will be nothing but FluentTD. It will collect the data from the another container and pass into Elasticsearch. Logging, inbuilt logging and monitoring tools, third-party logging and monitoring tools. So every tool has different pros and cons. It all depends upon which tool we want to pick up. But nowadays, guys, Swarm is getting killed. Hardly I have seen anyone is using Swarm. Everyone is moving towards Docker, Kubernetes. Okay, so guys, what we will do is we will create a cluster of two machines. One is a master and one is a slave. So let's fetch each and every machine. So let me pick up this guy K master. Let me give connection 30. Let me give colors, system colors, appearance, windows, change, open. So guys, I have two machines are there. So I logged in the first machine. Now what I will do is I will change the name of the machine. How to change the machine name? Which place I have to go? You can give host name command, or I can go to nano or vi anything, vi etc host name. And I will change the machine name from this IP address to uh, kmaster. Okay. Okay, this place I have changed. Now I have to mention which machine I have designated for what purpose. So I have to mention the host name. So what is the location of the host file? etc host, right? So I will go to etc host. Okay, and here I must be adding, which is my kmaster, which is my kslave. Kslave. I'll pick up my IP addresses. So this is the private IP address of my kmaster. So I will go here, home, I'll paste it, space. Now I'll pick up the IP address of my slave. Okay, let me copy this guy so that I can copy to my other machine also. Okay, so what I've done is, guys, I have added the private IP address of both the machines, as in one is a K master for me, one is a K slave for me. Now what I'll do is let me reboot this machine so that everything should be reset. Now I will go and pick up my another machine, which is a K slave. This is the public IP of my K slave. Okay, let's make it as a K slave, etc host name. Okay, I will make it as a K slave. And let me add here who is my master, who is slave. Okay, let me reboot the machines. Now in my both the machines, I have added their names. Now I need not to bother which machine is my master machine, which machine is my slave machine. You can see here, K master is getting mentioned here. Okay, now let me go and restart this machine. Let this machine be coming back. Yeah, okay. So this is my K slave machine. Let me make this guy here. You have your K master. We have designated it to be a K master machine. Now we have designated this guy as a slave machine. What is required to have in both the machines? Container environment, guys. Container environment. We need a container runtime environment. Okay. So what we have to install? Yeah, Docker engine we have to install, right? So we need a container environment. To have a container environment, we need Docker engine. So first what we have to install is, we have to install container platform in both the machines. This is the first step. This is the first step. Okay. Now guys, there is an article is there which I picked up from internet. Probably you can also use it. This is a good article and this seems to be working article. I picked up from here. Yeah guys, this is the link. You can also follow this article. This article has one issue. I will fix it. I will tell you what is the issue, where to fix it. So this article initially says that you make the changes in the host file, you add the entries. So this part we have done. Now there is a swap memory is there, which you have to switch off. So I can switch off the swap memory. Okay. Now we should install Docker. So we can pick up these commands. Okay. This is installing some certificates, which is nothing but kind of preparation for our Docker one. So guys, here when I'm installing this, it's not actually installing anything, right? So for that, what we can do is we have to update our package. So this is the command to update our package. So let me update my package. Okay. And now I can install this command. Yeah, now it's installing. Means prerequisite to this command is the package has to be upgraded. Swap off we are doing, Virendra, what happens is, this is a feature of the operating system. It allows to distribute your memory, swap your memory. So we have to switch off this feature so that whatever memory is there, it should be focused completely for our cluster. So this certificate we have installed. Now there is a Docker GPG keys there, which has to be downloaded. This is downloaded. Repository has to be added for Docker. This is being added. How many type of Docker engines are available in the market? How many engines are available in the market? One is community edition, one is enterprise edition. Okay. So you can see here in this link, they are installing C, means community edition. Community edition is open source and enterprise edition is a paid edition. So we will go with open source one. So now our Kubernetes Docker engine has been installed. So if I type here Docker version, you can see unit and server both are installed. So we are good here. And it's saying Docker engine community, it's installed. So in my master machine, this Docker engine is installed. Let me go to my slave machine, okay, and run one by one each and every command. So first I have to update it, let it be updated. Then I will go and add the certificates plus let me swap up the memory. Small scale cluster, it's not required, but when you're going for a commercial clusters, do this step. Okay, this is getting added. Then we have to add this GPG key. Okay, now we will add our keys in the registry. Now we will go and upgrade the package. And then afterwards, we will go and install the Docker Community Edition. Okay, now if I check here whether my Docker engine is installed. Okay, so that is installed. So we have done with the first, this guy is installed. Okay, this guy is installed. Now what is the second step, guys? Now what has to be installed in KM master? Now Kubernetes cluster. Okay, Kubernetes cluster has to be installed in both the machines. What are the components of the Kubernetes cluster, guys? kubeadm, kubelet, okay, kubeadm, kubelet, kubectl. Okay, so kubeproxy controller, it ships automatically if you install these three components. So let me go and pick up this installation of this Kubernetes cluster, this kubeadm, kubectl, kubelet. So let me add this key. First we will install in Kubernetes master, then slave. The repositories we have added. Now update our machine and then install kube these things. Now we'll install kubelet, kubeadm, kubectl. Yeah. Now you can see here, guys, in the last logs, kubectl, kubeadm installed. If I'll trigger this command again, okay, this will say that this is already being installed. Kubelet, kubeadm, kubectl. Okay. Now same thing we have to install on kslave also. Guys, I'm going very slow with the installation because if you remember the steps, okay, it will be very easy in the future. Okay, so kubelet, kubeadm, kubectl is getting installed. Okay, so you can see here kubelet, kubectl, kubeadm is installed. So this is completed till here. Okay, this is completed here. Both the platform has got container one, both the platform got Kubernetes, this thing also. Now we will see what is the next step. So guys, we have to designate one of the guy to become a master. So for that we have a command is there. This is the command, guys. Kubeadm init. This is the command is there, guys. So what they're saying is they are utilizing, okay, one of the master, okay, as a Kubernetes master, and we have to pass that master, and all the components which are internal to the Kubernetes has to be started in IP range. So they're passing on IP range. So private IP address of our master is this one. Okay. Now we will pass this to my master, which I'm designating as a master. Okay, now guys, this output of this command will give you a command which will allow your slave machine to be added as a part of your cluster. So guys, now if you want to start your cluster, you have to run these three commands. I can copy it. Okay, your cluster is ready now. Three commands we have added. And if you want your slave machine to join this cluster, then you have to run this command. Okay, so I just kept it safe. Now let me run one by one my command to start the cluster. Okay, we can check once again whether all the three commands has been run. Guys, let me run these commands again for the safer side. 1 minute. Okay, So these three commands have run. Now we'll see what is the next. Now we can see this command, like how many nodes are there in my cluster? How many nodes are there? One node is there. One node is there. So let me see. Yeah. So it's just saying K master is there, but it's not in ready state. Role is a master. Why it's not in ready state? I'll tell you why it's not there. If I will run this command, you will see few of the pods of the master. They are not in running state. They are in pending state. They're in pending state. Okay, because their core DNS is pending. So guys, when you see your core DNS level pods are pending, it means that your CNI is not installed. Okay, it means your CNI is not installed. Container network interface is not installed. And that's why this K master is saying not ready. So what is the solution is? Solution is, guys, you have to install your CNI. So there are multiple type of CNIs are there. As a Flannel is there, Calico is there, NetWeaver is there. I will go with the Calico because Calico range is very much similar to what range we are giving in 192.168.0.016. So in this article, there is a problem is there. The Calico plugin which they have given, it's not the correct one. So let me install the CNI. Yeah, so you can see CNI is installed. Now if I will go and check Kubernetes get namespaces, you will see the running pods, I mean pending pods will becoming now running pods. Okay, you can see the pending has coming as a running has coming as a pending. So this will be stabilized in some time. You can see, yeah, you can see all the pods are running. Now if I will type here my cluster nodes, you will see now it will say your master is kind of ready. Earlier it was showing not ready. Now you can see it. This is ready because now all the pods which are required for master to start, they are kind of ready. So these all are, you know, API server, controller, proxy, scheduler, core DNS, Calico. These are required to start your cluster, especially master. Okay, so whatever prerequisite were there, like when I asked what are the components are required to master, proxy, scheduler, controller, API server, everything is ready. So your master is completely 200% ready. Now, what is the next step, guys? Now your cluster is ready. In cluster, your master is ready. Now, what you can do is you can go to your slave machine and you should run that command which allows your slave machine to be added as a part of your master. So I will pick up this command. This command will go and add my cluster, this slave machine into my cluster. Okay, so this node has joined the cluster. Now we can run this command kubectl get nodes. Now guys, in my master, how many nodes it should be showing? 2 nodes it must be showing, right? You can see here k master slave, both are there, both are in ready state. Now your cluster is ready, guys. Now if you want, you can deploy your, you know, YAML files over there. Okay, so let me complete this diagram. Now you should designate this guy to become master, designate to become master, and then you should make this guy as a CNI installation. Okay, afterwards you will come here and you will ask this guy to join the cluster. Okay, so guys, I mean, this was just a orientation session.
What is kubectl? So the kubectl is simply a command line interface. So the kubectl command line tool lets you control these Kubernetes clusters that you create. Now for configuration, kubectl looks for a file named config in the home.kube directory. Here you can specify other kubeconfig files by setting the kubeconfig environment variable or by setting the kubeconfig flag. This overview covers kubectl syntax, describes the command operations, and provides various common examples. Now, if you look at the syntax of the screen, which is used to run kubectl commands from your terminal window, you can see that it is simply kubectl, command, type, name, and the flags, where command specifies the operation that you want to perform on one or more resources. For example, if you want to create, get, describe, delete, any of that. The next one is type, which specifies the resource type. Resource types are case sensitive, and you can specify the singular, plural, or abbreviated forms. Now, for example, you can, type in the following commands which produces the same output. For example, kubectl get pod1, kubectl get pods pod1, kubectl get po pod1. All of these commands produce the same output. Name, on the other hand, specifies the name of the resource. Names are case sensitive. Now, if the name is omitted, details for all the resources are explained or displayed. For example, kubectl get pods will really give you an entire overview of all the pods that are running on your cluster. When performing an operation on multiple resources, you can specify each resource by type and name, or specify one or more files. To group resources, if they're all the same, you can use the syntax type1, name2, etc. And to specify multiple resource types individually, you can just use the syntax type1 slash name1, type1 slash name2, type2 slash name3, etc. Flags, on the other hand, specifies optional flags. For example, you can use the -s or -- server flags to specify the address and port of the Kubernetes API server. Now that we know what is kubectl, which is just a command line tool that lets you control Kubernetes clusters, and also its syntax in detail, let's move ahead and talk about what is Minikube. So Minikube is a tool that lets you run Kubernetes locally. Minikube runs on a single node Kubernetes cluster on your personal computer, which includes Windows, Mac OS, and Linux PCs, so that you can try out Kubernetes or for daily development work. All you need is Docker or similarly compatible container, or also a virtual machine environment, and Kubernetes is a single command away. That is, you can use Minikube start to get it running. The advantages of Minikube is that it supports the latest Kubernetes release, it is cross-platform, and it can be deployed as a virtual machine, a container, or on a bare metal. It also contains multiple container runtimes. So Minikube is basically a tool that lets Kubernetes run on your local machine without any installation except for the Minikube library. So in summary, Minikube is a tool that lets you use Kubernetes on your local machine without any installation except for the Minikube library. It takes advantage of your local hypervisor and launches a virtual machine that runs Kubernetes in a single node. Now, to install the Minikube and kubectl, you can get the latest release or build from the official website. So without much ado, let's go and install them. So now currently I'm on my Oracle VM VirtualBox and we are working on Ubuntu. So we'll be installing the kubectl on Ubuntu, and we'll be installing using native package management, that is Debian-based distributions. So the first thing that we're going to do is we are going to update the apt package index and install packages needed to use the Kubernetes apt repository. And for that, I am going to type in the command sudo apt get update. Okay. So I have the list of commands already on my notepad. So I'm just going to copy this command and I'm going to paste it. So new packages will be installed and also the existing ones will be upgraded. So once the installations and updates have been done, I'm just going to clear the screen. And what I'm going to do now is I'm going to download the Google Cloud Public Signing Key. Okay, and for that, we're going to use this command, followed by which we can add the Kubernetes apt repository. So I'm going to copy and paste this command. So finally, I'm going to update the app package index with the new repository and install kubectl. Now, once it's successfully installed, in order for kubectl to find and access a Kubernetes cluster, it needs a kubeconfig file which is created automatically when you create a cluster using kubeup.sh or successfully deploy a minikube cluster. Now, by default, kubectl configuration is located in the .kube/config. So now that we've installed kubectl successfully, I'm going to test to ensure the version that we've installed is up to date. So for this, I'm going to execute the command kubectl space version space -- client. Now we can see the Git version and we can see the major version. All of the information is given here. We have successfully installed kubectl. Now let's clear the screen. So now that we've installed kubectl, let's move ahead and install Minikube to run a local Kubernetes instance. So as we've already talked about it, Minikube is a tool that lets you use Kubernetes on your local machine without any installation except for the Minikube library. You will have to install Docker and you'll have to install VirtualBox before you can install Minikube. Otherwise, Minikube will not work. So once you do all of that, then all you can do is you can just install the Minikube library into your system. So for this, we're just going to use these commands. I'm just going to copy them and paste them. And once Minikube is installed, you can verify the version that is running the following command, that is Minikube version. You can see that we've installed version v1.20.0. So you can start the Minikube by using the command sudo minikube start. Now, once the startup phase has finished, which will take some amount of time, your Kubernetes client, that is kubectl, will have a Minikube context and will automatically start using this context. So you can also see that kubectl is configured to using Minikube cluster and default namespace by default. We'll talk about namespace in a bit. Now let us just check what nodes we will have in our cluster, which will return the Minikube hostname. And for this, I'm just going to clear my screen and type in the command sudo kubectl get nodes. You can see there is a node Edureka. Its status is ready. So let us check out each of the commands that are available, some of the basic commands that are available. So first one is the get command. So what it does is the first command, it lists all the pods in PS output format. Okay. There is another type of command which lists all pods in PS output format with more information such as the node name. For that, we can just use the command kubectl get pods -o wide. Currently, we do not have any resources in the namespace, so it's not going to display any. Now, to test that kubectl can authenticate with and access your Kubernetes cluster, you can use the cluster-info command. So you can type in the command sudo kubectl cluster-info. And if kubectl is successfully authenticated with your cluster, you should see the following output. So kubectl is configured using kubeconfig configuration files. And by default, kubectl will look for a file called config in the home/.kube directory. Now, to view your kubectl configuration, you can use the view sub command. So I'm just going to type sudo kubectl config space view. And this will give you the API version, that is v1, the cluster, that's Minikube. So you can see the API version, that is v1, you can see the clusters, you can see the contexts, and you can see the correct context, kind, preferences, users. Okay, now I'm just going to clear the screen. Now, to fetch a list of clusters defined in your kubeconfig, you can just use the get-clusters command. So I'm just going to type in sudo kubectl config get-clusters. So the output will be the list of clusters that is defined in our kubeconfig file. And as you can see that in the output is the Minikube. So you can also delete a cluster from your config using the delete-cluster command. I'm not going to show you the output of this, but I'm just going to type in the command. Okay, so what this does is it only deletes the cluster from your config file. Okay, it does not delete the actual Kubernetes cluster. So this is really important to know. Now moving on, you can also see a list of all the configured contexts. For that, you can just use the command config get contexts. And what it does is it gives you the name of the cluster and the authentication information and the namespace. Okay, this is like just, it gives you like a list of contexts that are available. So I haven't explained you what exactly a context is. A context in Kubernetes is an object that contains a set of access parameters for your cluster. It consists of a cluster, namespace, and user triple. Contexts really allow you to quickly switch between different sets of cluster configurations. If you want to see your current context that you are working on, you can just use the current context command. Okay, and you can see that we are currently on the context minikube. Okay, now to set a particular context, you use the set context command. So for this, I'm going to type in the command set context 1. So I'm just going to name my context 1. Cluster dash cluster is equal to your cluster name. I'm just going to name this cluster 1. User is equal to user 1. And you can also have a namespace. We know that we have one namespace that is our default namespace, right? So I haven't really talked about namespaces either. So let me explain it to you now. So Kubernetes uses namespaces to organize objects in the cluster. You can think of each namespace as a folder that holds a set of objects. By default, the kubectl command line tool interacts with the default namespace. Now, if you want to use a different namespace, you can pass kubectl the dash namespace flag. So we're going to set a context, and we are also setting the namespace for that particular context. So I hope this is clear. So you can see that context 1 has been created. Now you can switch between contexts with the use context command. So for that, I'm just going to type use context, and I'm just going to type the context name. So we created a context that was named context 1. So I'm just going to switch to that. So it says switch to context 1. If you want to check the current context, we can just use the current context command, and you can see that it has been switched to context 1. Now I want to switch back to Minikube. I'm going to do that. And it says switch to context Minikube. That's great. You can also check out the list of contexts using the get context commands, and you can see that we have 2, that is Minikube and context 1, and the current one is where the star has been placed to. Okay, that is Minikube. Now, if you want to delete a particular context, we can do that. Okay, we will use the sudo kubectl config delete context and the context name. So we'll just name it context 1. Okay. Now it says deleted context 1 from the particular location. We can also view the contexts that are currently present, and we have only one, that's Minikube. So that's great. This is for contexts. So I'm going to repeat this again. A context in Kubernetes is an object that contains a set of access parameters for your cluster. I hope that's clear. Now let's go and check out namespaces. Okay, is basically again an abstraction that allows you to subdivide your cluster into multiple virtual clusters. Now by using these namespaces, you can divide cluster resources among multiple teams and scope objects properly. Now, for example, if you have a development namespace for development and test workloads and a production namespace for production workloads, so you can really divide the cluster resources among these, 2 teams that we have. I'm going to clear the screen. So what now we're going to do is we're going to fetch and print a list of all the namespaces in your cluster, and we are going to use the get namespace command. So sudo kubectl get namespace. So you can see the output as default, kube node lease, kube public, and kube system. Okay, now if you want to set a namespace for your current context, our current context is Minikube, you can use the set dash context space dash current command. I'm just going to show that, and you can see the context Minikube has been modified. Okay, now if you want to create a namespace, you can just simply use the create namespace command. So I'm going to use the command sudo kubectl create namespace 2. That is, namespace 2 is the namespace name that you would like. You want it to be 3, you want it to be 4. That's all up to you. I'm just going to name this namespace 2. And you can see that namespace 2 has been created. Okay. Now we'll just list out all the current namespaces. And you can see that the namespace 2 has been created and it is active, and it has been created 11 seconds ago. Now you can also delete a namespace by using the delete namespace command. Deleting a namespace will delete everything in the namespace, including running deployments, pods, and other workloads. Only run this command if you're sure if you'd like to kill whatever's running in the namespace, or if you're deleting an empty namespace. So you have to be aware of this. So what I'm going to do is I'm going to delete namespace, and I'm going to delete namespace 2. Okay. You can see that namespace 2 has been deleted. That's great. And I'm just going to view the namespaces that are currently there using the get namespace command. And you can see that our namespace 2 has been deleted successfully. I'm going to clear the screen. Now, if you want to fetch all pods in a given namespace or to perform other operations on resources in a given namespace, make sure you have to include the dash dash namespace flag. Okay. So say that I want to get the pods of namespace default. And it says no resources are currently found in the default namespace, which is fair enough. So I'm just going to clear my screen now. And we will be talking about another command, the API -versions command. So what this does is it prints the supported API versions on the server in the form of grouper version. Okay. And for that, we're just going to type the command sudo kubectl API -versions. And this just gives the supported API versions on the server. Okay. So these are some of the most basic commands that are available. We used create, we used get, delete, we used describe, API versions, cluster info, and there are a lot more. But to just get started and to just understand how Kubernetes works, you will have to start off from the basics, because this is a very vast topic. I think that you cannot go into detail that easily. You will need to have some experience over time with all of these commands that you use and their respective flags and their respective parameters that are involved here.
Now, anybody working with Kubernetes must also have an understanding of Kubernetes cluster, as that gives the basics for networking. So let me tell you what exactly Kubernetes cluster is. Now, the basic fundamental behind Kubernetes is that we can enforce what's called a desired state management, and really what that means is that I'm going to feed a cluster service in a specific configuration, and then it will be up to the cluster services to go out and run that configuration in my infrastructure, right? So one of the main components of the Kubernetes clusters is the API that sits in front of all of these services. So this is like the building block of a system, and the second building block of a system is a worker. So what is a worker? Well, a worker is just like a container host. So one unique thing about the worker or a container host in Kubernetes environment is that it does have a kubelet process, and that is responsible for communicating with the Kubernetes cluster services, and this whole setup with the workers and APIs and the pods is known as Kubernetes cluster. Now, let me explain you with an example here. So you can see this deployment file, right? So this deployment file has all the configuration that is required to feed into the cluster services. So it has pods, it has replicas, each pod has various container images which are going to be fed to the cluster services, and then it will be up to the cluster services to divide the pod and replicas into the worker nodes. So in this example over here, we have two pods, with the first pod having two container images and three replicas, and the second pod having only one container image and two replicas. Now, once this configuration is fed to the Kubernetes cluster services, it will be up to the cluster services to schedule these pods and the workers. So as you can see over here, The worker 1 has pod 1 replica 1 and pod 2 replica 2. The worker 2 has only one pod with one replica, and the third worker again has two pods with two replicas. So this can depend on the cluster services completely. Now, the main aim of cluster services is to make sure that the configuration is running across all of the containers or the workers. Now, you must be knowing about Docker, right? When Docker was there, why did Kubernetes come up? Because this has an approach of networking in a different way. So there are mainly four distinct networking problems to solve with Kubernetes that we have to deal with. The first one is the container to container communication. The second one is the pod to pod communication. The third one is pod to service communication. And the fourth one is external to service communication. So don't worry guys, I'll discuss each one of these communications in this session. So let me brief you about each one of them one by one. Now, container to container communication is basically the communication between two container images. The pod to pod communication is the communication between two different pods having various images and the replicas. The pod to service communication is how a service enables a pod to communicate with any other pod. And external to service communication is how something out of the cluster can communicate something which is inside the cluster. Now, before I get into the depth of all these, let me tell you the fundamental requirements of any network implementation in Kubernetes. So all the containers can communicate with containers without NAT. All the nodes can communicate with all the containers without NAT, and it's also vice versa. Not only this, but the IP that the container sees itself is the same IP that others see. So these are some fundamental requirements that you need to understand before you start with Kubernetes networking. So now, as I was talking so much about Kubernetes networking, let me tell you what Kubernetes networking is all about. So Kubernetes networking mainly deals with the communications between pods, services, and external services to the one in clusters. So it's all about communications. So for your better understanding, I've divided the networking concepts into containers and pods, services, and ingress network. First, let's start with containers and pods. Now, what do you think pods are? Well, pods are nothing but the basic units of Kubernetes applications that are built from. So a pod consists of one or more containers that are allocated on the same host and are configured to share a same network stack or other resources as volumes. In simple terms, we can just say that the containers in a pod can reach each other on the local host. So for example, if a pod has 5 container images, all the container images can interact with each other on the local host. Now let's consider an example here. So starting from the top, we have a physical network and a Docker bridge connected to it. So attached to that, we have two containers, one working at virtual Ethernet 0 and the other one working at virtual Ethernet 1. Now both these containers are on the same logical network as the bridge, and both the containers can communicate the bridge as long as they can discover the other container's IP address somehow. But this doesn't get the concept of shared network pod. So since namespaces are very flexible, Docker can start a container, and rather than creating a new virtual interface for it, it shares the existing interface. So both the containers have the same virtual interface and both are addressable and can hit ports opened by the other in the local host. So that's how two containers communicate between each other. But this can cause one problem. The problem is that this set of processes can take full advantage of decoupling and isolation of services, while at the same time collaborating the simplest possible networking environment. So to implement this, Kubernetes implements this pattern by creating a special container for each pod whose only purpose is to provide a network interface for the other containers. So when you use the pause command, it suspends the current process until a signal is required. So it's basically like the heart of the pod, providing all the virtual network interfaces that all the containers will communicate to use with each other and outside the world. Now you must have understood how two containers communicate with each other. But how will two different pods communicate with each other? So will two pods communicate with each other with the intranode network or the internode network? Now, before I talk about the two types of communication within the pods, let me introduce you to the components of pod network. So on every Kubernetes node, there is a root network namespace, a pod network namespace, and a Linux network bridge. Now, Each pod has its own network with a virtual Ethernet pair connecting it to the root network. So this is basically like a pipe pair with one end in the root network and the other end in the pod network. Now this is done for all the pods on the node, and to enable pods to talk with each other, the Linux Ethernet bridge is used. So now that you have understood the pod network components, let me start with the two types of communication, and let me start with intra-node pod network. So intra-node pod network is basically the communication between two different pods on the same node. So suppose we have two pods over here, pod 1 network and the pod 2 network, who have their own root network with the virtual Ethernet pair, right? So suppose just assume that a packet is going from pod 1 to pod 2. The packet leaves pod 1 network at Ethernet 0 and enters the root network at virtual Ethernet 0. Then it is passed on to the Linux bridge, which discovers the destination by using an ARP request, and then it finds out that the destination is on port 2. So the virtual Ethernet 1 says that it has the destination IP, and the bridge now knows where to forward the packet. So once the bridge knows where to forward the packet reaches the virtual Ethernet 1 and crosses the pipe pair and reaches the port 2 network. So that's how two ports communicate within each other on the same node. They just have to pass through the Linux bridge to know where is the destination IP, and then automatically the virtual Ethernet, which has the destination IP, takes the packet and forwards it to the pod network. So guys, that's how two pods communicate on the same node. Now, if you have two pods on two different nodes, how will they communicate with each other? So this is enabled by routing, and this is also known as the inter-node pod network. So as we all know that every node is assigned a unique CIDR block for the pod IPs, each pod has its unique IP, and that does not conflict with the pods on the other node. So as the same way that the cloud provider routes tables and makes sure that the packet reached a correct destination, the same thing can be accomplished here by using the network plugins. So over here we have two different nodes having their own virtual Ethernet pairs, network interfaces, and Linux bridge. Now we want two pods to communicate which are present on two different nodes. So suppose we want the packet to be transferred from pod 1 to pod 4. How is that possible? So let me show you how that's possible. So the packet leaves from the pod 1 network and enters the root network of node 1 at virtual Ethernet 0. Then it is passed on to the Linux bridge, which makes the ARP request to find the destination. After the Linux bridge finds out the destination, then the packet leaves the Linux bridge to the main network interface at Ethernet 0, since it finds out that nobody on this network have the destination IP address. So it leaves the machine node 1 and it enters the routing table to find out its destination. So the routing table has a route setup for each of the node CIDR blocks, and it routes the packet to the node whose CIDR block contains the port 4 IP. So now the packet comes to know that its destination is on node 2. So with this, the packet arrives at the node 2 at the main network interface at Ethernet 0. Now, even though the port 4 is in the IP of Ethernet 0, the packet is still forwarded to the Linux bridge since the nodes are configured with the IP forwarding enabled. So the node's routing table is looked upon for any routes matching to the port 4 IP, and then the Linux bridge finds out that the destination for this node is at CIDR block. So the bridge takes the packet and makes the ARP request, and then it finally finds out that the IP belongs to virtual Ethernet 1. So virtual Ethernet 1 takes the packet, and finally the packet crosses the pipe pair and reaches the pod 4 network. So that's how guys two pods on two different nodes communicate. They are just helped with the routing table, which helps them to find out the destination IP which is present on any different node, right? So that was all about container to container communication and pod to pod communication. Now let's move on and talk about the second topic, that is services. Now how do you think these services help in the communication of pods? So when clients connect to the proxy and the proxy is responsible for maintaining a list of healthy servers to forward its requests, there are few requirements to the proxy. It must be self-durable and resistant to failure. It must have a list of servers that it can forward to, and it must also have some way of knowing if a particular server is healthy and able to respond to requests. So the Kubernetes designers solved this problem in an elegant way by building all the basic capabilities of a platform to deliver all of these three requirements, and then they developed a resource type known as service. So we can define service as a type of Kubernetes resource that causes a proxy to be configured to forward requests to the set of pods. The set of pods that will receive a traffic is determined by the selectors which match the labels assigned to the pods when they were created. Once the service is created, we can see that it has the assigned IP address and will accept the request on the port. Now, there are four types of services that you have to understand so that you understand the option for exposing a service onto the external IP address. The cluster IP, the node port, the load balancer, and the external name. Now, the cluster IP is the default service type, and by choosing this type of service, we expose the service on a cluster internal IP. So basically, with this type of service, the service is only reachable within the cluster. After cluster IP, we have the node port. So this type of services exposes the node's IP at a static port that is nothing but the node port. A cluster IP service to which the node port service will route is automatically created, and you'll be able to contact the node port services even from outside the clusters. After the node port, we have load balancers. So the load balancer exposes the service externally by using a cloud provider's load balancer. Node port and cluster IP services to which the external load balancer will route are automatically created. And finally, we have the external name. So basically, this service will map the service to the contents of the external name field by returning a CNAME record with its value. There's no proxying of any kind in the setup, and it requires a 1.7 or a higher version of kubedns. So guys, these were the four types of services that you need to understand. So now that you've understood the pod-to-pod communication, the container-to-container communication, and the services-to-pod communication, let's deep dive into the external-to-service communication. And this comes with none other than the ingress network. So ingress network is a collection of rules that allow inbound connections which can be configured to give services externally through reachable URLs, load balanced traffic, or by offering name-based virtual hostings. So ingress is the most powerful way of exposing services. The services and pods have IPs only routable within the clusters. It acts like an entry point to the Kubernetes cluster. Ingress is also an API object that manages the external access to the services in a cluster with the HTTP request. And then, finally, it also sits in front of the multiple services and acts as a smart router, right? So now that I've told you about ingress networks, let me tell you how does it work. So let me explain you with an example. So we have two nodes having the pod and the root network namespaces with a Linux bridge. In addition to this, we also have the virtual Ethernet device called the Flannel 0, which is a network plugin. Now what the network plugin does is that it basically helps to route the packet to the desired destination. So over here, we want to route the packet from pod 1 to pod 4, which are on two different nodes. So the packet leaves pod 1 network at Ethernet 0 and enters the root network at the virtual Ethernet 0. Then it is passed on to the Linux bridge, which makes the ARP request to find the destination. And then when it sends the ARP request, it finds out that nobody on this pod has the destination IP address. So the Linux bridge sends the packet to the Flannel 0 as the node's routing table is configured with Flannel 0 for IP forwarding. Now, the Flannel daemon talks to the API server of Kubernetes to know all the pod IPs and their respective nodes to create mappings to the node IPs. The network plugin then wraps this packet in a UDP packet with extra headers changing the source and the destination IPs to their respective nodes, and then it sends the packet out via Ethernet 0. Now, since the routing table already knows how to route the traffic between the nodes, it sends the packet to the destination node 2, and then the packet arrives at Ethernet 0 of node 2 and goes back to the Flannel 0 to decapsulate and emit it back into the root network namespace. So the packet is again forwarded to the Linux bridge by making an ARP request to find out the IP that belongs to the virtual Ethernet 1, and finally the packet crosses the root network and reaches the destination port 4. So guys, that's how external services are connected with the help of Ingress network. So as I was talking about network plugins, let me introduce you to the top network plugins available in the market. So we have the Google Compute Engine, OpenContrail, Cilium, Project Calio, Flannel, Amazon Web Services, Romana, Weaveworks, OpenWeaveSwitch, and many others. So these are just few. We have many more in the list that you can refer from the Kubernetes official documents, right? So guys, that was all about the theory part of Kubernetes networking. Let me show you a real life case study about Kubernetes networking and how a company benefited by using Kubernetes. So Wealth Wizards is an online financial planning platform that combines the financial planning and smart software technologies to deliver expert advices at an affordable cost. Now, it was extremely important for the company to quickly discover and eliminate code vulnerabilities with full visibility of their cloud environment, but they also wanted to control the traffic through access restrictions. So, they used Kubernetes infrastructure to manage the provisioning and rollout of clusters with the help of tools to manage the deployment and configuration of microservices across the kube clusters. They also used network policy features of Kubernetes to allow them to control traffic across restrictions. Now, the problem was these policies are application oriented and can only evolve with applications, but there was no component to enforce these policies. So, the only solution the company could find out for this was to use a network plugin, and hence they started using the network plugin ViewNet. So, the network plugin created a virtual network that has a network policy controller manager to manage and enforce the rules in Kubernetes. Not only this, but it also connected the Docker containers across multiple hosts and enabled their automatic discovery. So suppose you had a workload in the cluster and you wanted to stop any other workload in the cluster talking to it, you can achieve this by creating a network policy and that restricts the access and only allows ingress to it via the ingress controller on a specific port. Now, with this deployment on each Kubernetes node, the plugin manages the interpod routing and has access to manipulate the IP tables. In simple terms, you can just understand that each policy is converted to a collection of IP table routes coordinated and configured across each machine to translate the Kubernetes tags. So guys, that was how Wealth Wizards benefited by using Kubernetes network with the help of network plugin. Now, as I was talking so much about network plugins, let me show you practically how it is done. So we're going to deploy a multi-tier application over Kubernetes networks which are present on two different pods and have a container image. So suppose you want to store the product name and product ID. So you'll need a web application and a database. So those are the two applications that we're going to use, and each of these applications will have their own container images and pods. And then we're going to form a communication line between them with the help of services. So let's get started with the hands-on part. So the first step is to make a working directory for your project. So we'll make a working directory. So let me type in the command mkdir, and let's say I create a directory saying demo, and then I'll change my working directory to that directory. So I'll type in demo. So we are in a working directory. Now you have to create a deployment YAML file for both of your applications. So to create that, you just have to open a new file and then mention the specifications required. So let me create the file. Let's create a deployment file for the web application first. Let me open a file. Alright. So I've created my deployment file for the web application. So we have the API version, basically defining the API version for it. Then in the metadata, I've given my deployment name as web app 1 with the labels for web app SQL, tied to be front end because this is the front end application, and then we are mentioning the specifications for the containers and also for the port. So in the same way you have to create for the MySQL application. So let me again open a new file. Alright, so I've created my deployment file for the MySQL application. So again, the API version is defining our API version and the kind to be deployments because it's a deployment file. And then we are giving the name for this deployment file to be SQL database and the tier to be backend since it is a backend application. And then we'll also mention the specifications for the containers. So in the specifications of the containers, we are mentioning the port where we want it to run and also the image from where we are pulling it. So once all this is mentioned, you just have to close your application file and then you'll have to check for your deployment. So for that, you have to type in the command kubectl apply -f and the name of your deployments. So over here, I have my deployment files. So you can see that our first deployment has been created with the command kubectl apply-f and the name of the deployment file. So similarly, you have to do it for the MySQL application. So you just have to again type in the command kubectl apply-f and the name of file, right? So you can see that both the deployments have been created. Now, if you want to check if your deployments have been created or not, so you just have to type in the command kubectl get deployment. So you can see that both your deployments have been created with their respective names that we had given them. Now, what you have to do is you have to create services. So to create services, you again have to open a file and then mention the specifications required. So let's open a file. So let's say, suppose I open a file, web service. So we have mentioned the API version to be v1, which we had mentioned in the deployment file. The kind to be service because it's a service that we are creating, the name of the service, and then the app name, and the type to be front end because we're creating the service for the front end applications, and the port. So the type of service that we're choosing is the node port. So I'll save this file and then I'll close this. Similarly, I'll do it for the MySQL service. Let me create a new file, MySQL service, and mention the specifications. Alright, so again, we have mentioned the API version to be v1, the type to be service, because with service that we're creating, the name, the type to be backend, because it's a backend application that we're dealing with, the port, and the type of service is cluster IP. So once it is done, I'll save this file and then I'll close this. Once your services are created, you have to again deploy your services. So for that, you'll use in the command kubectl apply-f and the name of the services, right? So I'll type in the name of the service. And you can see that the web service has been created. Similarly, we'll create for the MySQL service. So I'll again mention the command kubectl apply-f and the name of that file. So that's MySQL service. Now, once both of your services are created, just to check if your services are done or not, you just type in the command kubectl get services. So you can see that apart from your Kubernetes cluster service, you also have the web app service and the SQL services. So now you have to check the configuration of pods after you're done creating with the services. So for that, you'll type in the command kubectl get pods. So you can see that the web application and the SQL are running on two different pods and have their own container images. So now to create a communication line between the web app application and the database, you have to go inside each container image and you have to configure some stuff. So let's first go inside the web app container. So for that, I'll type in the command kubectl exec-it, the container ID of the web app application, and in the command with a bash. So once you're inside this container, what you have to do is you have to open the index.php file, which is basically the configuration file for your web app application. So for that, I'll type in the command nano and then I'll mention the directory. So once your configuration file has been opened up, you have to change the server name, password, and the database details that you want. So let's mention the server name to be web app SQL1 that we mentioned for the MySQL container. The password to be Edureka since it's my user ID password. The database name to be, let's say, product details. So once you're done mentioning all the details, you just have to save this file. Once you're done saving this file, come out of this container. So for that, type in the command exit and you'll be out of this container. So now once you're out of the web app container, you'll come inside the MySQL container. So for that, you'll type in the command kubectl exec-it, the container ID, and bash. Then you'll have to get the access to the MySQL container. So type in the command mysql-u root-p and your password. So now once you've got the access to the MySQL container, you have to create the database and the table that you mentioned in the web app containers configurations. So for that, you'll type in the command create database product details. And then you'll use the database. For that, you'll type in use product details. Then you'll create a table that you mentioned. So you'll type in the command create table products, product name, and varchar, let's say 10 characters, product ID, and let's say 15 characters. Once it is done, you can see that a table has been created. Now just exit this MySQL container and come out of it. Alright, so now once you're done with this, you'll check the port on which the services are working. So for that, you'll type in the command kubectl get services. Alright, so you have to open your web browser and then open the web application. So you can see that our web application has been opened up. Now let's input some values. So let's say I input headphones with some ID and then I'll submit query. So you can see that a new record has been created successfully. So let me type in some input so that I can show you in the database whether they are stored or not. So I've entered few products. So now let me go back to my MySQL container and let me use the database. Once the database is used, let me show you the tables inside it. So we just have one table, that is products. So we'll select all the tuples from products. So for that, I'll type in the command select staff from products. All right. So as you can see that we have got the output of all the products that we have given as input. So there was one product that I did not give an ID and rest all stored with the product name and the product ID.
What is YML? YML's official definition is a human-friendly data serialization standard for all programming languages. YML's main advantage over other similar formats like JSON or XML is its human readability. That is, it was specifically designed to be easily readable and editable by humans. This makes it very ideal for dual human-machine use cases, such as log files, configuration files, inter-process messages, and in this case, also for Kubernetes config and definition files. Now let us discuss some of the most common use cases as to why YML files were really created. Firstly, YML files are used as configuration files, log files, inter-process messaging, cross-language data sharing, object persistence, and even to work on complex data structures. These are the very few common use cases as to where YML files can be used. Now that we know why YML was really created and some of its common use cases, let's move ahead and talk about why should you use YML. Firstly, YML files are extremely readable by humans. They're very expressive and extensible. Even a small child going to school, if you show him or her a YML file, they could identify few things and how the structure is completely laid out. It's really that easy. And the second reason as to why you should use YML files are because they're very easy to implement and use. The third benefit is that they're easily portable between programming languages. So if you want to switch from one language to another, if you want to create these YML files in Java, for instance, you can easily port this YML file to Python. Okay, so it's very portable, and that's the biggest advantage of YML files. The next advantage is they match the native data structures of agile languages. So that's another advantage. That is why porting between programming languages is also possible because it matches the native data structures. The fifth important benefit is that you can perform maintenance. You can really, maintainability among these files are extremely easy. The last advantage is that they are flexible. Now let's move ahead and talk about the structure of a YML file. There are three building blocks of a YML file. The first one is a key value pair. The second one is arrays and lists. And the third one is dictionary or map. The basic type of entry in a YML file is of a key value pair. After the key and colon, there is a space and then the value. List, on the other hand, would have a number of items listed under the name of the list. The elements of the list would basically start with a dash. They can be a number of lists. However, the indentation of various elements of the array matters a lot. Dictionary or map, on the other hand, is a much more complex type of YML file, which is a much more complex type of YML file that would be a dictionary and a map. Now, let me explain this with an example. Key value pair could be fruit colon apple, vegetable colon radish, liquid colon water, meat colon goat. Arrays would be a group of similar items, like fruits would be orange, banana, mango, vegetables would be potato, tomato, carrot. Dictionary or map would be how these items within an array or list are classified. So, banana can have three features that are calories of 200, fat of zero point 0.5 grams, carbs of 30 grams. Grapes, on the other hand, could have calories of 100, fat of zero point 0.4 grams, and carbs of 20 grams. So once the structure of a YML file is clear, let's move ahead and talk about some of the basics of YML. So as you can see, it is difficult to escape YML if you're really doing anything related to many software fields, particularly Kubernetes, SDN, and OpenStack. YML stands for yet another markup language, which is a human readable text based format for specifying configuration type information. So usually when you're learning anything about Kubernetes or anything related to deployment, you would first learn how to create a pod and then a deployment, right? So when you're defining a Kubernetes manifest, YML gives you a number of advantages that includes convenience and flexibility. Firstly, you will no longer have to add all your parameters to the command line. When defining a Kubernetes manifest, YML gives you a number of advantages, including convenience, maintenance, and flexibility. So in terms of convenience, you'll no longer have to add all your parameters to the command line. And when you talk about maintenance, YML files can be added to source control, such as a GitHub repository, so you can track your changes. In terms of flexibility, you'll be able to create much more complex structures using YML than you can on the command line. YML is basically a superset of JSON, which means that any valid JSON file is also a valid YML file. So, on one hand, if you know JSON and you are only ever going to write your own YML, you're all set. On the other hand, that's not very unlikely, unfortunately. Even if you're only trying to find examples on the web, they are most likely non JSON, that is YML, so we might as well get used to it. Still, there are many situations where the JSON format is much more convenient, so it is good to know that it is available to you. Fortunately, YML is relatively easier to learn, and there are only two types of structures you need to know about it. The first one is list, the second one is map. That's it. You might have maps of lists and lists of maps and so on. But if you've got those two structures down, you're literally all set. That's not to say that they aren't more complex things to do, but in general, this is all you need to get started. So let's move ahead and talk about YML maps. Let's start looking at these. Maps really let you associate name value pairs that we've already discussed, which of course is convenient when you're trying to set up configuration information. For example, you might have config file that starts like API version v1 kind as pod. The first line is basically a separator and is optional unless you're trying to define multiple structures in a single file. From there, as you can see, we have two values, v1 and pod, mapped to two keys, API version and kind. This kind of thing is pretty simple, of course, and you can think of it as in terms of JSON equivalent API version as to 1 and kind as pod. So in the YML version, the quotation marks are optional. So in the YML version, you don't really have to add the quotation, it's optional. The processor can tell that you're looking at a string based on the formatting. You can also specify more complicated structures by really creating a key that maps to another map rather than a string. In this case, we have a key, metadata, that has as its value a map with two more keys, names, and labels. Okay, the labels key you can see itself as a map as its value. You can nest these as far as you'd like to. The YML processor knows how all of these pieces relate to each other because we have intended the lines. In this example, we've used two spaces for readability, but the number of spaces doesn't really matter as long as it's at least one and as long as you're consistent. For example, names and labels are at the same indentation level, so the processor knows they are both part of the same map. It knows that an application is a value for labels because it's indented further. One thing you'll have to know is never use tabs in a YML file. So you could imagine the JSON file of this, right? So I hope maps are clear. So now that we've understood about maps, let's talk about YML lists. YML lists are literally a sequence of objects. You can see this example. We have argument sleep, 1000, message, bring back Firefly. You can have virtually any number of items in a list, which is defined as items that start with a dash indented from the parent. And of course, members of the list can also be maps. So in the JSON file, this would be arguments sleep with quotation, 1000 with quotation, message with quotation, bring back Firefly with quotation. And of course, members of this list can also be maps. So you can have list of container objects, each of which really consists of a name, an image, and a list of ports. Each list item under ports is itself a map that lists the container port and its value. So now that we know maps and lists quite in detail, let's move ahead and talk about YAML usage in Kubernetes. So having seen the advantage and basic building blocks of a YAML file, let us understand how YAML is used in Kubernetes. The Kubernetes resources are created in a declarative way, thus making use of YAML files. Kubernetes resources such as pods, services, and deployments are really created by using the YAML files. The example here contains both basic and advanced specifications. Firstly, let us talk about the various fields that are available. The first one is replicas. This tells Kubernetes how many pods to create during a deployment. Modifying this field is a very easy way to scale a containerized application. The second one is in spec strategy type. So suppose there is another version of the application that needs to be deployed, and during the deployment phase, you need to update without facilitating an outage. The rolling update strategy allows Kubernetes to update a service without facilitating an outage by proceeding to update pods one at a time. Again, under spec, under strategy, you can see max unavailable. This is the maximum number of pods that can be unavailable during the rolling update. Also, the max surge option gives you the maximum number of pods that can be scheduled above the desired number of pods. Now, again, in specification, you can see minute ready seconds is an optional integer that really describes the minimum number of seconds for which a new pod should be ready without any of its containers crashing for it to be considered available. Revision history limit is an optional integer attribute that you can use to tell Kubernetes explicitly how many old replica sets to retain at any given time. Under metadata labels, you can add labels to a deployment specification, whereas the selector under spec is an optional object that tells the Kubernetes deployment controller to only target pods that match the specified labels. Thus, to only target pods with the labels of application and deployer, you can make the following modification to our deployment YAML. You can see from the explanation of the various fields that YAML files can really help you maintain and control Kubernetes resources in a very declarative way. YAML is on its way to be considered as a de facto standard for configuration files. So in the next part of the session, let us learn how to create a pod using YAML. Okay, so now what we're going to do is we're going to be creating a Kubernetes pod using the YAML file. There are some prerequisites. You will have to have kubectl and minikube installed on your VM. Okay, so currently I'm working on my Linux virtual machine and I already have my kubectl and minikube installed successfully. To check if kubectl has been successfully installed, I'm just going to execute the command kubectl version space dash dash client. This will just give me an idea if the kubectl client version has been installed successfully, and you can see that there is the version info, the git version, git commit, go version, etc. So we know that kubectl is installed in my VM. Now, if you want to start the default minikube cluster, all you have to do is execute the minikube start command. For this, I'm just going to type minikube start. This command will automatically start the minikube cluster for me in less than a minute. Now that we've successfully configured our minikube cluster, so what we can do is we can just clear the screen And let's move ahead and create our YML file. So the first thing that we're going to do is we're going to learn how to create a Kubernetes pod using the YML file. Now, to create a Kubernetes pod with this file, you first need to create an empty file and assign it the necessary access permission, and then you define the necessary key value pairs, that is lists. The important lists are the API version, the kind, that is basically the pod, its name, and the containers that are present within the pod. So now what we're going to do is we're going to create a file that is named pod1.yml. Okay. So now what we're going to do is we're going to code the YML to create a pod that has been named new pod. So first I'm going to specify the version. The API version is v1 and the kind will be pod. The metadata, will specify the metadata. Its name will be new pod. Labels, the labels will be app and environment, and this will be test. Once that is done, we're going to execute the specification. Here we have containers, and here the name will be test container and image will be nginx. I'm just going to specify a dash. I'm just going to save this file, and once I've saved, I'm just going to use the kubectl apply command pod.yml. So you can see that there's a new pod that has been created, and once that is successfully executed, you're going to get new pod has been created. So now to see the state of the pod, if it is up and running, we're just going to execute the kubectl get pods command, and you can see that there are many pods that have been created in the past. So you can see that the new pod has been created 27 seconds ago and its status is container creating. Okay. After some time, if you execute the same command, you can see that the new pod is in the running state. So basically, this file is really important. Taking it apart one piece at a time, we can start with the API version. Here it's just v1. When we need to get to deployments, we will have to specify different version because deployments do not really exist in v1. Next, we are specifying that we want to create a pod to hold our application or cloud service. We might specify instead a deployment, job, service, and so on, depending on what you're trying to achieve. Moving on, we specify the metadata. Here we're specifying the name of the pod as well as the label we'll use to identify the pod in Kubernetes. Okay, then we will finally configure the actual objects that really make up the pod. Okay, the spec property includes any containers, memory requirements, storage volumes, network, or other details that Kubernetes needs to know about, as well as properties such as whether to restart the container if it fails, etc. All of that specifications can be mentioned here. So we have a fairly minimal definition here, that is a name, that is the front end, and the image on which it's based on, that is nginx. And if you want to mention one port on which the container will listen internally, you can also mention that. You can also move ahead and specify more complex properties such as a command to run when the container starts, arguments it should use, a working directory, or whether to pull a new copy of the image every time it's instantiated. You can also specify when deeper information such as the container's exit log, all of that can be specified here. So now that we have finished the first part and created our first pod using the YML file, let's move ahead to the next part of the session. Okay, so now what we're going to do is we're going to be creating a deployment using the YML file. So let's quickly switch back to our terminal and get started. So now what we're going to do is we are going to run an application by creating a Kubernetes deployment object, and you can describe a deployment in a YML file. For example, a YML file can describe a deployment that runs the nginx 1.14.2 Docker image, right? So that's what we're going to do. We're going to create a deployment. So I'm just going to clear my screen. So what I'm going to do is I'm going to name this as deployment.yml. Okay. And once I create this, I'm going to just add all of its fields, right? So firstly, I'm going to add the API version, that is apps/v1. Then the kind will obviously be a deployment. Then I will specify the metadata field. Here I'm going to specify its name as Nginx deployment. Once that is done, I'm just going to mention the spec. So here I have the field selectors and then match labels under it. And the app here is going to be Nginx, right? Okay. After this, I will set the replicas to 2. So what this really does is it tells deployment to run 2 pods matching the template. And now I'm going to specify the template field. Under this, I'm going to specify the metadata field, followed by labels. And here we're going to specify the app again, that's Nginx. I'm going to give specifications to the containers. And here the name Nginx. Image is going to be Nginx 1.14.2, and the ports, and then under the ports field we're just going to specify the container port, which is 80. Once we've completed writing the code in the YML file, what we're going to do is we are quickly going to save this file, and we are going to create a deployment based on the YML file, right? So for this, I'm simply going to use the kubectl apply command. With the help of the F flag, I'm just going to create this deployment, right? So let's do it. You can see that the deployment has been successfully created. You can also, really describe this information, right? You can display the information about the deployment by using the kubectl describe command. So I'm just going to describe the deployment, Nginx deployment. And you can see that the output is available. You can see its name, that is the Nginx deployment. You can see the namespace, it's been created in the default namespace. The labels, if there are any annotations, the selector, the replicas, there are 2 right now, and the strategy type is rolling update. All of the detailed information about this deployment has been given or described after this command has been executed. So once that is done, what we can do is we can also scale the application by increasing the replica count. For this, you can also create a scale YML file and then apply the new YML file, then verify that it has pods. So if you want to check out the number of pods that are currently present in the deployment, what you can do is you can use the kubectl get pods command. Okay. And you can specify the L flag, assign app to Nginx. So you can see that I've created 2 pods, right? That is 2 minutes ago, 2 minutes 30 seconds ago, and the status is running. That's great. So this is up and running, we know that. So now what you can do is we will clear the screen and we will check our pods IPs. Okay. So now what we're going to do is we're going to use the kubectl expose command, and we are going to be exposing the deployment that we've just created. And the deployment name is Nginx deployment. So that's what I'm going to mention. And you can see that the Nginx deployment, that is the service that we've created, has been exposed successfully. Now, what I'm going to do is I'm going to open the service file, the service.yml file, using the vim command. So I'm just going to write the code. So firstly, we're going to specify the API version, that is v1. Then I'm just going to mention the kind, that is service. So this is a service file, so that's the kind. And in the metadata field, so I'm just going to mention the various tags that's associated. First, we will write the name. The name will be Nginx deployment. Then we have the labels, and under this, we have to specify the run tag. Here, we're going to specify Nginx. Then in the specifications field, we are going to mention the ports. And under this, you can see that the port we're going to specify is 8080, followed by the protocol, which is going to be TCP. And in the selector field, we're going to specify the run tag, and this also will be Nginx. I'm going to save the service file. So once it's done and saved successfully, so using the kubectl get command, so we're just going to see the list of supported fields in the service definition, and my name is Nginx deployment, so that's what I'm going to really work on. So you can see that you have the type, that is cluster IP, the IP address is given, the port is 80 TCP, the age is 9 minutes 28 seconds. So you must be aware that a service is backed by a group of pods, and these pods are exposed through endpoints. The services selector will be evaluated continuously, and the results will be posted to an endpoint object, which is also named as Nginx. When a pod dies, it is automatically removed from the endpoints, and new pods matching the services selector will automatically get added to the endpoints. And if you want to check the endpoints and note that the IPs are the same as the pods created in the first step, we can just use the describe svc command and check it out. And you can see that the name is Nginx here, namespace is default, the app is equal to Nginx. You have the selector, all of the information is given here. And the endpoints is 172.17 and so on. Now we're just going to execute the get command. You can see that both of these endpoints are the absolutely same, right? The Nginx and the service that we've created. Now we should be able to call the Nginx service on the cluster IP port from any node in your cluster. So now I'm just going to clear my screen. So this is all you have to know to get started with the Kubernetes YAML tutorial. Okay, so now what we're going to do is we are going to be deploying a service in an application. So for this, firstly, what we have to do is we'll have to create a YAML file, and I'm just going to create a deploy.yml file. And as you can see, the file opens. So here I'm just going to type out the entire code. So you can run an application by creating a Kubernetes deployment object, and you can describe a deployment in a YAML file. So now let me explain this code, okay? We start with the API version. Here it is apps/v1. So next we are specifying that we want to create a deployment to hold your application or service. We might specify instead a job, pod, service, and so on that we already know, depending on what we're trying to achieve. Next, we specify the metadata. Here we'll be specifying the name of the pod as well as the label we'll use to identify the pod to Kubernetes. And then we will configure the actual objects that make up the pod. The spec property includes any containers, memories, replicas, all of that. So here we have a simple, fairly minimal definition and name for the spec container. In the spec property, we have containers, that is a name and an image and different ports. You can also specify more complex properties such as a command to run when the container starts, arguments it should use, a working directory, all of that. Okay, and then moving on to the next part, we add 3 dashes, and then in the next part, we'll mention the service. So you can see that the API version is v1, the kind is service. We're creating a metadata where the name of the metadata is Nginx. And using the spec property, we're going to specify the type, which is node port, a selector where the app is named node port, and ports by default and for convenience, the target port is set to the same value as the port field. So the port is set to 80, the target port is also set to 80. And we also have an optional field. For convenience, the Kubernetes control plane will allocate a port from a default range. So the node port here is specified as 3007. We're quickly going to save the file. Now that we've talked about the YAML file in detail, let's go ahead and save this. Now, once the file has been saved, let's use the kubectl apply command. You can see that the deployment and the service has been created. And what we're going to do is we're going to use the kubectl gets a, and you can see that Nginx on port with cluster IP 10.99.84.28 has been successfully created, and it's been deployed on port 30007. So what I'm going to do now is I'm going to open a web browser. I'm just going to add the external IP on which my instance is running on 30007, and you can see that the application has been successfully created. You can see that there's welcome Nginx and there's some more details that has been given. So just by creating one YML file, we can add the application and the service and deploy it all together. So this is how easy it is to work with Kubernetes using YML files.
Now, the Kubernetes proxy here is responsible to distribute the traffic based on the network rules across the nodes. Okay, kube proxy will be used. So this is the architecture of Kubernetes, friends. If you understand this, working with Kubernetes is very easy. Okay, now let me directly jump on to the practical, friends. So you have understood the architecture of Kubernetes. So here, friends, I have started two machines, two Ubuntu machines, friends. Okay, two Ubuntu machines I have started. On these machines, if you see, I've already created a Kubernetes cluster. Okay, in this cluster, I will execute the commands using kubectl. That is a process that basically that's a client process that sends your request to the APIs. Kubectl get nodes means it will get the number of nodes that are part of your cluster, Kubernetes cluster. I have two nodes, friends: kube master, kube slave. Okay, one is the master machine where I'm executing the orchestration activities. Another one is the slave, friends. Nothing is there on this slave. Only Docker is available. Okay. Now, friends, first thing, how do you create a pod? How do you create a container? In Kubernetes, we create a container. Okay, container C1, let's say, of nginx type. This image you are going to get it from Docker. This is Docker image. But friends, in Kubernetes, we have another layer over your container, and it is called as a pod, friends. Pod is a layer of abstraction over your container. In Kubernetes, you will never create a container. You will create a pod. A pod in turn will create a container for you. Remember it. So in Kubernetes, we say creating pods. That means creating a container. I want 10 pods. That means 10 replicas of container. Okay, a layer of abstraction. All right. Maybe why a pod then? Why a pod? Because container runtime interface can change in Kubernetes, right? Kubernetes command should be same. In Kubernetes, you will give only the single command kubectl create pod. Let's say tomcat pod. This is not the correct command. This is just an English algorithm. Create a pod of tomcat. It will remain the same. This command will remain the same. Based on the container runtime interface that you have on the master machine, that container will get created. Isn't it, friend? Okay, so Kubernetes command is same. Kubernetes will create a pod. It's the task of the pod to check which container tool does it have in the cluster. Create that container. So user does not have to bother which type of container to create, right? User will just create a pod. Now, how do we create a pod? Let us see here. Kubectl, first command for the day, friends. Kubectl pod, give a name to the pod. Okay, I will give the name as pod1. Kubectl run. Run is the command. Just like in Docker, you create run, you use the run command to create container, right? Same thing. Kubectl run pod1. Which image you want on the pod? I want the image, let's say nginx image. Now, here you are not mentioning anything, whether it is a Docker image, which image, we don't have to care about it. Kubernetes pod object will take care of it to create the container. Please observe, here one pod has been created. One pod has been created with the name as pod1. Nginx is just a web server. It's a web server. Okay. Now let me show you what actually happened when you created the pod. Let me show you what happened when you created the pod. So kubectl describe pod, which pod? Pod 1, name of the pod. See here, these are the events that occurred. First, you sent a request to the API server using the Kubernetes command. Which process took care of it? Scheduler decided where should the pod run on the slave, decided the slave. Then kubelet process on the slave pulled the image, took help of Docker to pull the image, successfully pulled the image, created the container in pod 1, started the container in the pod 1. Which container? You want to see those details? Let us see that also inside the pod. Same describe command only. I will give less. See here, pod 1 got created here on the node slave because scheduler decided it to be on the slave. Right now it just got created. Okay, it is in the running status. Pod 1 container name, image nginx, image ID. No port mapping done so far. Okay, got it? All right. So this is how you create a pod. Now you know how to create single pod in Kubernetes. If you want to create 10, 20 pods, and that too you want to create for your application, you want to deploy your application. For that, we have another object in Kubernetes called as deployment fridge. Let me talk about it. kubectl explain deployment. So friends, if you want to learn what a pod is, what deployment is, what replicas are, replica set is, just use this explain command of Kubernetes. Hey Kubernetes, explain me what is pod, what is the deployment. Please see here. Okay, deployment enables you to update your pods and replicas. It allows you to create pods and multiple replicas of the pod, friends, basically. Okay, deployment. And in order to create a deployment, you have to give 4 information, friends. That is code library that is needed in Kubernetes to create the deployed API version. What kind of object are you creating? Name of the deployment and the specifications. That is, in your deployment, which image do you want to create the container of? How many containers do you want to create? Should the containers be created at the same time? Should the containers be created one after the other? What is the utilization of those? The limitations, resource limitations of those containers. We will define under specifications section. You must be thinking, where should we give all these details, Sona? Deployment, okay, we are talking about deploying an image, okay, on multiple containers in the cluster. But how do I provide these details? Metadata details, specification details, where do we provide? Friends, in Kubernetes, we write something called as manifest file or object definition files. We write it in YAML format. Okay, Kubernetes object definition files, friends, they are written in YAML. Let me show you one such file. Vim deployment.yaml. Okay, I'll write down one. It consists of 4 sections, friends. Any YAML file. Even to create a pod, you will have to write a YAML file. Okay, so the first thing is API version you will do. That is, in programming language, we have packages, right? To work with existing methods, we pull the package, we import the packages. Similarly, in Kubernetes also, you have to import a code library for the object that you are creating. We are creating a deployment object. So here API version is apps/v1. Okay, apps is a code library that will help Kubernetes to create an object of kind deployment. Deployment consists of following things, friends, if you are confused. Okay, that I directly jumped from pod to deployment. Not to worry. Pod is what? One single container. In a pod, you will have one container only, friends. If you want to create multiple pods, friends, multiple pods of the same image, C1, C1, C1. Okay, and also, friends, you want to manage these replicas. They are called as replicas. I hope you remember it. Multiple containers of the same image, replicas. You will create a deployment, friends, deployment. And another advantage of deployment, it's also called as replica set. Creating multiple replicas of a container is called as a replica set object. replica set. Deployment is just like replica set. The only difference is you can also update an image, update the image version. Right? You can deploy new images with the help of deployment object. Okay, that's the advantage of creating a Kubernetes object called deployment. Please observe deployment. Kind of object that I'm creating is deploy. After this, you will give metadata. Metadata. In metadata, you will give the name of your deployment. I will say my deployment. I'll give my nginx. I'll do an nginx image deployment. Okay, I'll give my nginx. Now after this, you will give specification section. Specification as in pods to be created. Which pods have to be created? Using which image the pods have to be created? Which application do you want to deploy? Which applications do you want to deploy is the question. So you will provide a template here. You will provide a template over here under the spec section. First, you will tell Kubernetes, hey Kubernetes, I need 3 replicas or 10 replicas. So replicas is what you will give me. Replicas, I'll say 3 replicas I want to create. Kubernetes will ask, replicas of what? Replicas of what? So here you give the template that, hey Kubernetes, create pods, friends. Template, you give the pod template. Metadata, again, metadata of details about the pods. That is, what will be the name of your pod? Name of your pod. So I will say my pod. Okay. And after this label, we will also give a tag to the pod. Okay. Labels. Here you will give the labels as type is equal to web server. That means all the pods, we are going to create 3 pods. All the 3 pods are going to have a label called as web server. Right now, just assume that label is nothing but a common tag to all the pods created as part of this deployment. For example, you all are students of my webinar. For all of you, the common tag is Sonal Mittal being the instructor for this webinar. Similarly, as part of this deployment, 3 pods will get created. The tag is web server. Okay. Next, after this, under labels, at the metadata level, you will provide specifications of the container. Right inside the pod, what is there? Another specification, that is container. Containers. Which containers do you want to create? I want to create an image. I want to create one container with an image called as nginx. And this time I will take the version as 1.7.9. This is the version, specific version of image that I am choosing. Okay. For this deployment, 3 pods should be created. In the pods, there should be a container with the image nginx 1.7.9. And name of my container is going to be C1, friends. Okay, anything you can give. Okay, friends. Make sure specification is at the same level of metadata. Name of the pod, labels. Okay, done, friends. Now, friends, here I will give one condition also. Why to just create it? Why to just do an easy job? Let us make it a little complex. I will give a condition here under replicas. What we will tell to Kubernetes, hey Kubernetes, do a search in the cluster. Do a search in the cluster. If in your cluster right now you have any pods, yes, there is a pod. One pod is available right now. On that pod, if the label is web server, is the label as web server? No, right? My pod does not have any label. If there is a pod, in your cluster with the label as same as web server, consider it part of my replica. Consider it as part of my replica. So already there is a pod with web server, let's say. So number of replicas to be created 3. Already 1 is there in the cluster. So with this deployment, I have to create just 2 more replicas. I just have to create 2 more replicas because 1 pod is already available. 1 replica is already available with the same label. So I'm adding a condition here. Selector. In selector, you will give a condition here, match labels. That is, Match the label. Which label? Type. I have given a label, right? Label for the pod. Type is the label. Web server. Go and check. Hey, so before creating the pods, we are asking Kubernetes to go and check in the cluster if there are pods with the same label as that of web server. If there is a one, then just create 3 minus 1, 2 pods. If there are no pods, with the same tag not available, with the same label, it's not available, then here is the template. Here is the template. Create the pods, 3 pods you create this time. Just a condition, just if condition. If there are pods with the label type is equal to web server, select them and rest you create. Okay, all right. You can read about it. Selectors and labels. Now this is my deployment here done, friends. What does this deployment do? It's a high-level object, friends, in Kubernetes. As you will see, when I will execute this deployment file now, friends, deployment. What will this deployment do? This deployment will first create a replica set. Replica set is an object in Kubernetes. That is number of multiple replicas it will create. That is 3 will be the 3. Replica set will maintain 3 replicas. In addition to this, it will create pods. 3 pods. 3 pods will get created of the same image. Of this image, 3 pods will be created. So deployment is a high-level object which in turn creates 2 other objects in Kubernetes. Replica set and pod. So let me execute this and I'll also show you a shortcut for it. Okay. Now how do you create this? How do you create this deployment? You will use a command kubectl create -f deployment.yml. Okay, take that. Deployment has been created. Now observe the objects which got created. kubectl get all. So from where are we getting this all the details? From the etcd database that we have on the Kubernetes. See here, 3 new pods got created. Containers are being created. Okay, and 1 deployment got created. 1 replica set also got created. If you want to create multiple replicas of an image, you will use replica set. Pod is what your container will be there. Deployment is same as replica set, just created containers. So what is the advantage of using deployment? I have not given Rahman for providing pod details for accessing your service, containers from the external world. We have another object in Kubernetes called a service, using which we can give pod details. Okay, all right. Let me just rerun this command to see if the containers are up and running. Pods are up and running. See, all the 3 pods are up and running. Now, friends, let me do a rolling update. Basically, deployment is for what? You have deployed a version of an image. So, kubectl describe deployment. What is my deployment name? My nginx. See here, I should have given less. So if you see here, this is the image which got updated. This is the image which got updated, right? Now let us run a command. I'm going to now run a command kubectl set image of my deployment. Okay, deploy. What is the name of my deployment? My nginx. Okay, container name C1. Right now it had an image nginx 1.7.1. I want to update it to nginx 1.9.1. New version of the image I want to update, friends. I want to change the image on my deployment. A new code has come up, new version has come up, I want to update it. You will observe that the pods will get created. Okay, the pods will get updated with the image immediately. Okay, one after the other, friends, one after the other. So please observe here. So deployment has been updated. kubectl get all. See here, the previous running containers have been deleted. They will get deleted. One by one, new pod will get created. One after the other, a new pod will get created. Before that, see here, previous replica set, this one. 3 desired count. Okay. First, what Kubernetes does here, when we are talking about deployment, deploying a new image, Kubernetes will first create one container, one pod it will create with the new image version 2, let's say. Okay, once it is up and running, it will, from the previous deployment, it will reduce. Okay, it will become 2 after this. Okay, and it will reduce the one of the, again it will increase the new replica here with the version 2. Here in the previous replica set, older version will be deleted. Older version will be deleted. Again, desired count will increase for the new replica set. The previous replicas will be deleted. Rolling update one after the other. See, we have version 1, version 1, version 1. 3 replicas are available. I sent an image to update. Okay, I sent a request to update the image version 2. What Kubernetes will do? It will first create one new replica, as you see here. Created one new replica, version 2. It will bring this down once it is up and running. Once the status changes to running, one of the previous replica will be down. 3 replicas in the cluster. User requests are still managed. Now it will again create one more replica with version 2. This will be deleted once this is up and running. Again create one more replica with version 2, delete. This is how rolling update happens. Let us see now again. It must have updated all the replicas. Can you see here? Previous replica set deleted everything. Just few seconds ago, new replica set got created with 3 new replicas of the latest version. You can still check it. You can check it. You can check on the pods. Let us check the pod. kubectl describe pod. What is the name of pod? Let us take this name. See here, version has been changed. Image version has changed. This is deployment front. Kubernetes deployment object front. You can also execute the log. You can check the log of your containers, okay, on Kubernetes front. If a pod is evicted from a node, all the corresponding containers are also evicted, right, along with their logs.
So moving ahead, let us now understand what is Kubernetes controllers in general. Okay, but before we move ahead to controllers in Kubernetes, let's see what does this controllers actually mean in a common sense term. Okay, so this controllers, right? Controllers are basically an infinitely running loop that keeps on executing as long as we have that application running. Okay, and the responsibility of these controllers is to monitor everything that is happening in the system. So to give you a real-time example, let's take something like a room temperature controller. Okay, so we basically have this thermostat installed in majority of the rooms, right? So whatever the current state of the room is, whatever is your desired state of the room, that is monitored by a thermostat. And thermostat continuously monitors if the room temperature is dropping or increasing. And if the room temperature is changed, right? So it brings it according to whatever the difference amount is there. So coming back to Kubernetes, right? Well, controllers in Kubernetes are basically like this control loop that watches the entire state of your cluster and then make or do request changes needed to be done. Each controller tries to move the current state that is closer to the desired state over here. So let us now move ahead and discuss some of the popular controllers that is available to us in Kubernetes. First off, we have something called as replica set. You see, replica set's purpose is to maintain a stable state of a replica pod running at any given time. As such, it is often used to guarantee the availability of a specified number of identical pods. You see, replica set ensure that a specific number of pod replicas are running at any given time. However, a deployment of a container is a high-level concept that manages the replica sets and provides directive updates to pods along with a lot of other useful features. Therefore, we recommend using deployment rather than just using replica set at once. So what I'm trying to say here is that you may never need to manipulate replica set object. Instead, you can just use a deployment instance over here. Alright, so speaking about deployments, right? So deployment basically provides a declarative updates for pods and replica sets. You describe a desired state in a deployment and the deployment controller changes the actual state to the desired state at a controlled rate. You can define deployment to a creative new replica set or to remove the existing deployment and adopt all the resources with a new deployment. So moving ahead to the next type, that is stateful set. So stateful set is a workload API object used to manage stateful application. This manages the deployment, scaling of the pod, and provides guarantee that ordering the uniqueness of these pods. Like deployment, a stateful set manages the pod that are based on identical container specs. Unlike deployment, a stateful set maintains a sticky identity of each pod. These pods are created for the same spec, but are not interchangeable as they are referred to by unique identity. So moving ahead to the daemon set. You see, a daemon set ensures that all the nodes run a copy of a pod. As nodes are added to the cluster, pods are added to them. As nodes are removed from the cluster, then those pods are removed and sent to a garbage collector. Deleting a daemon set will clear out all the pods that it has created. Some of the typical use cases of daemon sets are running a cluster stored daemon set on every node. Okay, running a logs collection on a daemon on every node. In a simple case, right, a daemon set covers all the nodes and would be used for each type of daemon. A more complex setup might use multiple daemon sets for a single type of a daemon. But the different flags or different memory and a CPU request for different hardware types are used here. So let us now move ahead and see what are Kubernetes services, right? So what do you understand when someone says what exactly is a service, right? Well, a Kubernetes service is a logic abstraction for a deployment group of pods in a cluster. Since pods are ephemeral, a services enables a group of pods which provides a specific function, such as web services or image processing or whatever it is, to assign a name and a unique IP address. As long as the service is running that particular IP address, it will not change. Services are defined like with different policies that goes there. Majority of the time we get asked what is the difference between service and a deployment. Well, you see, in Kubernetes, a deployment is a method of launching a pod with a containerized application and ensuring that this necessary number of replica is always running on the cluster. On the other hand, a service is responsible for exposing an interface to those pods which enable network access from either within or from outside the cluster. Alright, so now that we know a brief about what exactly is services, let us now move ahead and see what are the different types of clusters that are available. Starting off with cluster IP service. So the cluster IP service is a default type of service which is used to expose service on IP address internet to the cluster. This access is permitted only from within the cluster. Moving on to the next one, we have headless service. Services that do not need load balancing and only expose a single IP can create headless service by specifying none as the cluster IP. Headless service can be defined as a selectors, in which cases endpoint records are created at the API that modify the DNS to return address that point to the pods that are exposing the service. Headless services without selectors don't create an endpoint records. The DNS ecosystem configures either the CNAME record or the record of the endpoint with the same name as the service. Moving on to the next type, that is node port service. You see, node port are opening ports at every cluster nodes. Kubernetes will route traffic that come into the node port to the service, even if the service is not running on that particular node. You see, node port is intended as a foundation of high-level method of ingress such as load balancing and are useful in deployment. Moving on to the next type, we have external name service. External name services are similar to other Kubernetes services. However, instead of being accessed by a cluster IP address, it returns a CNAME record with a value that defines in the external name. Alright, so moving on to the last type, we have load balancer service. For those clusters that are running on a public cloud providers like AWS or Azure, creating a load balancer service provides an equivalent to a cluster IP service extending to a load balancing service that is specific to that particular cloud provider. You see, Kubernetes over here will automatically create a load balancer and provide a firewall rules if needed, and then populate the service with an external IP address assigned by the cloud provider. So now that we know Kubernetes services, let us now understand how can you access these services, right? So how do you access these services? Well, you see, services simply point to the pods using labels. Since services are not node specific, a service can point to a pod regardless of if they run in a clustered environment or not. Here, by exposing the service IP address as well as the DNS service name, the application can be reached to either methods. So how do you access these Kubernetes services is a question over here, right? Well, you see here there are two basic ways. First off, we have DNS, which is actually the most common way, and the other one is env variable. Talking about DNS, right? The DNS method is recommended method for discovering the services. To use this method, a DNS server must first be installed to the cluster. The DNS server monitors the Kubernetes API And when new service is created, its name becomes available for easy routing and for requesting of an application. Next, as I mentioned earlier, we have env variable. This method relies on something called as kubelet adding environment variable for each active service for every node that is running at any given point. So to conclude over here, we can access Kubernetes services by two ways. One is by DNS and the other one is by env variable.
Firstly, we will understand why do we need ingress. So when you're creating pods in Kubernetes, you assign selector labels to them. You can see these labels in this snippet of a deployment manifest on the screen. So this deployment.yml file, what it does is it creates 3 replicas that run the Docker image my app and assigns the app that is equal to the FOO label to them. Rather than assigning the pods directly, it is typical to group them under a service, which makes them available at a single cluster IP address, although only from within the same cluster. The service also acts as a layer of abstraction that hides the ephemeral nature of the pods, which can be scaled up and down or replaced at any time. It performs rudimentary round-robin load balancing. So, for example, on the screen, you can see the following service definition, which collects all the pods that have a selector label app is equal to FOO and routes traffic evenly among them. However, the service is accessible from inside the cluster only by other pods that are usually running nearby. So, Kubernetes operator grappled with how to give clients outside the cluster access. The problem was pretty apparent early on, and 2 mechanisms were integrated directly into the service specification to deal with it. So when you're writing this service manifest, you can include a field that is named type, which takes a value of either node port or load balancer. So the example snippet that you can see on the screen sets the type to node port. So let's firstly talk about services with a node port. So this type are typically very easy. They essentially announce that they'd like the Kubernetes API to assign to them a random TCP port and expose it outside of the cluster. What makes this more convenient is that a client can target any node in the cluster using that particular port, and their messages will be relayed to the right place. For example, it's like saying you can call any phone in India and whoever picks up will make sure you get forwarded to the right person. The only downside is that the port's value must fall between the range 30,000 and 32,767, a range safely out of the way of well-known ports, but also conspicuously non-standard compared to the familiar ports 80 for HTTP and 443 for HTTPS. The randomness itself is also a hurdle, since it means that you do not know what the value will be beforehand, which makes configuring NAT, firewall rules, etc just a bit more challenging, especially when a different random port is set for every service. So the other type of option that is available to set type is to load balancer. However, this comes with some prerequisites. It only works if you're operating in a cloud hosted environment like Google's GKE or Amazon's EKS, and if you're okay with using that cloud vendor's load balancer technology, since it is chosen and configured automatically. The most costly disadvantage is that a hosted load balancer is spun up for every service with this type, along with a new public IP address, which has additional costs. So allocating a random port or external load balancer is easy to set in motion, but comes with various unique challenges. Defining many node port services creates a tangle of random ports. Defining many load balancer services leads to paying for more cloud resources than desired. It is definitely not possible to avoid completely, but perhaps it could be reduced, contained, so that you would only need to allocate one random port or one load balancer to expose many internal services. The platform needed a new layer of abstraction, one that could consolidate many services behind a single entry point. It was then that Kubernetes API introduced a new type of manifest called an ingress, which offered a fresh take on the routing problem. So it works like this. You write an ingress manifest that declares how you would like clients to be routed to a service. So the manifest here doesn't actually do anything on its own. You must deploy an ingress controller into your cluster to watch for these declarations and act upon them. Ingress controllers are just pods just like any other application, so they're a part of the cluster and can see other pods. They're built using reverse proxies that have been active in the market for many, many years now. So you have your choice of an HA proxy ingress controller, an NJX ingress controller, and much more. The underlying proxy gives it layer 7 routing and load balancing capabilities. Different proxies bring their own set of features to the table. For example, the HA proxy ingress controller doesn't really need to reload itself as often as the NGIX ingress controller because it allocates slots for servers and fills them in it at runtime using its runtime API. That can eventually lead to better performance. Being inside the cluster themselves, ingress controllers are susceptible to the same vault in jail as other Kubernetes pods. You need to expose them to the outside via a service with a type of either node port or a load balancer. However, now you have a single entry point that all traffic goes through, one service connected to one ingress controller, which in turn is connected to many internal pods. The controller, having the ability to inspect HTTP requests, directs a client to the correct pod based on characteristics it finds, such as the URL path or the domain name. So, in short, ingress is an API object that manages external access to the services in a cluster that is typically HTTP. Ingress may provide load balancing, SSL termination, and name-based virtual hosting. There are definitely some terms that you'll have to be familiarized with, such as node, which is basically a worker machine in Kubernetes, which is a part of the cluster. Also, the meaning of cluster, which is a set of nodes that run containerized applications that are managed by Kubernetes. And edge router, which is a router that enforces the firewall policy for your cluster. This could be a gateway managed by a cloud provider or a physical piece of hardware. And I'm sure you know what a service means. A service is simply a Kubernetes service that identifies a set of pods using label selectors that we've already discussed in the previous part of the session. Cluster network is simply a set of links, logical or physical, that facilitate communication within a cluster according to the Kubernetes networking model. So what ingress really does is it exposes HTTP and HTTPS routes from outside the cluster to services within the cluster. Traffic routing is controlled by rules defined on the ingress resource. So let's take a simple example where an ingress sends all of its traffics to one service. An ingress may be configured to give services externally reachable URLs, load balance traffic, terminate SSL or TLS, and offer name-based virtual hosting. An ingress controller is responsible for fulfilling the ingress, usually with a load balancer, though it may also configure your edge router or additional front ends to help handle the traffic. An ingress does not expose arbitrary ports or protocols. Exposing services other than HTTP and HTTPS to the internet typically uses a service of type service.type is equal to node port or service.type is equal to load balancer. So firstly, you must have an ingress controller to satisfy an ingress. Only creating an ingress resource has no effect whatsoever. You need to deploy an ingress controller such as ingress NGX, or you can choose from a number of ingress controllers. Ideally, all ingress controllers should fit the reference specification. In reality, the various ingress controllers operate slightly different. So firstly, we will look at how a minimal ingress resource looks like. So as with all the other Kubernetes resources, an ingress, as you can see, needs API version, kind, and metadata fields. The name of an ingress object must be a valid DNS subdomain name. Also, ingress frequently uses annotations to configure some options depending on the ingress controller, an example of which is the rewrite target annotation. Different ingress controllers support different annotations. The ingress spec that you can see, that is the specifications, has all the information needed to configure a load balancer or proxy server. Most importantly, it contains a list of rules matched against all the incoming requests. Ingress resource only supports rules for directing HTTP or HTTPS traffic. So let's move ahead and talk about ingress rules. Firstly, you'll need an optional host. Now, in this example, no host is specified. So the rule applies to all inbound HTTP traffic through the IP address specified. If a host is provided, for example, foo.bar.com, the rules apply to that particular host. Secondly, a list of paths, for example, front/test path, is required, each of which has an associated backend defined with a service.name and a service.port.name or service.port.number. Both the host and path must match the content of an incoming request before the load balancer directs traffic to the reference service. And finally, you'll need a backend, which is a combination of service and port names. HTTP and HTTP requests to the ingress that matches the host and path of the rule are sent to the listed backend. A default backend is often configured in an ingress controller to service any requests that do not match a path in the specification. With this, let's move ahead and set up ingress on the default Kubernetes cluster, that is Minikube. So now what we're going to do is we are going to set up ingress on Minikube. So before we move on, there are some prerequisites. Firstly, you will have to have Docker installed. You have to have an hypervisor installed. You will also have to have Minikube. You'll also have to have kubectl, that is the command line interface for Kubernetes, installed along with Minikube. Okay, so if you want to install all of these tools, firstly, you will have to install Docker. And for this, you can just go to the official website of Docker and you can check out the version that you want to install. Now, currently, I'm working in the Linux virtual machine, so I'll want to install Docker for that. So I'm going to go to the official website of Docker. I'm going to click on Get Started button, which is present on the right-hand side. And if I just scroll down, you can see several options. You can play with Docker. You can sign up for Docker Hub, which is basically a website or a cloud-based application registry for collaboration purposes. So now what I'm going to do is I'm just going to scroll down and I'm just going to click on Docker Desktop. There are various options you can download for Windows, you can view for Linux Engine, you can download for Map, and I'm just going to click on for Linux. And this will redirect me to a page where I can just install the Docker engine, right? I have to install the Docker engine for the Ubuntu community, and I can just do that. So I'm just going to click on this. So this will redirect me to a page where I can install Docker. So if I scroll down and click on this link, I can install Docker engine on Ubuntu. Okay, if you want to uninstall the older versions, you can simply execute this command. If I scroll down, you can see that there are various ways you can install Docker into your Linux machine. The most convenient way to install Docker would be by using the repository. So there are some steps that you can follow, and you can update the app package index and then install packages to allow the apt to use a repository over HTTPS. Then you can add the Docker's official GPG key using this command. And then finally, you can execute this command based on your architecture, your system's architecture. And then finally, you can move on and install the Docker engine. If you want to install a specific version, you can just mention that too. You can select any of the versions that you'd like to install and then execute the command accordingly. Okay, once that is done, you can just verify that Docker engine is installed correctly by running the hello world image. And I'm just going to copy that. And since I've already installed Docker in my virtual machine, I'm just going to execute this command and check if Docker is up and running. You can see a message that says hello from Docker, and you can see that this message shows that your installation appears to be working correctly. That's great. So we have Docker installed in our virtual machine. Okay, now what I'm going to do is I'm going to open a new tab and I am going to install Minikube. Okay, so I'm just going to look for Minikube and kubectl. If I scroll down, you can see that there is a web page that says install tools, and I'm just going to click on that. So it redirects me to a page where you can choose the tools, the Kubernetes tools that you can install in your local machine. There's kubectl and there is Kind and there's Minikube. We don't really need to work on Kind and kubeadm. So we're just going to be working on kubectl and Minikube. So that's what you will have to install first. So before you install Minikube, there are some prerequisites. Firstly, you'll need 2 CPUs or more. You'll need 2 GB of free memory, you need 20 GB of free disk space, internet connection, you'll need container or virtual machine manager such as Docker, that's the best thing. And also you will need Hyper-V or KVM or HyperKit, any of that, okay? And you'll also need a Hyper-V or KVM or VirtualBox or VMware, any of that installed successfully in your local machine. And once that is done, you can go ahead and install Minikube or you can install kubectl. So since I'm installing kubectl, which is simply a command line tool that will allow you to run commands against Kubernetes clusters, you can just click on the install Kubernetes option on Linux. And again, there are some prerequisites that you'll have to follow. And you can just scroll and you can see that there are 3 ways to install this into your local machine. The first one is you can install it by using the kubectl binary with curl on Linux. You can install using native package management, and you can also install using other package management. I would suggest or recommend you to install kubectl binary with curl on Linux. So there are a few steps. Firstly, you will have to download the latest version with the command. Then you have to validate the binary. And then finally, once the validation has been successfully done, you can install kubectl. Okay. And since I've already installed it in my VM, I'm just going to check the client version of kubectl. So you can see all the information of the client version, the Git version, the Go version, the platform that it is currently on, working on, the build date, all of that information is given here. That's great. So once you've successfully installed kubectl, we will go check out how to install Minikube. Okay, so first here you'll have to select your operating system. Okay, you have Linux, you have Mac OS, you have Windows, the architecture type, and there are 3 options. That is the binary download, the Debian package, and the RPM package. Again, I would suggest you to pick your choices according to what you're comfortable with, and then finally install Minikube on Linux. So as we all know, this is a cluster. Minikube is basically a cluster, right? So you can start your cluster by simply executing the Minikube start command, and then you can get on with the interaction. Okay, so what we're going to do is, since I've already again installed, I'm just going to execute the start command. Before that, I'll just clear my screen. So once I have cleared my screen, I'm just going to execute the Minikube start command. So as you can see that Minikube is up and running. It says kubectl is now configured to use Minikube cluster and default namespace by default. So that's great. We have a namespace that is created and that is named as default. We also have the Minikube cluster up and running. So I'm just going to clear my screen. And now what we're going to do is we are going to enable the NGX ingress controller. As I've already mentioned in the previous part of this session, we will have to enable the ingress controller. Then only we can move ahead and create our resource, right? So that's what I'm going to do. I'm just going to enable my NGX ingress controller by using the command minikube add-ons enable ingress. So for this command to execute, it's going to take you a minute or two. So I recommend you to be a little patient. And once that is done, you can see that the ingress add-on has been successfully enabled. Okay. Once that is done, what we're going to do is we're going to verify that the NGX ingress controller is up and running. For this, I'm just going to execute the command kubectl get pods -n kubesystem. So I've just opened the link and you can see that the output is hello world version 1.0.0 and also the host name has been specified. You can now access the sample application via the Minikube IP address and node port. Okay, so what we're going to do is we're going to access the application using the ingress resource. Okay, so firstly, we will have to create an ingress resource, right? I'm just going to clear my screen. So there is a file which is an ingress resource that sends traffic to your service via helloworld.info. So first we are going to check out the file. So for that, I'm just going to go to my web browser. So I just have the link of the YML file and you can see that the YML file has the API version, the kind, the metadata, the specification, the rules. We discussed the rules, right? So all of that has been specified in this YML file. Now what we're going to do is we're going to create this YML file, right? So I'm going to switch back to my terminal, and I'm just going to use the kubectl apply command. So I'm just going to type out the file that it has to fetch. I'm just going to cross check if it is right. And once that is done, I'm just going to execute it. So you can see that the example ingress has been created. Okay, so we're just going to verify the IP address is set. And for that, we're just going to use the command kubectl get ingress. So you can see that the example ingress has been created successfully, and it hosts helloworld.info, and there is an address, its ports, its age, all of that information has been given. Okay, so now what we're going to do is we're going to add the IP address to the bottom of the etc host file. So for that, what we're going to do is we are simply going to edit the file. I'm just going to execute the command vim host. Okay, so now that it is open, we can edit it. So once I get on the insert mode in this file, so I'm just going to add the IP address. So I'm just going to type in hello world info. So what this does is this sends requests from helloworld.info to Minikube. Okay, so I'm just going to click escape, save this file. So once that is done, what we're going to do is we are going to verify that the ingress controller is directing traffic. And we are going to do this using the curl command. You can see successfully the command has been executed. So if we shift to the browser, you can see that it's up and running. Okay, once that is done, I'm going to shift back to my terminal. So now what we're going to do is we are simply going to test our ingress. Okay, so in the next part of the session, we'll be testing our ingress. So testing is the absolute same way. You're simply going to be accessing using the curl command, and it will just give you the output of what you are accessing. You can create many deployments, and you can also add these deployments to your example ingress.yml file, and this will also be tested and it can also be applied. So firstly, we will understand why do we need stateful set in Kubernetes. So as I've already mentioned in the introduction, stateful set is used to manage stateful applications. What it really does in Kubernetes is that it manages the deployment and scaling of a set of pods. So the pods that you create in Kubernetes is simply a collection of one or more containers and is the smallest unit of a Kubernetes application. So stateful set really manages the deployment and scaling of a set of pods. Okay. The second reason as to why stateful set is required in Kubernetes is that it provides guarantees about the ordering and uniqueness of these pods. Also, unlike a deployment, a stateful set maintains a sticky identity for each of the pods. Replica pods of MySQL, for example, are not identical. These pods are created from the same spec but are not interchangeable. Each has a persistent identifier that it maintains across any rescheduling. The persistent identifiers are predictable pod name like mypod0, mypod1 instead of hash fixed endpoint or individual DNS name. So when a pod restarts, while the IP address changes, the name and endpoint stay the same. Stateful sets currently require a headless service to be responsible for the network identity of the pods. That is, we are responsible for creating this particular service. And stateful sets do not provide any guarantee on the termination of pods when a stateful set is deleted. To achieve ordered and graceful termination of the pods in stateful set, it is possible to scale the stateful set down to 0 prior to deletion. The storage for a given pod must either be provisioned by a persistent volume provisioner based on the requested storage class or pre-provisioned by an admin. Now that we know why stateful set in Kubernetes is really important, let's move ahead and talk about what is Kubernetes stateful set. As I've already mentioned before, stateful set is the workload API object used to manage stateful applications. It basically manages the deployment and scaling of a set of pods and provides guarantees about the ordering and uniqueness of these pods. Like a deployment, a stateful set manages pods that are based on an identical container spec. Unlike a deployment, a stateful set maintains a sticky identity for each of their pods, and these pods are created from the same spec but are definitely not interchangeable. Each of them have a persistent identifier that it maintains across any rescheduling. We've already discussed these points in the previous part. Now, if you want to use storage volumes to provide persistence for your workload, you can use a stateful set as a part of the solution. Although individual pods in a stateful set are susceptible to failure, the persistent pod identifiers make it much easier to match existing volumes to the new pods that replace any that have failed. So, in short, a stateful set is a Kubernetes controller that is used to manage and maintain one or more pods. However, so do other controllers like replica sets and the more robust deployments do. So, what does Kubernetes use stateful sets for? A stateless application is one that does not care which network it is using, and it does not need permanent storage. Some of the examples of stateless applications may include web servers like Apache, Tomcat, etc. On the other hand, we have stateful applications. Now, if you deploy such applications on Kubernetes, you'll need to ensure that pods can reach each other through a unique identity that definitely doesn't change. Some examples of stateful applications include MySQL clusters, Redis, Kafka, MongoDB, and others. Now that we understand what a stateful set, let's move ahead and talk about the differences between stateful set and deployment. So, at the heart of any Kubernetes deployment strategy lies the pod, the workhouse of distributed container solutions. The Kubernetes pod glues together a bunch of containers to a single networking stack and process namespace. Pod processes can communicate with one another over loopback and signal each other using signal mechanics. Deployments in stateful sets allow you to scale up your pods, roll out new images and configurations, and much more. But how do you pick which one to use for a given situation? It all depends on what you want out of your pods. So when your pods are interchangeable, you can use deployment. If scaling up means just run more of these, then you want a deployment. These are by far the most common in the wild, and they fit very nicely with application workloads and other 12-factor applications that share no state and have no need for identity. Let's say you have a deployment of a Rust-based web application. The load balancer out front routes traffic to the single application instance. The application itself keeps all state in the relational database behind it. So if you want to scale it, you have to just ask for more copies, as you can see in figure 2. Kubernetes deployment controller immediately springs into action, creating all of the new pods at once. Now, these new pods boot with the same environment variables set and the same config maps mounted in, presumably allowing them to talk to the database just like the first pod. The best use cases for deployments is when you want to use stateless application workloads and when you just want a single pod. Now we'll understand when to use stateful set. The 12-factor never be responsible for the data approach is a great one for commodity computation, like the kind of workloads that make up API services, backend service brokers, etc. Eventually, somebody has to actually handle data in order to make the whole thing worthwhile. Now, to scale stateful systems, you need a stateful set. Now, let's consider the relational database system behind the applications. Ideally, we'd like to be able to scale it up and build some sort of consensus-based leader or follower topology. We can't really discuss the details of how this would work, but suffice it to say that one cannot hold elections without identity. When we scale the stateful set from one replica to 3, the stateful set controller starts to incrementally deploy a new missing pods one at a time. First, the pod 1 comes up initialized and then settles into a ready state. Then the second pod does likewise. One of the more powerful features of a stateful set is the use of persistent volume claim templates, a means to provide each pod in a stateful set with its own persistent volume. Now, if you're trying to replicate database contents, this is a critical capability. The best use cases for stateful sets are when you're working with data services like databases, key value stores, etc., Or if you're working with identity sensitive systems like consensus systems, leader election clustering, etc., or anything that really needs a slow rollout. Now that we know the difference between when to use deployments and when to use stateful set, let's go ahead and check out a stateful set example. So now currently I'm working on my Linux virtual machine. So if you want to try this on Ubuntu, you can follow this procedure. So before we begin, there are some prerequisites. Firstly, you will have to download kubectl, you have to download Minikube, you will have to download Docker, all of the procedure you can find in their official website. So install all of that and then we can get started. So the first thing that we're going to do is I'm just going to start my Minikube using the command sudo minikube start. Okay, so once that is done, you can see that kubectl is now configured to use the Minikube cluster and default namespace by default. I'm going to clear the screen. So sometimes running Minikube with the default resource configuration results in inefficient resource errors. So to avoid those errors, you can also start Minikube with start -- memory 2048 -- CPUs is equal to 2. Or you could just use the Minikube start command. I've already mentioned that stateful sets require a headless service to be responsible for the network identity of the pods, and we are responsible for creating the service. Stateful sets are intended to be used with stateful applications and distributed systems. However, in order to demonstrate the basic features of a stateful set, what we're going to do now is we will deploy a simple web application using a stateful set. So we're going to use a web.yml file which creates a headless service called the Nginx service to publish the IP addresses of pods in the stateful set. So what we're going to do is I'm just quickly going to open my web browser. So I'm just going to copy this web.yml file and I'm going to paste it on my web browser so we can view the entire file, the YML file. So I'm just going to explain this YML file really quickly. So firstly, there is a headless service which is named Nginx that is used to control the network domain. The headless service is created by explicitly specifying none for the cluster IP. So for the headless services, a cluster IP is not allocated. This is what we'll have to remember. So the stateful set, which is named web, has a spec that indicates that has two replicas of the Nginx container, which will be launched in unique pods. We must also set the .spec.selector field of a stateful set to match the label of its spec template metadata lab. And the volume claim templates will provide stable storage using persistent volumes. So I know we haven't learned what is persistent volume, but it is simply a piece of storage in the cluster that has been provisioned by an administrator. So that's what a persistent volume is. Kubernetes creates one persistent volume for each volume claim templates. In our case, each pod will receive a single persistent volume with the default storage class and one GIB of provisioned storage. Now, when a pod is rescheduled or scheduled onto a node, its volume mounts mount the persistent volumes associated with its persistent volume claims. However, the persistent volumes associated with the pod's persistent volume claims are not deleted when the pods or stateful set are deleted. This must be done manually. When the stateful set controller creates a pod, it adds a label statefulset.kubernetes.io/pod name that is set to the name of the pod. And this label allows you to attach a service to a specific pod in the stateful set. So I'm going to switch back to my terminal. First, what we're going to do is we are going to start with creating the stateful app. That is the stateful set along with the persistent volumes and the headless server. And we're going to do this using the kubectl apply command. So after the -f flag, I'm just going to paste the YML link. So you can see that we have created the headless server and stateful set successfully, which is defined in the web.yml file. And I'm going to open another terminal. And here we are going to use the kubectl get command to watch the creation of the stateful sets pods with selector flag. So I'm just going to use the kubectl get command. And you can see an output that is very similar to this. So you can see the status, you can see if it's ready, the age of it, how it restarts. etc. All of that you can see here. Now, the pods I've already mentioned in a stateful set have a sticky unique identity. This identity is based on a unique ordinal index that is assigned to each pod by the stateful set controller. Now, the pods' names take the form stateful set name ordinal index. Since the web stateful set have two replicas, it creates two pods, that is web O and web 1. You can see that on the screen, right? Now, each of these pods have a stable host name based on its ordinal index. So as you can see that each pod has a stable hostname based on its ordinal index. And we can also use the kubectl execution command to execute the hostname command in each pod. Now when the pods restarted, the pods ordinals, host names, SRV records, and A record names have not changed, but the IP addresses associated with the pods may change. You can use the delete command to delete all the pods in a stateful set and wait for the stateful set to restart them and for both pods to transition to running and ready. And we can do this using the delete command. So I'm just going to first clear my screen and I'm just going to use the kubectl delete command. So it says the pods have been deleted. Now what I'm going to do is I am going to use the get pod command. Now the status is currently terminating. That means it is deleting. Now again, if I execute the command, it says the status is container creating. So there's a lot of things that you can really do in stateful set. You can write to stable storage using the persistent volume claims for all of the pods. You can also scale up via stateful set using the kubectl scale stateful set. So this is all to begin with stateful set. Let's move ahead and check out its limitations. So the storage for a given pod must either be provisioned by a persistent volume provisioner based on the requested storage class or pre-provisioned by an admin. Also, deleting and or scaling a stateful set down will not delete the volumes associated with the stateful set. This is done to ensure data safety, which is generally more valuable than an automatic purge of all related stateful set resources. Stateful sets currently require a headless service to be responsible for the network identity of the pods, and you are responsible for creating the service, which can be sometimes a limitation. Stateful sets also do not provide any guarantees on the termination of pods when a stateful set is deleted. To achieve ordered and graceful termination of the pods in the stateful set, it is possible to scale the stateful set down to 0 prior to deletion. And when you're using rolling updates with the default pod management policy, it's possible to get into a broken state that requires a manual intervention to repair. So these are some of the disadvantages of a stateful set. Challenges of data. Now, containers have changed the way we build, ship, and run applications. This transformative technology affords great velocity and application portability, but has also brought new challenges to technology teams. The challenge of persisting data in a transient system. As I've already mentioned in the introduction, Kubernetes is the leading orchestrator for container workloads. So let's discuss a particular scenario. What if a container stops for one reason or another? Kubernetes is definitely able to start a new instance almost immediately, making availability and recoverability something that happens in seconds as opposed to minutes or even hours. But this new instance of the application may not have access to the file system from the old instance, especially in the case of local file systems, so additional orchestration is required to ensure that the stateful component of the application is bound to the instance at restart. This focus on stateless applications and epithermal systems have prevented certain stateful and complex applications from being a good fit for this revolutionary technology. As companies look to bring applications into Kubernetes, the inability to persist data through a container's lifecycle is undesirable. People need a way of dealing with stateful applications and persisting data, all without inhibiting the positive aspects of the self-healing capabilities of the Kubernetes platform. Now, to get a better sense of how to address challenges in Kubernetes, we'll take a look at one of the earliest challenges that have been successfully addressed, that is handling log data. The Kubernetes community found a successful way to address log data by sending it to an external system. Now, by using solutions such as the Elasticsearch, Logstash, and Kibana stack, you have a pattern of leveraging an agent in a container alongside different applications. Now, the process enables developers to send logs to a standardized endpoint, which makes it portable and flexible. In the enterprise, moving storage into external system isn't something new or unique. The use of a storage area network, that is SAN, has been a staple practice of enterprises for a large number of years. But typically, it has been implemented by delivering a pre-configured, dedicated volume to a virtual or physical machine. So now the next question that arises is, how do you provide a stable storage solution for any type of content with an equally composable and portable convention as the EKL pattern? Firstly, you do not want to inhibit your IT team's abilities to back up, recover, or secure the data either. Fortunately, this is where Kubernetes enters the picture. Its features and capabilities address this challenge as they are rapidly growing and maturing. Kubernetes began with the storage features as part of the pod API and soon expanded these into standalone interfaces, which include volumes, persistent volumes, storage classes, and container storage interface. In the previous sentence, if you noticed, I mentioned the word pod. You must be wondering what pod is, right? A pod is simply the smallest schedulable resource in Kubernetes. It is a logical collection of containers which ensures the encapsulated containers share resources and are hosted on the same node in your cluster. So typically a pod really contains of a single container and is an instance of an application. Now let's move on to the next topic of this session and discuss volumes in Kubernetes. The Kubernetes volume in its simplest form is a directory that's attached to a pod and mounted to one or more containers in the pod. Such coupling is tight and is a foundational construct for how data can be presented to a container. Now, because of this relationship with the pod, Kubernetes volumes are designed to have the same life cycle as the pod. If an epithermal volume is defined by the pod, for example, its contents do not survive a container restart. Now, when a pod is removed from Kubernetes, any volume relationships are broken and epithermal volumes will be destroyed. Kubernetes volumes are typed, which is how you define the storage mechanism backing the volume. Volume characteristics may be defined via volume type specific parameters. This may be a physical disk or path on the Kubernetes node, a SAN, a network attached storage, or even a storage service from a cloud provider, to name a few. So what really volumes do is it really allows applications to have a very defined storage part that stays consistent through the redeployment of a container. Okay, so this layer of abstraction really helps, but on its own does not solve all persistent storage concerns. There are many special volumes available for use, like the empty directory, config map, secret. So all of these have their own advantages and can be used in many ways. When a pod is scheduled to run on a node, a volume is created on that node and will remain there until the pod is deleted or moved to another node. This volume is an empty directory volume that begins empty and is backed by the storage of the host itself. The other two types of config map and secret are volumes whose content is actually stored by Kubernetes. This mechanism is often used to pass configuration information, such as credentials, into a container and ensure they are available wherever the pod is scheduled to run. Now that we understand volumes just allow applications to have a defined storage path that stays completely consistent and same throughout the redeployment of a container, let's move ahead and talk about persistent volumes in Kubernetes. Now, as the relevance and utility of local storage options are literally exhausted, the need arises to leverage external storage. Individual nodes may have storage provided by a SAN, but that's not the same as being able to orchestrate the external storage along with the rest of the instructions for managing an application. Kubernetes here provides a persistent volume claim, which is a request for storage. So the request made by the persistent volume claim defines characteristics of the storage that are desired by your application, such as access and volume modes, size of volume, selectors, storage cache, all of that. In conjunction with PVCs, that is persistent volume claim, Kubernetes also provides a persistent volume resource. Okay, so a persistent volume has historically been a pre-provisioned storage volume, but more commonly is provisioned from a storage class dynamically and made available to the cluster for use by a pod. So persistent volume is simply a piece of storage in the cluster that has been provisioned by an administrator. And it also provides a persistent volume claim, which is basically a request for the storage. And you can see all of this represented in the diagram on the screen. In a Kubernetes cluster, when you create a storage class, you define provisioners, parameters, and reclaim policy. Provisioners are the utility or component responsible for interacting within the backend storage system, whereas parameters helps in the setting or values that you can pass to the provisioner. The reclaim policy instructs Kubernetes to either retain or delete the volume when it's released. If your volume is retained, you may need to perform your own volume cleanup and maintenance. To make storage systems support more extensible, plugin based storage driver mechanisms are really important and necessary. So instead of only developing and shipping storage drivers as part of Kubernetes itself, storage vendors and users wanted a way to provide and use the drivers they need and to omit the ones they do not. So along came CSI and Flex Volume, which are the out of tree extension points for storage drivers. Both of these plugin types allow for administrators to deploy storage drivers that can be loaded dynamically by Kubernetes nodes, and both provide the ability to provision volumes of any number of storage types. Flex Volume was introduced first, but CSI is emerging as a more dynamic and comprehensive specification. Flex Volume is included for completeness, however, the convention is being only deprecated. Only use it if you must. On the other hand, the CSI specification outlines a number of storage operations in a way that can extend to additional container orchestration platforms. Now that we understood what are volumes and persistent volumes in Kubernetes, let's move ahead and talk about why do containers need storage. Okay, so when you think of adopting a new application architecture, such as, cloud native, it seems really logical to do with a new application. More times than not, however, you do not find yourself only developing new applications. If you're like most folks, you have to blend the traditional needs of applications and the functions they serve while applying emerging application architectures to improve speed, adaptability, and costs. Now, at this point, Kubernetes and the real world collide, and storage is a big part of this transformation. So I'm sure most of you are aware that you build business applications in containers. They implement business logic, automate decisions, and really set out to make our lives much easier. Your applications also produce a lot of data. It may be in the form of files, data tables, reports, and much more. Building small functional bits of logic into containers is a very good decision, but what would you do with so much data? Now, without storing data in a persistent volume, the file system of a container is also epithermal. Now, when a container restarts, the file system is reset to whatever the file system state is in the container's image, and files not stored in a persistent volume do not survive the restart. You really need a sustainable and supportable way to store data and objects in flight or as output from your applications while taking advantage of the portability, scalability, and recoverability of containers. Now, instead of fighting the natural tendency of containers to be stateless and lightweight, the pattern looks to augment Kubernetes to facilitate the behaviors we want. If your Kubernetes cluster has access to or is in public cloud providers such as AWS, you have the platform services that can provide block devices, file system as a service like Elastic File System, databases as a service like Relational Database Service, and object storage like Simple Storage Service. Now, each of these offerings have individual performance characteristics, that is, they have their own pros and cons, and you must align your application and workload with the proper type of storage for its needs. This alignment requires multiple unique methods and processes for orchestrating the various storage mechanisms, and not all are aligned with the way the application is orchestrated by Kubernetes. GCP, AWS, and Azure all have storage drivers in Kubernetes, that help offload the concerns of managing and provisioning the platform storage services and provide a common interface in PVCs and storage classes. But how do you achieve parity for clusters running inside corporate data centers or for storage services you wish to use when a consistent experience in Kubernetes doesn't exist yet? There's one solution, which is to host your own storage system. So let's move ahead to the next part of the session and check out the storage solutions in Kubernetes. Hyper-converged infrastructure is the combination of compute, networking, and storage, all implemented as software and all deployed on the same nodes. Now, this software-defined approach introduces immense flexibility in the underlying hardware, eliminating dependency on specific vendors and specialized components. It also affords IT teams the ability to achieve portability and consistency of management and configuration. Rook is a storage orchestration for Kubernetes. It uses the declarative nature of Kubernetes to make storage services self-healing, self-scaling, and managed with similar conventions as your containerized applications. Rook uses a plugin extensible architecture to help you automate storage administrative tasks such as deployment, bootstrapping, configuring, scaling, provisioning, and monitoring. So, what does this really mean? Rook allows you to use a declarative style of management that really empowers you to achieve as code capabilities for a multitude and various types of storage types. It implements the new necessary Kubernetes objects so you have a common interface to provision storage software that provides object, block, and file system storage types. That is, Rook goes way beyond primitive storage types and also really enables you to orchestrate databases and other storage types in a claims-based fashion. This common way of dealing with volumes and now other storage types in Kubernetes is one way it is growing to orchestrate all of the storage types. So Rook on its own isn't a storage system. It must be coupled or collaborated with a portable storage subsystem or service. So Rook has operators to support the following storage backends, and one of it is Ceph. Ceph is a high-performance distributed storage platform designed to bring similar capabilities found in GCP and AWS to any cloud platform such as Kubernetes. It provides object storage, block storage, and distributed file systems backed by a single reliable storage cluster, which is running on commodity server hardware. Ceph is designed to be extremely scalable. It is based on the reliable, autonomic, distributed object store that is a self-healing system that distributes and replicates data safely across storage nodes. It then layers a distributed file system, block storage service, and S3 compatible object storage service on top of RADOS, that is the reliable, autonomic, distributed object store. So there's a huge advantage of using Ceph, that is, it is open source and purely software. It can really provide its rich set of storage capabilities and features when deployed across almost any server hardware and either hard drives, SSDs, or any combination of the two. It is widely used in a range of environments, especially private cloud deployments, but it can be complicated to properly provision and connect a Ceph system to Kubernetes. Rook simplifies the deployment and management of Ceph itself and also provides an extremely simple and Kubernetes native way to provision storage services. So some of the storage best practices are with the persistent volume settings, limiting the storage resource consumption, and definitely making requests and limits on the resources. So the persistent volume life cycle is independent of any particular container in the cluster. Persistent volume claims are a request made by a container user or application for a specific type of storage. So when you're creating a persistent volume, you will have to follow its rules. Okay. The next best practice is to limit the storage resource consumption. It is definitely advisable to place limits on the container usage of storage to really reflect the amount of storage actually available in the local data center or even the budget available for cloud storage resources. There are two main ways to limit storage, that is resource quotas and storage classes. The next best practice is to implement resource requests and limits. Kubernetes provides resource requests and resource limits that really help you to manage resource consumption allowed for individual containers in Kubernetes. So a resource limit can be specified for some temporary storage. Okay. So setting storage requests and limits can help prevent containers from being constrained by resource scarcity on container hosts or taking up too many resources unexpectedly. With this, let's move on to the case study. So the case study that we'll be talking about today is by using a cloud provider storage service to externalize data from the container. As you can see in the figure, you can see the implementation of the application and storage patterns in a progressive fashion. You can use each of these application and storage patterns in the HCI system. Okay. You can also see an application that consumes storage via a persistent volume. And if you move from AWS to a different provider such as Google, you can provision the application in the exact same way. However, if you're running Kubernetes on premises, there is no pre-existing storage service to consume. So here in the figure, an application is attached to a persistent volume backed by Amazon EBS. So now what the application can do is they can use a storage provided by Rook, Ceph, or another software-defined storage solution, which is in turn consuming compute and storage resources from any cloud provider. Okay, so it shows your application deployed to a hyper-converged cluster, and the diagram really illustrates your ability to make your applications portable across similar HCI clusters hosted in two different providers. It is really critical to point out that this is accomplished with only one set of orchestrations to manage applications and storage, thanks to the common interfaces and consistency provided by Kubernetes plus the Rook and Ceph combination. You can now move your applications as is between providers now. So the diagram that you see has an application that consumes persistent volumes that are provided by Rook Ceph in any environment. Why use Prometheus? Before we answer this question, first let us understand what is Prometheus. Now, Prometheus is an open source systems monitoring and alerting toolkit that was originally built at SoundCloud. Since its inception in 2012, many companies and organizations have adopted Prometheus, and the project has a very active developer and user community. So if you have any queries, you can address them to the community, and I'm sure you'll have a very quick response. It is now a standalone, currently it is a standalone open source project and maintained independently of any company. To emphasize this and to clarify the project's governance structure, Prometheus joined the Cloud Native Computing Foundation in 2016 as the second hosted project after Kubernetes. Prometheus is free and an open source event monitoring tool for containers or even microservices. It collects numerical data based on the time series. So the Prometheus server works on the principle of scraping. This invokes the metric endpoint of the various nodes that have been configured to monitor. Now, these metrics are collected in regular timestamps and stored locally. The endpoint that was used to discard is exposed on the node. Prometheus works very well for recording any purely numeric time series, that is, it fits both machine-centric monitoring as well as monitoring of highly dynamic service-oriented architectures. Now, in a world of microservices, its support for multidimensional data collection and querying is a particular strength. It is designed for reliability to be the system you go to during an outage to allow you to quickly diagnose problems. Now, as we've already discussed, each Prometheus server is standalone, not depending on network storage or other remote services. You can rely on it when other parts of your infrastructure are broken, and you do not need to set up extensive infrastructure to use it. Prometheus is a pull-based tool. There are basically two kinds of tools that are currently present, that is a pull-based and a push-based tool. And Prometheus, as you can already see, is a pull-based tool. And as I've already mentioned in the previous slide, what the Prometheus server does is it works on the principle of scraping. That is, it invokes the metric endpoint of the various nodes that have been configured to monitor, and these metrics are collected in regular timestamps by pulling. Finally, the endpoint that was used to discard is exposed on the particular node. Now let's move ahead and understand the main reasons as to why one should use Kubernetes. Now, two technology shifts took place in the past few years that created a need for a new monitoring framework like Prometheus. The first shift that took was the DevOps culture. Now, prior to the emergence of DevOps, monitoring consisted of hosts, networks, and services. But now, what developers need is the ability to easily integrate applications and business related metrics as an organic part of the infrastructure. And this is because they are more involved in the CI CD pipeline and can do a lot of more operations debugging on their own. Monitoring needed to be democratized, making them more accessible and cover additional layers of the stack. And the other technology shift that resulted in needing a new monitoring frame is containers and Kubernetes. Container based infrastructures are radically changing how we do logging, debugging, high availability, etc. And monitoring is definitely not an exception. Now you have a huge number of volatile software entities, services, virtual network addresses, and exposed metrics that suddenly appear or vanish. Traditional monitoring tools are not designed to handle this. Now, the question that arises is, why is Prometheus the right tool for containerized environments like Kubernetes? These four characteristics made Prometheus the de facto standard for Kubernetes monitoring. The first one is because of its multidimensional data model. The model is completely based on key value pairs, similar to how Kubernetes organizes infrastructure metadata using labels. It basically allows for flexible and accurate time series data, powering its Prometheus query language. The second reason is it has accessible format and protocols. Exposing Prometheus metrics is a pretty straightforward task. Metrics are human readable in a self explanatory format that we'll see later on in this session and published using a standard HTTP transport. Later on in this session, we can check the metrics that are currently exposed by using our web browser. The third reason is it allows service discovery. Now, the Prometheus server is in charge of periodically scraping the targets so that applications and services do not need to worry about emitting data. That is, metrics are pulled, not pushed. These Prometheus servers have several methods to auto-discover scraped targets. Some of them can be configured to filter and match container metadata, making it an excellent fit for epithermal Kubernetes workloads. The last reason is because of its modular and high available components. Metric collection, alerting, graphical visualization, all of these are performed by different composable services in Prometheus itself. Now, all these services that I just mentioned are designed to support not only redundancy and also sharding. So now that we know what is Prometheus and why we need to use it, let's move ahead and understand what is Grafana. Grafana is a multi-platform open source solution for running data analytics, pulling up metrics that make sense of the massive amount of data, and to monitor our applications with the help of some cool customizable dashboards. What it really does is it helps you identify and tackle performance issues by giving you the tools you need to analyze and monitor your database. Not only does it help solve problems, but it also aids you in becoming proactive with your maintenance by using alert system management. Grafana is open source, compatible with a wide range of databases, and has a thriving community. It also supports a huge number of data sources, and since the application is open source, you can be sure that the moment a new data source has been released, someone out there is adding support for it. The most common use case of Grafana is displaying time series data such as memory or CPU over time alongside the current usage data. Now that we know that Grafana is simply a data visualization tool, let's move ahead and talk about some of its prominent features. The first one is visualize. From heat maps to histograms, graphs to geomaps, Grafana has a plethora of visualization options to help you understand your data very clearly. The second one is alert. Grafana seamlessly defines alerts where it makes sense while you're in the data. It defines thresholds visually, and it can also send you notifications via Slack, PagerDuty, and much more. The third feature is unify. You can bring your data together to get better context. That is, Grafana supports dozens of databases natively. You can also mix them together in the same dashboard. The fourth feature of Grafana is that it is open source. Grafana gives you options. It is completely open source and backed by a vibrant community. You could also use Grafana Crowd or easily install it on any platform. Moving ahead, let's discuss and talk about Kubernetes monitoring architecture. Now, as you can see, there is a Kubernetes API, there are Kubernetes nodes. In the middle, we have the Prometheus server, we have the Prometheus Alert Manager, and then finally we have Grafana. Now, in the first step, the Prometheus servers need as much target auto discovery as possible. And there's several options to achieve this. That is via Prometheus Kubernetes Service Discovery, or the Prometheus operator and its custom resource definitions, or even Consul SD, Azure SD for Azure VM, GCE SD for GCP instances, EC2 SD for AWS VM, and also File SD. Apart from the application metrics, we also want Prometheus to collect metrics related to the Kubernetes services, nodes, and orchestration status. For example, node exporter for the classical host-related metrics like CPU, MEM, network, etc. And also kube state metrics for orchestration and cluster-level metrics for deployments, pod metrics, resource reservation, etc. And finally, Kubernetes control plane metrics like kubelet, etcd, DNS scheduler, etc. Prometheus can basically configure rules to trigger alerts using PromQL. Alert Manager will be interchangeable. Now moving on to step 4, Prometheus can configure rules to trigger alerts using PromQL. Alert Manager will be in charge of managing alert notifications, ping inhibition, etc. Now the Alert Manager component configures the receivers and gateways to deliver alert notifications. Finally, Grafana can pull metrics from any number of Prometheus servers and display panels and dashboards, that is the visualizations of data. So this is the basic architecture that you see. As we've already discussed, Prometheus and Grafana are pull-based tools. So all of these metrics that they want to scrape are pulled from their respective targets, and then they're finally displayed based on visualizations or metrics, anything. Along with Prometheus and Grafana, we'll be making use of Helm, which helps you manage Kubernetes applications. Helm charts here help you define, install, and upgrade even the most complex Kubernetes applications, and this is exactly why we need to be working with it today. Helm charts are really easy to create, version, share, and publish. So I think it is really important for everyone to start using Helm and stop the copy-paste part. Helm is basically a graduated project in the CNCF and is maintained by the Helm community. We'll move ahead and talk about some of its features. First one is it helps in managing complexity. Helm charts describe even the most complex applications that provide repeatable application installation and also serve as a single point of authority. Also, Helm has extremely easy updates. They take the pain out of updates with in-place upgrades and custom hooks. There is also an option of extremely simple sharing. Charts are easy to version, share, and host on public or private servers. Finally, Helm also supports rollbacks. You can use the Helm rollback option to roll back to an older version of a release with complete ease. With this, we'll move ahead to the demo part of the session and install all of the tools that we'll be working with in this session. So now for the demonstration part, I'll be working on my Ubuntu virtual machine. So there are some prerequisites before we get on this demonstration. So the first thing is that you will need a Kubernetes cluster up and running. Kubernetes has a local cluster that is Minikube. So I have both Minikube and the command line interface tool that is kubectl installed on my virtual machine. So that is one thing. The second thing is you'll have to download Helm. As we've already discussed, Helm is basically a package manager for Kubernetes where developers develop and manage Kubernetes using the Helm chart. Okay, so now what we're going to do is we already have Minikube and kubectl installed on the VM, but we do not have the Helm chart up and running. So firstly, I'm going to check out the Minikube version for you all to know which version I'm currently working on. You can see that I'm working on Minikube version v1.20.0. Okay, so now let's start Minikube. I'm going to use the command sudo minikube start for this. And as you can see that Minikube is up and running. We have configured to use the Minikube cluster, and we have one default namespace that is named default itself. Okay, now that we have Minikube up and running, I'm just going to clear my screen. So now what we're going to do is we are going to view all the namespaces that are available in the Minikube cluster, and I'm going to do this by using the command kubectl get ns, that is namespace. So once that is done, you can see that there's a default namespace which is active and created 13 hours ago. You can also see some namespaces. You can also see kube node list, kube public, and kube system namespaces. So now what we're going to do is we are going to go and download Helm tool in our VM. So I'm just going to quickly switch to my browser and I'm just going to look for Helm. So this is the first result, and as you can see, you have Helm, the docs, charts using Helm, the architecture, and installing. So I'm just going to click on installing. This will redirect me to the official website of Helm, and this entire guide really shows how you can, download Helm into your OS. So there are various OSs that Helm can be installed within, that is Mac, Linux, or even Windows. So there are basically two ways to install Helm. The first one is the official methods to get the Helm releases, and the second one is through different package managers. Okay, so installation through these methods can be found on this page. So you can download Helm from the binary releases or from script or through package managers. Okay, so I'm just going to download it from the binary releases. And for this, there are 3 steps that can be followed. So the first step will allow you to download your desired version, and then you can unpack it and then find the Helm library in the unpacked directory and move it to the desired location, that is user local bin. So I'm just going to open this page, and this will take me to GitHub where all of the Helm releases have been put into. So currently I need to download Helm Linux AMD 64. So I'm just going to click on that. This will download a tar file of the Helm package. I'm just going to say okay. I'm just going to click on this and I'm going to click extract. And this will allow me to untar it right here. So I can extract the file. So I can extract or unpack my package right here. So I'm just going to click on the extract option. I'm okay with extracting my file in home. I'm just going to say show the files and you can see that it's been extracted. Okay, that's great. I'm just going to close this window. Now that we have unpacked it too, we can skip this step, directly move the Helm binary into its desired location, that is user local bin Helm. Now I'm quickly going to switch back to my terminal and I'm just going to paste this command. So we're using the move command, that is MV, to move the file into the desired location. Okay. So once that is done, we have our Helm binary in our user local bin location, our desired location. Okay. So now that we also have the Helm binary in our VM, so now we're going to get started with the next part of the session. So the first thing that we're going to do is we are going to check the status of Minikube using the Minikube status command and check if it's up and running. So you can see that it is all configured and running. So what we're going to do now is we are going to look at our namespaces that are available, which we have already. So these are the namespaces that we currently have. So what I'm going to do now is I'm going to create a new namespace. Okay. So for that, I'm just going to use the command kubectl create namespace Prometheus. So I'm just going to use the command kubectl create namespace to create a namespace that is named Prometheus. All right. I'm just going to enter and it says a namespace Prometheus has been created. Okay. Now, if you want to view the namespaces, I'm just going to use the kubectl getNS command and you can see that the Prometheus namespace has been created. It's active and its age is 12 seconds. So once we have created our namespace, so now what we're going to do is we're going to install the Prometheus operator. Before that, we'll need to have the Prometheus Helm chart installed successfully in our VM. So we're going to do that. I'm just going to clear the screen. So for this, I'm going to use the sudo helm repo, that is repository add. We're going to add a new repository and name it whatever you want to. So we're going to add a repository that is named monitor, and I'm just going to use charts.helm.sh/stable. So I'm just going to use the Helm repository add command to add a new repository that is named monitor. And I'm just going to add the link to from where the charts can be installed from. Once that is done, I'm just going to click enter. So you can see that monitor has been added to your repositories. Now we're quickly going to update our repositories using the Helm repository update command. So just going to add all of the latest information into our repository. So once that is successfully completed, what we're going to do is, so finally we're going to install the Prometheus operator into our local machine. Okay. And now we need to make use of the Helm chart of the Prometheus operator to deploy Prometheus and Grafana and many other services, in fact, that have been used to monitor Kubernetes cluster. So for this, we're going to use the command helm install Prometheus monitor. This is the repository name, /Prometheus operator. So we're going to just specify the namespace that it has to be installed within. So you have the helm install command, and we are going to install Prometheus into the monitor repository, and I'm going to click enter. So now you can see that the Prometheus operator has been installed successfully, and you can check its status by running this command. So before we do that, what we're going to do is we are going to check the pods that have been installed in our namespace Prometheus. So for this, you can just use the command kubectl get pods -n Prometheus. So the flag that we specify here, that is -n, allows us to choose our namespace. So if you want to, find the pods of the default namespace, you can just specify this flag and then mention the name for it. So we're just going to check out the pods that are currently present in Prometheus. You can see that we have the alert manager that's running, we have Grafana, we have Cube State Metrics, we have Prometheus Node Exporter, we have the operator, we also have Prometheus running. Okay, so this is great. So what we're going to do is we're going to activate the Prometheus server. And how do we do this? We're just going to simply use the command kubectl port forward, and we're going to specify the namespace. We're just going to copy this entire pod name, and I'm just going to paste it. So you have to specify the namespace that you're working on and repeat. So we're just going to use the kubectl port forward command. We're going to specify the namespace, specify the name of the pod, and then finally specify the port that it can run on. Okay, and I'm going to quickly switch to my web browser, and let's check out if Prometheus is up and running. This is how the Prometheus time series looks like. There's a navigation bar on the top. You can see alerts, you can see graph, you can see the status, you can see different rules, targets, the service discovery. You can also get help from the Prometheus community, and you can add an expression here. You can execute it and view it in graph or in the console. So if you click on the insert metric at cursor option, you get many queries that you can work with. Now, if I want to check the kubepod info, okay, I'm just going to execute this command, which shows the node count and the value is currently 1. If you want to check out the graph, you can just click on the graph option and it will execute the graph. Okay. And if you want to see the memory available, okay, the sum of the memory that is available, you can execute this command and you can see the value on the right hand side. There's several other queries that you can execute, and we're going to do that now. We will check out the namespaces that has been created. Okay, so you can see the instance, you can see the namespace. As we've already noticed and seen before, we had 4 namespaces initially, One is the default namespace that is created by Minikube. Then we had Cube System, then we had Cube Node Lease, and then we had Cube Public. But we created we created Prometheus. So we have 5 namespaces. That is great. Also, if you want to check out the node information, you can execute this command. And you can see the container runtime version, that is Docker, the endpoint. You can also see the job. All of that can really happen within the Prometheus. Now, if you want to create your own rules, you can create them henceforth from here onwards. You can see the alert manager rules. You can also see the etcd rule that is present in Kubernetes. You can see the K8 rules, that is the Kubernetes rules. All of that can be accessed via the status option. You can also see the targets. Currently, we have the alert manager up and running. We also have the API server, which is up. You can see that the kube controller manager is down. All of the statuses of each of these targets also can be viewed in this command. So this is a pretty important option in Prometheus itself. If I want to view the command line flags, I can just check them out here. You can see what port it is running on, the external URL, all of that can be viewed here. Then when I click on the runtime information, you can see that the working directory is Prometheus, and all of the information, the Go version is mentioned here, and the Prometheus version is also mentioned here. You can see the number of series in the alert managers. You can see the endpoint. All of that can be viewed here. Okay. Now I'm just going to click on Prometheus. So all of the monitoring part of the data can be done on Prometheus. Let's move ahead and talk about Grafana. So for this, what we're going to do is we're going to quickly switch back to this. Okay, I'm going to clear my screen. So what we're going to do is the Prometheus operator itself installs Grafana and Prometheus with other deployments, right? We saw that. Now with the installation of the Prometheus operator, Grafana is also installed with it. We can access the Grafana dashboard by the port forwarding the Grafana pod. So we're just quickly going to view the pods that are present in the Prometheus namespace. Once that is done, we're just going to use the kubectl port forward command. So we're just going to add the Grafana pod in this. I'm going to quickly copy paste this option. And I'm going to click on port 3000. Now what I'm going to do is go to my web browser and we will look for what's there in port 3000. Okay. You can see that there is a welcome page to Grafana, and also it will prompt you for a username and password. Now to find out this username or password, what we're going to do is we are going to switch to our terminal and we are going to use the get secret command to, check out the password and the username. So I'm just going to type that out. kubectl get secret. I'm going to specify the namespace. So you will get the admin password and also the admin user here. So as you can see that the secret data is encoded with base 64 and you can only decode it so by using a certain command. But before that, if you notice that the admin password has been decoded and also the admin user has been decoded. So what we're going to do now is we are going to get the username using the command OpenSSL base 64-D. So this is taking a considerable amount of time to load. I'm just going to clear my screen. So now what we're going to do is we're going to just use another command. So we're going to execute the command and get our admin user and password. Once that has been executed, we are just going to check out the admin username. Okay, so we are just going to echo this and base64, and you can see that the admin username is admin. Okay, and the same thing we're going to do with the password. Okay, we're just going to type in echo and add in the password and decode it using base64. You can see that the password is prom operator. So I'm just going to execute the command kubectl port forward and I'm just going to execute this. So we'll quickly switch to our login page, and you can see that the username is password and password is prom operator. So once you're logged in, you're redirected to the Grafana page. And here you can see that this is the basic structure of Grafana UI. You have panels that you can really move around with and play. You can increase them in size, you can decrease them in size. Most of it is made of panels. If you scroll down, you can see some, information from their blog and community. You can add your first data source, you can create your first dashboard, and you have some icons that are present on the side. You can search for any dashboards that you create. You can create dashboards, add folders, import data. Also, you can manage your dashboards and your playlists, your snapshots. You can explore, you can access alerting. In the configuration options, you can add data sources, you can search for data sources, or add whatever you'd like to by clicking on the add data source option. You can check out the user. If you want to create teams, you can do that. You can check out the various plugins that are available, the preferences, and API keys. Okay. So this is the brief overview of how Grafana user interface looks and how it really works too. So now what we're going to do is I'm just going to click on dashboards and click on manage. So by default, Prometheus operators are deployed with some pre-configured Grafana dashboards. And to see this, you can click on manage on the dashboard options and you can see the default dashboards. So if I want to click on compute resources namespace, this will give me a complete overview of the CPU utilization, the memory utilization, and you can see the CPU usage in the form of a very colorful graph. And you can also see the CPU quota, you can see the memory quota, the network. You can really, see these panels if you want to. You can move these panels, you can arrange them however you'd like to. All of them can be done with these default dashboards that are available. Now, there are several dashboards that are available. Now, if I want to see the volumes, I can also click on this option. Okay, and you can also create your own dashboard. You can add your own data source via Prometheus, and then you can really make your own dashboard. So let's move on to the next part of this session. So now let's check out the challenges of Kubernetes. Okay, so the major challenges in monitoring is that it is really hard to manage and monitor many containers. Also, it is really hard to dynamically monitor clusters, and monitoring new layers of infrastructure can be a little tedious too. But by implementing some right practices and by understanding how Kubernetes works, it is definitely possible for you to overcome all of these challenges that you face while monitoring either containers or while practicing dynamic monitoring or even by creating many layers of infrastructure. Introduction to Minikube. So, firstly, we must understand what is Minikube. As I've already mentioned in the introduction, Minikube is an open source tool that really enables you to run Kubernetes on your laptop or any other local machine. It can work with Linux, Mac, and Windows operating systems. Minikube, what it does is it runs a single node cluster inside a virtual machine on your local machine. So, in other words, Minikube takes the vast cloud scale of Kubernetes and shrinks it down so that it fits even on your laptop. Don't mistake that for a lack of power or functionality, though. You can do plenty with Minikube. And while developers, DevOps engineers, and the like might be the most likely to run it on a regular basis, IT leaders and the C suite can use it too. That's the beauty of Minikube. With just a few installation commands, anyone can have a fully functional Kubernetes cluster ready for learning or supporting development efforts. But all you will need is you'll need 2 CPUs or more. You'll also need 2 GB of free memory, 20 GB of free disk space, internet connection, and a container or virtual machine manager such as Docker, HyperKit, Hyper-V, KVM, Parallel, Spodman, VirtualBox, or VMware. So these are some of the prerequisites. If you have all of these satisfied and installed, then you can get started with Kubernetes in a single command, that is Minikube start. So I'll be working on a Linux virtual machine, that is Ubuntu, and I'll be showing you some of the steps for you to install Minikube on a Linux using, binary download. Okay, so before we begin, we have to install kubectl and minikube. So for installing kubectl and minikube, there's certain set of commands that you will have to remember or that you'll have to execute. You can pick any of the commands based on any of the architecture or OS in the official website of Kubernetes. So to download kubectl, initially you'll have to execute the first command, followed by the second command, and then finally check if it has been successfully installed. Since I've already installed kubectl on my VM, I'm just going to check if it has been installed successfully. And you can see that you have the client version, you have the Git version, the Git commit, you have the build date, the Go version, all of that. So next thing what you're going to do is you're going to download Minikube. So this is the command to download Minikube, followed by install command. And then finally you start the Minikube instance. This is really important, okay? So that's what we're going to do. Once the startup phase has finished, your Kubernetes client kubectl will have a minikube context and will automatically start using this context. Checking what nodes you have in your cluster will return the minikube hostname. So I'm just going to use the command sudo kubectl get nodes. So you can see that there's a node Edureka which is ready. And also you can view the minikube version using the command minikube version. Sorry, I just put an extra O. So currently we have the v1.20.0 version. So I'm just going to clear my screen. Now let's move ahead to the next part of this session and talk about Minikube dashboard. Now the dashboard is a web-based Kubernetes user interface, and you can use it to deploy containerized applications to a Kubernetes cluster. You can also use it to troubleshoot your containerized application, manage cluster resources, get an entire overview of applications running on your cluster. You can also create or modify individual Kubernetes resources such as deployments, jobs, etc. For example, you can scale a deployment, initiate a rolling update, restart a pod, or deploy new applications using a deploy wizard. Now to access the dashboard, you simply use the command minikube dashboard, and this will enable the dashboard add-on and open the proxy in the default web browser. It is worth understanding and noting that web browsers generally do not run properly as a root user. So if you're in an environment where you're running as root, see the URL only option. To stop the proxy, abort the started process using Ctrl+C. So if you don't want to open a web browser, the dashboard command can also simply emit a URL, minikube dashboard -- URL. Now let's switch back to the VM and access the dashboard. So first what we're going to do is we're just going to type the command minikube dashboard. Now once the dashboard has been enabled, you will be automatically redirected to the dashboard page on your browser. So on top, you can see there's an overview button, and here you can see the workload, service, config and storage, cluster, settings, about, custom resource definitions, all of that. You can also see the workload status where you have deployments, the pods, and also the replica sets. Now to create an application, you can just click the plus button in the top right corner, and which will give you three options that says create from input, create from file, and create from form. Here you can specify the application name and also specify the Docker image that you want to use. So after all of that is done, you can just click on the number of pods, the service, and then finally you can click the deploy button, which will be presented with a new view that shows deployments and replica sets. And after a bit of time, you will also see a pod. So these are some of the key API primitives. So I'm just going to create from form. I'm going to type Redis, and also the container image will be Redis. Okay, and then I'm going to click on the deploy option. If you want to view the pods, you can just click on the pod option. If you want to view the replica sets, you can click on the replica sets option, and you can see the replica sets that has been created. You can also view the deployments by clicking on the deployments option. So we can switch back to the terminal now, and we can view all of this using the command kubectl get pods, rs, that is replica sets and deployments. You can see that the Redis pod has been created and the replica set Redis has been created, and also deployment has been created for Redis. Now your Redis pod will be running the Redis server. So you can see that using the logs command. And I'm just going to copy this. So here you can see all of the information, that is the version of Redis. You can also see the running mode and the port that it's currently activated on, and if it's ready to accept connections. So with this, we have discussed what is the dashboard and how to make the maximum use of the dashboard. Now let's switch back to our terminal and clear this. So what we're now going to do is we're going to learn how to manage your clusters. You can pause Kubernetes without impacting deployed application using the mini pause command. You can also stop the cluster by using the minikube stop command. As the same way we started the cluster using the minikube start option, you can also stop it. Okay. You can also increase the default memory limit by using the config set memory command. Okay. You can also browse the catalog of easily installed Kubernetes service. You can do this by using the command sudo minikube add-ons list. You can browse through the Kubernetes services. You can see that the dashboard has been enabled, the default storage class has been enabled, also the storage provisioner has been enabled, and the REST ingress and log viewer, ambassador, autopause, all of that has been disabled as of now. We aren't using it. If you want to delete all of the minikube clusters, you can use the command minikube delete -- all. I'm going to clear the screen. Now, if you want to view the various commands in Minikube, you can just simply type the command minikube -- help, and this will list all of the commands that you can really use. You can see that there's the configuration and management commands like add-ons, config, profile. There are also advanced commands. You also have troubleshooting and debugging commands like describe, CP, authorization, which inspects authorization, and many other commands that you can use. We will now create a Kubernetes deployment named Hello Minikube using an existing image named Echo Server, which is a simple HTTP server with the port set to 8080 using the -- port flag in our command. So you can see that I have typed out the command sudo kubectl create deployment hello minikube image is equal to k8gcr.io/echo server 1.10. And it says that hello minikube has been created. Now to access the deployment, you will have to enter the command expose deployment. The -- type is equal to node port flag specifies the type of the service. So you can see that the service hello minikube has been exposed. Now to verify this expose, you just type in the command kubectl get deployments. You can see that it is ready and up to date and also available right now. Now that the deployment has been exposed, I'm just going to clear the screen. Now you can just use the kubectl get services command, and you can just check out all of the services that are currently running. Now, if you want to delete this service, you can just simply use the kubectl delete service hello minikube. And once that is done, you can see the services that are currently present and you do not have minikube in it. And if you want to stop minikube, you can simply type in the command sudo minikube stop. Once that is stopped, you can also delete minikube by using the minikube delete command. Now let's conclude this session with some tips that you'll require to use minikube. So once you have minikube up and running, the following tips can really help you get the most from the environment. First one is to sharing your Docker daemon. A Docker daemon is included with minikube. This is the same daemon you use for Docker only deployments and can be shared between minikube and Docker. Now, if you share, you can speed up your local tests and make any Docker builds you create available to minikube. The second one is using add-ons. Now, add-ons we already saw in the demo session. They're just the extensions of minikube that you can enable or disable to provide access to advanced features. Add-ons can enable features like the dashboard, registry, credentials, or ingress. You can also use add-ons that are already available, or you can use customizable add-ons by modifying the associated YAML file. The last tip is to gain access to host files. Now, if you want to make files on your host system available to containers running inside minikube, you have a couple of options. First, you can use Minicube's mount command, which uses a 9p file system implementation under the covers to expose host files to the Minicube VM. Now, the Minicube 9p mounts have some performance impacts compared to hypervisor native mounts and work best for directories with just a few files. As an alternative, some hypervisors automatically mount a host system directory and make it available for use inside the Minicube virtual machine. Now, these special mount points that we're talking about provide superior performance to the user definable Minicube 9p mount points. So these are a good option if you need to expose a large collection of files to the containers you're testing inside Minicube. Unfortunately, the hypervisor guest mount points differ depending on the host system OS and hypervisor you are using. So these are some tips that you will have to really remember when you're using Minicube or when you're starting to use Minicube.
Now, AWS, as we know, is the global leader in terms of cloud computing services. So AWS has having always had and currently still it holds the biggest market share in terms of cloud computing. So currently it has almost 32% of market share, then followed by Microsoft Azure, having a market share of around 18 to 19%, and then followed by GCP, having a market share of around 11%. And then we have multiple other vendors, like we have DigitalOcean, we have IBM, we have VMware, we have Alibaba Cloud Services as well. So there are multiple vendors that we have in terms of Amazon Web Services, right? And these all are different cloud platforms. And AWS, as we know, is a collection of more than 150 plus services. AWS has a collection of more than 150 plus services that we can go ahead and deploy our applications on. So when we talk about 150 plus services, that includes services for computation, for storage, for networking, for IoT, for AR, VR. So there are multiple services on which we can deploy it. All the major companies, they all are customers for AWS, be it Hindustan Unilever, be it Netflix, BMW, Adobe. So they have a long list of clients, those who all have deployed the services on top of Amazon Web Services itself. And they are different domains now. As we had discussed, there are 150 plus services currently offered in AWS. To be precise, it is 157. And it offers services on computation, on migration, security, storage, networking, content delivery, messaging, databases, and management tools. And for getting a detailed view here, so we can simply open up this link called aws.amazon.com. We can see the entire list of all the services that AWS has to offer to us. So based on computation, integration, cost management, on blockchain, on containers, on end-user computing, on media services, on IoT, on databases. There are multiple applications on top of which we can deploy the services or deploy our application here. And then why AWS is such a hit? Because of multiple reasons. Because again, AWS has, first of all, a large collection of different services based on different categories, right? For example, suppose if we talk about the computation, then we have the service called as Amazon EC2, where EC2 is cloud computation service. Then we have Lambda as a part of serverless computing. So EC2 is based on the virtual servers, whereas Lambda is based on serverless computing. Then we have ECS as Elastic Container Service, offered as a service on where it is mostly used as a DevOps tool when we are working on the entire AWS platforms. Now here we can get started with Amazon Elastic Container Service for Kubernetes. Now here, first of all, here we have to provision the Amazon EKS cluster. Then we can deploy the worker nodes as a part of CloudFormation template. And then we can connect to EKS using the kubectl. And then we can run Kubernetes application on the entire EKS cluster. We can do that. What is the advantage of EKS over the normal containers? So again, we cannot compare containers over the EKS. So containers are the containers in which we deploy the application, and Kubernetes is simply used for management of those containers. Just like we set up the Kubernetes on our on-premise servers, right? Same way, we can use EKS as a fully managed service offered by AWS, on top of which we can deploy Kubernetes for management of our entire cluster of containers. EKS is a service for deployment of Kubernetes on top of AWS. EKS is chargeable. So not all services are available under free tier, but again, EKS is chargeable. So now let's see how exactly to go around with this one and how to actually start deploying it. So now let's go back to our entire console. All right, so now here we can create the entire cluster here. Now for the implementation of EKS, let's log into the console. Here we can define the root username. Let's define the root username. Now for this, we do need the access to the entire AWS account. Here we can log into our console here. Now, once we log into the console, first of all, we do need to have, now before we can start deploying the EKS here, we do need to have entire custom VPC created. And we also need to deploy the entire custom VPC along with the entire AWS cloud formation as well. Because at the end, we will require to deploy the application on top of our own custom VPC. So now in here, we can define the role here. First of all, in order to get started, we have to define the role. So here we can come back to our service called as IAM. IAM is basically used for identity and access management service. So we can open up IAM, let it open up. May take a couple of seconds. It's taking a bit longer than usual. Now, once we are into IAM here, we have to define the roles here. We can open up roles. And then under roles here, we have to create one role for the EKS. So here we can simply click on create role. Here under the service here, we can choose EKS. So here we can choose EKS manage to, because here we have to allow EKS to manage clusters on our behalf. So here we have to define permissions. We can define add permissions. Here we also already have these two policies, EKS cluster policy and service policy. We can define tags, review. We can name this role as EKS review. Just a moment. Now, once we have the entire role created, now here we will be using this entire EKS review has been created that we'll be using here, right? Now, once we are done, next is we do have to have a custom VPC that we have to create. We do need to have a custom VPC that we do have to create here, right? So what we can do, we can use a custom stack template. So let's first of all fetch the entire VPC template in case there is no VPC created from your end. Just a moment. Now, in terms of VPC, we already have a custom VPC created. So for checking for that part, we can come back to VPC. And because again, as a part of our own cluster management, we do need to have a custom VPC deployed. So first of all, we have deployed the entire role, and then in VPC, we need to have a custom VPC deployed. Here we are using the default VPC that is available from our AWS. So let's change our region from North Virginia to Mumbai. And currently we can see we do have a custom VPC created that we will be using as a part of entire cluster management. Check for the roles as well, just a moment. Now, once we have the VPC and role created, now we can come back to our EKS cluster. So here we can, another service here, we can search for service name as EKS as Elastic Kubernetes service. Let's open this up. And this is a dashboard for Elastic Kubernetes service on top of Amazon EKS service here. And that's how here we have Elastic Kubernetes as a service, which is a fully managed Kubernetes control plane service as a part of service offered by AWS. Now here we have to start by defining a cluster name. Let's suppose here we name it as EKS and review itself, just like the same role that we define here, or we can name it as EKS Edureka. So here we can define EKS Edureka, then we can simply define next step, and then we can define the Kubernetes version. So here we can define Kubernetes version. Which version are we to install here? So by default, it will be set to 1.14, and here we can keep it to 1.13 or 1.15. So by default, it is basically focused on 1.14. And then we can define the role name here, right? Because again, role has to be assigned, because until we have a role defined here, we won't be able to create that. We won't be able, now this entire cluster will not be created, right? So here we can define the entire VPC, that means the custom VPC that we may have created. So we can choose the default one, or we can choose the custom one as well. We can choose default or custom both. We can choose accordingly. So Dilip, so what is the difference between Kubernetes control plane and basic Kubernetes cluster? So it's like now, just like we have a dashboard, Dilip. Now in the default, we have to set up the dashboard, correct? So same way we'll be having the entire control plane with us. And then here we have VPC. So under VPC, we have VPC. In here, we can define the entire subnets one by one. And then we can define the security groups. Let me suppose here we can define in which particular zone and again in which particular subnet we are trying to deploy this one by one. What is a security group? What is the entire security group that we on which we are looking to deploy us? Right. So here we have the entire security groups having the access to one specific protocol from which we can choose. Just like we have multiple services defined here, we can simply define this one by one. So now, once we have defined this, then we have to choose the network group in which we are given the access here, right? And then we can define the private access. If we want to keep it for private within a VPC, then we can define that. And then we can define the public access here by defining the enable. If we want this to be accessed outside our entire current VPC, then we can define the entire VPC endpoint there. And then we can define the entire encryption. If we're looking to encrypt this with our own KMS, then we can simply encrypt that as well. If we are looking to encrypt this with our own KMS, we can do that. And now once we define the entire cluster here, so now in here we can simply define the entire individual clusters one by one. So here we can simply click on create clusters. We can define the cluster templates if we want to start with the entire cluster template based on networking only, or if we want to go for the AWS Fargate, we can simply create the entire cluster templates, and then we can start deploying the cluster, and then we can simply create the entire cluster so that we can start deploying the containers inside this cluster that for which we have deployed on top of AWS. Whatever activity we can do on this console, the same activity can also be done on the entire concept of CLI as well.
So first and foremost, let's try and understand what Azure Kubernetes service is. Now, I'm not going to get into the details of this service right away, but just to give you an introduction, Azure Kubernetes service is a fully managed container management service. It is provided by Microsoft Azure, obviously, which is a very popular cloud service provider. And recent stats also state that it is one of the leading public cloud service providers in the market. So when you talk about Azure Kubernetes, it is basically managed by Microsoft Azure. What it does is it offers serverless continuous integration and deployment experience. Now, what does that mean? What we can do with it? We'll discuss all those things as we get into the details of Azure Kubernetes service. For now, we need to understand quite a few other concepts before we get to that point. But to summarize a few of its benefits, what Azure Kubernetes service does is, what it offers is end-to-end deployment, scalability, and availability. Now, how do these things work? We'll discuss that. But before that, let's try and understand what evolution of software development and deployment is and how it has evolved with time, right? So we all know how applications were built and how they've progressed with time, right? So if you talk about the popular ways in which software development and deployment has evolved, we all think of waterfall model, agile model, and DevOps, which is the current way in which we basically go ahead and deploy applications, right? Or basically not only develop, but also maintain, monitor, and deploy applications, right? So let's try and understand all of these one by one. Let's see how they evolved with time. So when you talk about waterfall model, agile model, or DevOps, they all have these three things, which basically sets them apart, right? The application architecture, be it their deployment or packaging, and finally, the application infrastructure that we can think of. Now, when you talk about the application architecture, the first one, that is your waterfall model, is known for its monolithic architectures, right? Something that we came away from. If you talk about current generation, we are more into the microservices model that is handled by a DevOps, right? So when you talk about waterfall, we had monolithic applications. That means everything was inside a single application. Your servers, right? Your applications, be it your management tools and stuff like that, everything was inside a single application. And these kind of architectures were called as monolithic architectures. Now, with time, we had agile model, where we had multi-tier applications, where some of your applications or some of the functionalities of your applications were handed over to some other domain or to some other tier, right? And hence we had multiple tiers. Say for example, you would have your application tier in one place, and you'd have your basically your database tier in other place, right? Something like that. And when you talk about DevOps, they took this functionality to a further classified, I'd say, architecture, where we had microservices or granular parts of your application that could function independently. Now, why do we need these kind of changes, right? Why did we not opt for monolithic applications? Now, when you talk about monolithic applications, these were bulky and these were very rigid, not easy to basically go ahead and modify. If you had to change the entire thing. When you talk about Agile, it gave you more flexibility. How? We had multi-tiers, right? So if one of the tiers is not functioning, right? So we could actually go ahead and work on that tier, and it would not affect the remaining functionality. But when you talk about DevOps, or when you talk about microservices in particular, it basically breaks down your application into granular chunks where each of these applications performs as a whole, but you can think of them as an individual part, which you can basically go ahead and function or operate on individually, and also ensure that you can basically make changes to these individual parts individually without affecting the functioning of the entire application. Now, when we talk about deployment and packaging, we have different ways in which these applications are hosted, right? Or in which these different ways of software development and deployment work, right? So when you talk about deployment packaging, your waterfall model supported or supports your physical servers, right? You have a physical server. Similarly, when you talk about your DevOps, or rather we have Agile first. So when you talk about Agile, you had your virtual servers. Now, if you talk about cloud computing, yes, to some extent it supports virtualization, but back in those days, virtual servers were a little different. So if you talk about Agile model, it basically lies on a deployment model which is based on virtual servers. When you talk about microservices, on the other hand, they are more based on containers kind of an deployment, is what I would say. Similarly, if you go ahead and discuss their application infrastructure, now for your waterfall models, we had data centers that basically had all these applications being hosted, right? Your monolithic applications. Similarly, when you talk about Agile, we mostly move to the hosted platforms, right? And when you talk about current microservices or your container infrastructure, we talk about cloud hosting. And that is why we've come up with this session where we'd be understanding how containers work on top of cloud. That is your Kubernetes orchestration tool. In this case, would be working on our Microsoft Azure cloud platform. So I believe the evolution of development and deployment is clear to you all. Let us now go ahead and understand or discuss some of the other bits that are there on our plate. Now, before we actually go ahead and understand how Kubernetes works, right? And why are we talking about containers and stuff? Now, to give you a brief about Azure Kubernetes service, as I've already mentioned, it is a Kubernetes service that is hosted on the Azure cloud platform. Okay. So let me just go back to the slide one and explain that again so that we can go ahead and understand how working of Azure Kubernetes happens. So we've already seen this slide, right? What is Azure Kubernetes service, but now it would make a lot more sense for you. Okay. So what can happen, or what Azure Kubernetes service offers to you. Now, if you talk about Azure to start with, it is a popular cloud service provider. What that means is, with Azure Kubernetes or with Microsoft Azure, you can basically have various services that help you in software development, planning, management, right? Be it your administrative practices, development practices, or architectural practices related to a software. All these things can be hosted on a public server in this case, which again can be your Microsoft Azure cloud. Now, what it does is it basically gives you all the services that are needed to carry out all the actions that I just mentioned, where you can rent these resources or follow a pay-as-you-go model and use these services to benefit your requirement. Okay. Now, when you talk about a platform like Microsoft Azure, which again is a cloud platform, as I've just mentioned, the possibility of dealing with applications are plenty, or the possibilities rather are plenty. So you can do so many things. So what that does is that gives developers or application owners options to work with these applications in numerous ways. Okay. It simplifies their complications, right? Since if you're talking about a platform like Microsoft Azure, it helps you basically orchestrate quite a lot of activities, be it managing your servers, infrastructure, right? Be it basically load balancing, be it auto scaling, all these things can be controlled by using the cloud platform. So what that does is that gives developers this added benefit, okay, or the application owners this added benefit. And that is why what these cloud platforms are doing these days is they are encroaching or basically covering different domains, be it your big data, DevOps, analytics, right? All these things are or can be implemented using these cloud platforms, because when you talk about these cloud platforms, they're already owning various markets of software development and application hosting. Okay. So that is why having something like Kubernetes work on top of Azure is a benefit. Why? Because some of the complications that you'd find difficult to implement using Kubernetes can be controlled by using Microsoft Azure. And that is why you have these added benefits, be it your end-to-end, deployment, be it your availability or scalability. If you talk about some of the benefits that it actually offers, what it does is you pay only for the nodes that you use. That means last time I checked, Microsoft Azure did not charge you for your master node. You only get charged for your worker nodes that you use. Okay. Your cluster upgrades are easier, so you do not have to worry about the patching part and stuff like that. Integration with various Azure and other tools and services becomes easier. Not just that, what you can also do is you can actually go ahead and enforce various rules that are under Azure policy across multiple clusters to have uniformity if you need to, right? What you can also do is you can scale Kubernetes and other nodes using autoscaler that Microsoft Azure supports. And you can even expand your scale even greater by scheduling your containers on Azure containers. So that is what Microsoft Azure Kubernetes service provides you with. Okay. Let us now move further in this Azure Kubernetes service tutorial video, and let's try and understand some of the other important pointers, like how does the architecture of Azure Kubernetes services works. Okay, to understand the working of AKS or Azure Kubernetes service, right? You can see this diagram on the screen. It's a fairly simple diagram and it tells you what Azure Kubernetes service does. Okay, so we've already seen how Azure Kubernetes architecture works, right? I mean, we know what all components it has and stuff like that. This is a more detailed view. So what you'll have is you'll have again a Kubernetes master node or cluster is what you can call it. Okay, so in this master node, the functionality would be same. It would be controlling how the deployment and how the management of your containers work. So basically, Azure will manage your master node. It will basically help you control quite a few activities that are there. As a customer, you'd be managing the applications only. There too, you would have support from Microsoft Azure. How we would understand that? Now, if you talk about the control plane, what you have here is you have your API server. Now, when you talk about your API server, what it does is it basically tells you how the underlying Kubernetes APIs are exposed. Okay. What this component basically does is it provides the interaction for your management tools, be it your Kubectl or the Kubernetes dashboard. Similarly, you have your etcd. Now, etcd basically what it does is it maintains the state of your Kubernetes. When I say the state of Kubernetes, I'm talking about the Kubernetes cluster, and basically it helps you control all the configuration that is there. This thing is highly available and it is key value based in nature. Okay. What you also have here is basically you have a scheduler. What a scheduler does is it lets you create and scale your applications to basically determine which nodes can run on what workload and stuff like that. Okay. And finally, you have your controller manager. Now, this is an important bit again. What it does is it controls or oversees a number of smaller controllers, whether they're performing their actions or not. And what it also helps you in doing is replicating the pods that you have and handling your nodal operations as well. So this is what your control plane does, and it is basically managed by your Azure. Now, what is the benefit of having Azure manage it, right? Since Azure is managing it, you do not have to worry about the configuration part, setting up part, right? Your cluster node is basically set up by Microsoft Azure, and that is what it simplifies. Then the other bit is your customer managed bit, be it your kubelet, right? Kube proxy, your container, and container runtime. To understand this better, I think this diagram should draw a clearer or a better picture for you. Okay. So basically, when you talk about your customer part, now there are quite a few things that you need to know. I've mentioned kubelet, which basically lets you run your pods, right? Your pods are run by your kubelet. That is what your kubelet does. Okay. There are other things as well that you need to know here. You have your Azure Virtual Network Interface. Now it is something that takes care of all the interface requirements that you might otherwise have. Okay. And similarly, you have your kube proxy, right? Kube proxy again works together with your virtual network interface, right? Or basically your Azure virtual network and tells you what needs to be done. Okay. Now, all these things, they reside on a virtual machine again. So we've discussed all the differences and benefits of it. So what Azure does is it basically launches a virtual machine for you on top of which your containers would reside. Okay. So when you talk about these containers again, these are nothing but your applications that are running for you. Okay. And these are the services that would help you actually implement or control all these applications that are there. You can actually go ahead and scale up your virtual machines to meet the requirements of your application in different ways. So this is how the working of AKS is. I mean, this is how the master node works, and this is how your basically customer node or your worker nodes work when you talk about AKS. We'll see these as we get into the demo part. But before that, let's go ahead and understand a use case or see a use case as to how vehicle safety with AKS is supported. Now, when we say vehicle safety, we are talking about a use case that was set forth by Bosch. Okay, Bosch, as we all know, is a very popular company which has numerous thousands of employees working across the globe for meeting different technological needs of the world. Okay, in this particular use case, what they thought of was the amount of accidents that happen due to wrong way driving. Okay, and what they thought was, could we find a solution that could basically help us overcome this bit of problem? Okay, so what were the problems that they were facing, right? When you talk about wrong way driving problems, right? What are the issues that we face? Okay, because of wrong way driving, there could be a lot of accidents, unplanned casualties, and stuff like that. But if I am to avoid wrong way driving using technology, it's a very tedious task. The reason for that is what I can try and do here is I can basically set up an application that notifies me of wrong way driving, right? But then for that to happen, I have to have a lot of data that is in real time. And when I'm driving, my only way of fetching data is by using cell phones and GPS, right? But then again, there are problems with these things. When you talk about cell phones, they basically function very well in a radius of 5 meters distance when you talk about their operational radius rather, or their limitations when you talk about range on exchanging this data. Okay. So you can transfer data to a larger audiences. We see that through WhatsApp and stuff. But if you talk about GPS kind of data, we are talking about multiple points or multiple data that we are dealing with. And to deal with them parallelly can be a difficult task. So because of that, Bosch felt was that this was an impossible task to deal with. Why? In order to get the last piece of information out of the noisy sensor data can be a problem. And in order to develop a highly scalable and ultra flexible service to process this data in real time can also be a tedious task. What they also figured out was to solve this problem, they needed this data in real time and in very short duration. If we could do that, we could actually go ahead and save accidents and we could save these wrong way driving incidents. And that is why they decided to work with Microsoft Azure, which was their already supporting partner. What they also did was they ensured that they did go ahead and accommodate Azure Kubernetes service in their infrastructure. What this did was it ensured that Bosch would get repeatable, manageable clusters of containers. And since they work in such shorter durations, do not have latencies in minutes, but rather in seconds, they offered a simple form of services for them to work with. And what that ensured was they had the average time to calculate whether a driver is going the wrong way or not in milliseconds. So around 60 milliseconds they could figure out. That is around a second where they could figure out whether a driver was in the wrong way or not. And that is what basically your Azure Kubernetes service enabled them to do. Their major problem, that is they had the time constraint, that is something it helped them solve. And because of that, they could come up with this wrong way driving problem solution where they basically use Microsoft Azure to host their data and basically Azure Kubernetes service to basically help them in simple provisioning scaling of applications, and ensuring that the real-time data is made available to the drivers within a span of 60 milliseconds, which again is a big achievement. So that is what AKS or Azure Kubernetes Service had to offer. If you go to Microsoft Azure's website, there's so many good use cases that talk about AKS. So you might want to go ahead and take a look at that as well. As far as the session goes, we'd go ahead and take a look at the demo and understand how we can actually go ahead and set up an Azure Kubernetes cluster and a lot more. Okay, so guys, let's go ahead and get into the demo part now. This is how the Azure portal looks like. Okay, I've signed into the Azure portal. Now for people who are new to Microsoft Azure, what Microsoft Azure does is it gives you an Azure portal where you can implement all the cloud related activities that concern Microsoft Azure. Okay, so if you want to practice from scratch, it also offers a free tier account where you have a number of services available free of cost. Okay, or rather, in case of Azure, it works differently. For AWS, you have those free services. With Azure, you have this $200 of credit that it gives you. So you can spend those $200 on creating resources for 11 months duration. Post that, those will expire. So if you do not have an account, you can just go ahead and create a free tier account, fill in the details, right? And you should have this free Azure portal for your usage. Okay. In my case, this is a paid account. This is the company's account. So it's called as pay as you go in my case. In your case, it would be a free tier account. But the functionality would be similar for you as well. The only thing is with the paid account, you have more services available to you. And even the larger instances is something that you can actually go ahead and spawn and use because you're paying for those, right? Under free tier, you don't have to worry about paying for them, right? So there are certain restrictions and limits there. So do go ahead and register to Microsoft Azure's portal. Okay. Now, coming back to the demo part, what we are going to do now is we are going to create a Kubernetes cluster. And on top of that, we are going to deploy an application. And the application would be a basic pre-built app by Microsoft Azure. We are not going to create a new app. I'll be sharing the code for the application. So do not worry about that. So we are just going to go ahead and use that pre-built code, and we are going to deploy that code on top of Kubernetes cluster that we have. Okay. So the main thing to note here is we have to see how easily the cluster is created. We are not concerned about the orchestration process at all here. Everything is taken care by your Microsoft Azure, and that is what we are going to look into. So let's not waste any time. Just quickly go ahead and get an instance in place, rather a cluster in place. Okay. So to do that, we are going to click on this icon and say create a resource. Okay. Here you can see all the service domains that are there for offering. So I'm going to click on the containers one and click on Kubernetes service. Once you do that, you see you'll be brought to this page and you'll get all the details, right? AKS manages your hosted Kubernetes environment, making it quick and easy for you to manage containerized applications. The main point is without having to container orchestrate or have any expertise in that. Okay. It eliminates the burden of ongoing operations and maintaining, provisioning, upgrading, scaling your resources rather, which happens on demand here. So you don't have to worry about those things. So let's just go ahead and create a resource group. So for people who do not know what resource groups are, resource group is nothing but you can think of it as a small container or a folder where you put forth all the necessary things that are important for your resource to work. Now, in this case, our resource is Kubernetes. So quite a few other nitty-gritties related to it would be in the resource group. Okay. So let's just go ahead and create one. So I'm going to click on create new. Let's just say we have RG for demo. I'm going to give a simple name so that I can remember that. Okay. So I'm going to say, okay, I'm going to create a cluster. I'm going to call it cube cluster. Okay. This is enough. So cube, let's call it cube cluster. Okay. And this is in place. Where do I want it? If you're using a pay-as-you-go model, there won't be any restrictions here. If you're using free tier, there might be some. Okay. So just select any region that you want to do. I'm going to randomly select a region now. What region it should be? My region would be, okay, let's pick this one. And it would ask me how many nodes do you want to create? Let's create one. Since it's a very simple demo, we do not need more nodes. Okay. We've discussed what nodes are, right? So that is what we are doing. We are creating a node here where our application would run basically. So I'm going to say review, or let's just go ahead and see if we have all the settings. Node pools, authentication, you have two options, whether you want your server or rather your cloud platform to manage your identity pools and basically create resources accordingly, you can do that, or you can select a service principal, which is an older way to do it, where you use an Azure Active Directory to do that. So there's no rule here. You can go for this one as well. I'm just going to do this just because I've thought of showing it to you. I selected that. It does not hold a lot of impact on our demo. Okay. Just going to say create and review. Okay. So for creating this thing, now it will review all the requirements. If the requirement, what it will do is it will just go ahead and create your cluster and put everything in place. Okay. So it says, do you want to create it now? I'll say yes, create. Okay, let's just refresh and see whether our application is done. It's still deploying. Let's wait for this deployment to get in place, and once it's done, we'll just go ahead and get these things in place. After this, the process is very simple. Okay, we are gonna just go ahead and put in certain set of commands and our job would be done. So you don't have to wait for too long post that. Okay, let's just refresh it again and see whether it's in place. Normally it takes a couple of minutes, so could take longer, right? But it's a very easy deployment process. So let me give you an idea as in what happens when you say that the deployment is happening. So first your Kubernetes will actually go ahead and launch a Linux instance to start. Okay. So once the Linux instance is in place, that is when we'll actually go ahead and put forth all our resources on top of it. In that Linux instance, we'll set up a cluster, right? All the nitty-gritties that we need, and on top of that cluster, our application would start working. Here in this case, it would probably set up a cache, could be a Redis as well. We'll have to go ahead and look into it, whether it's that one, okay? And then accordingly, we can go ahead and implement everything on top of that. But we don't have to get into the complications of things. It's a fairly simple process for us, okay? Okay, let's just go ahead and refresh it once more. Okay, it's done. Your deployment has been complete is what it says. That means we are good to go ahead and use our resource. You can do other things as well on top of it. It is suggesting what all you can do. Okay. So we are going to do one of these things. Do not worry. So just go to the resource in our case. Okay. And in this resource, you can see there's all the information that you need. Okay. You'll get to know where it is hosted and stuff like that, what kind of instance it is, where it is located, everything. One node pool is what you have, right? So you have all the information to actually go ahead and connect to it. So in your case, I'm hopeful that it would happen faster than what you see in my case, or on my screen rather. You see, Cloud Shell is up and running. So let's just go ahead now and basically get credentials, right? Here, let's get the credentials or merge our cluster, okay? So that we can start using it. So how do we do that? We use this command. We say AKS, okay? And in this case, what we are going to do is we are going to say get credentials. Okay. Now the next thing is, what do we need? Resource group details. So I'm going to say resource dash group. And I'm going to give the resource group name, which I am certain that we should see if we just scroll up. Okay. So the resource name is RG for demo that we used. Okay. RG for demo. And what we also need is we need the name of the cluster, and in that case it is kube cluster. So you can do it vice versa as well. You don't have to go this order. You can start by giving in the details for your cluster and then the detail for your resource group. I'm just going to hit the enter button now. Merge kube cluster as a current context in this path is what it says. Okay. Now let's just go ahead and get the details for the node. In this case, we know there's only one node, but you could be working on multiple nodes, right? So in that case, you have to use this command. You say kubectl. Now it is basically a client-side interactive tool for interacting with your Kubernetes. Okay, so that is what kubectl is all about. Okay, and you say get nodes. If there are multiple nodes, it will give you multiple nodes. If there's only one node, it will give you only one node. So there you go. You can see that there's one node that we have with us. Okay. We have all the details. It's been running for 5 minutes, it says, right? Because that is when we started the node. Okay. Now the next thing is we are going to go ahead and select the YAML file where we've actually put forth the details for our application, right? So how do we do that? For that, we are going to go ahead and use this command, okay? Nano, okay, space, Azure. The name of the application is, or the application rather, is related to voting. So that is why I'm going to use this name, and I'm going to say .yaml, okay? Okay, so guys, I've already pasted a piece of code here because I tried implementing this demo before. So you'll see that there's code here, okay? So in this case, what we are going to do is we are going to remove this code just to be safe. I'm going to just paste the code again. So basically, this is where you'll have all the details. What is the API that is being used? What is the container port, right? What is the memory that you are using? What call are you making, right? All those details are here. Do not worry, I'll share the link to this piece of code in the description. If not, you can just look for Azure demos or getting started with Azure on your browser, and you'll find this piece of code. It's available everywhere. You'll get this code on GitHub as well. I do not own this code, so I will not take any right in saying that this is something that I've created. It is a code that has been used and it is somebody else's work. Okay. So you may check out online the details. I'll also pass in the details in the description. Okay. So everything is removed now. I'm just going to go ahead and paste my piece of code here. Okay. I'm going to say paste, and all the same code is again here with us. Okay. Now, how do I go ahead with it? In this case, I'm going to say justify, cut, uncut. Do I want to replace? I'm just going to say exit for now. So it's Control X in my case. And I'm going to say no, will discard the changes. So we'll say yes. So Y. That means it will save my code. Okay. I'm going to hit enter now. So it will take me back to my cluster. Okay. The next step is, now what we are going to do is we are going to go ahead and call out this YAML file. Okay. So once we do that, this is how we are going to do it. We're going to say kubectl again. Okay. And apply /f Azure. What was the name again? /vote dot YAML. I'm going to hit the enter button. And there you go. What it has done is it has created a vote back application. Its front is created, its back is created, right? So we need to see how it looks like, right? So we are gonna find out all the details, as in if we want to watch this app working, we need the details for it. So we are just gonna go ahead and use a command called as get service. Okay, so get service is in place. And in this case, again, my app name Azure vote, but this time I want the front. Okay, so I'm gonna say front, and I'm gonna say watch and hit the enter button. I basically made a blunder here, and that blunder is we have to call this command through kubectl, right? So in this case, again, we'll have to type the remaining command again. So I'm just going to do it quickly. Okay, get service Azure vote dash front watch. And there you go. You have your external IP here. So guys, at times what you see here, your external IP, if your system is very slow, which is in my case, but I don't know how it happened, its age is only 85 seconds is what it says. So normally it takes time for you to see this external IP. Okay, but luckily we can see it. So I'm gonna just copy it here. Okay, and I'm gonna paste it here, and this way we should be able to see the application that we've created. Okay, so you can see you can vote here. One, let me vote for dogs, twice, thrice, and I can just go ahead and reset it as well. Okay, so guys, this is how you actually go ahead and create a cluster. Okay, a suggestion here would be you delete all the resources that is there. Delete this one, delete the resource group, and also the Azure Active Directory, so that you do not get charged. If you want to see what all we did here, right, and how the performance went on, Azure lets you track all the working as well, right? If you want to take a look at the insights and stuff, if you click here, you'll have all those details as well. So there you go. If I just refresh it, you should have all the details, right? How long did we use the cluster? This is where the usage started. Okay, so you'll get all these details that you want. So you can do that. So That's it. I believe this demo was clear to you people, and you got to know what things we've worked on, how we've used these things, and how basically your Kubernetes cluster works. Okay. So we've created a simple Kubernetes cluster and explored it. Ensure when you go back, you just delete. Just go to the resources and delete the resource group, the cluster, and the Active Directory, if any. Okay.
So currently I'm working on my Linux virtual machine. So firstly, what we're going to do is we're going to install Docker on our virtual machine. And if you do not use virtual machine, you will need to start a Linux virtual machine and run Docker inside that VM like I did. If you're using Mac or Windows, you can install Docker as per their requirements. Docker will set up a VM for you and run the Docker daemon inside that particular VM, okay? The Docker client, on the other hand, will be executable and will be available on your host operating system and will communicate with the daemon inside the VM. So I'm just going to click on the web browser and I'm going to click on Docker download. And I'm just going to click on the third link that you can see that says Get Docker. And I will click the option Docker for Linux. Okay. And if you scroll down, you have the server option where I can click on Ubuntu. So here you can uninstall the old versions if there are any, and you can go down, scroll down. Using the repository installation method, you can set up the repository and then add Docker's official GPG key. And then finally, you can install the Docker engine. Now, to verify if Docker has been installed successfully after following all of these steps, you can simply run this command. Okay, so I'm just going to copy it. So since I've already installed Docker on my virtual machine, I'm just going to cross check if it has been installed successfully. You can see that there's an output that says hello from Docker. So if you want to share images, you can use hub.docker.com. And for more examples and ideas, also you can visit the Docker website to get started. So after completing the installation, you can use the Docker client executable to run various Docker commands. For example, you could try pulling and running an existing image from Docker Hub, which is the public Docker registry, and it contains ready-to-use container images for many well-known software packages. And one of them is the BusyBox image, which you will use to run a simple echo hello world command. So if you're unfamiliar with BusyBox, that's okay. It's just a single executable that combines many of the standard Unix command line tools such as echo, ls, gzip, and much more. Okay, instead of the BusyBox image, you could also use any other full-fledged OS container image such as Fedora, Ubuntu, or other similar images, as long as it includes the echo executable. I'm simply now going to clear my screen. And once that is done, let us see how to run the BusyBox image. You don't need to install or download anything. All you have to do is run the docker run command and specify what image to download and run and what command to execute in the following listing. So now I'm just going to type the docker run command, BusyBox echo hello world. So this doesn't look that impressive, but when you consider that the whole application was downloaded and executed with a single command without you having to install the application on anything else, you'll somewhat agree it's really, really cool. Now, in your case, the application was a single executable that is BusyBox, but it might as well have been an incredibly complex application with many dependencies. The whole process of setting up and running the application would have been exactly the same. What's also important is that the application was executed inside a container that is completely isolated from all the processes running on your machine. So what firstly happens is when you execute this command, what really happens is you perform the docker run command. So first what Docker does here is it checks if BusyBox latest image, which was already present on your local machine. If it wasn't, Docker gets pulled from Docker Hub registry at docker.io website. And then after the image is downloaded to your machine, Docker creates a container from that image, and then it ran the command inside it. So the echo command printed the text to std out, and then the process terminated and the container stopped. So there is also an option that will allow you to run other existing container images the same way you ran the BusyBox image. So what you have to do is you have to search or browse through the publicly available images on the hub.docker.com. or any other public registry. And here you will tell Docker to run the image using the Docker run, and then you specify the image. All you have to do is run the Docker run command. Okay. Now that you have a working Docker setup, what we're going to do is we'll be creating an application. Okay. You will be creating a trivial node.js web application and package it into a container image. The application will accept HTTP requests and respond with the host name of the machine it's running on. So this way you'll see that an application running inside a container sees its own host name and not that of the host machine, even though it is running on the host like any other process. And this will be very, very useful later, because when you deploy the application on Kubernetes and scale it out, you will see your HTTP requests hitting different instances of the application. So what we're going to do now is we're going to have an application will consist of a single file called app.js with some content within it. So we're just going to create an app.js file. So I'm just going to write some code. So once that I've created the app.js file, we should be really clear with what this code does. Firstly, it starts up an HTTP server on port 8080. The server responds with an HTTP response status code 200 OK. And the text you have hit host name to every request. The request handler also logs the client's IP address to the standard output, which you'll need later. Now, the returned host name is the server's actual host name, not the one the client sends in the HTTP request host header. Now I'm just going to save this file. So now what we're going to do is we are going to download and install node.js and test your app directly. So what people usually do is they download and install node.js and test the app directly, but this isn't necessary because we'll be using Docker to package the application into a container image and enable it to run anywhere without really having to download or install anything except Docker, obviously, which does not need to be installed on the machine which you want to run the image on. So now to package your app into an image, you first need to create a file called Docker file, okay, which will contain a list of instructions that Docker will perform when building the image. The Docker file needs to be in the same directory as the app.js file and should contain some certain commands. So what I'm going to do is I'm going to be creating a Docker file. So what we're going to do is we're just going to check the status of Docker. So it's active and running, so that's great. So I'm just going to clear my screen and I'm just going to create the Docker file. Okay, so once that is done, I'm just going to type some commands within the Docker file. Now the from line defines the container image you will use as a starting point. That is the base image you're building on top of. In your case, you're just using the node container image tag 7. In the second line, you're adding your app.js file from your local directory into the root directory in the image under the same name, that is app.js. Finally, in the third line, you're defining what command should be executed when somebody runs the image. Now, in your case, the command would be node app.js. Now, you must be wondering why we choose this specific image as your base. And this is because your app is a node.js app. You need your image to contain the node binary executable to run the application. You could have used any image that contains that binary, or you could even use a Linux distro base image such as Fedora or Ubuntu and install node.js into the container at image build time. But because the node image is made specifically for running node.js apps and include everything you need to run your application, you'll use that as the base image. So now that is done, I'm just going to save this. Okay, great. So what now we're going to do is we're going to build the container image. Now that you have your Docker file and the app.js file, you have everything you need to build your image. To build it, you have to run the command docker build. Okay, so I'm just going to clear my screen. So to build it, I'm just going to use the docker build command. And I'm going to type kubia space dot. Okay, so what it does is you're telling Docker to build an image called kubia based on the contents of the current directory. Docker will look for the Docker file in the directory and build the image based on the instruction in that file. Now, the build process isn't performed by the Docker client. Instead, the contents of the whole directory are uploaded to the Docker daemon and the image is built there. And the client and daemon obviously do not need to be on the same machine at all. Now, if you're using Docker on a non-Linux OS, The client is on your host OS, but the daemon runs inside a VM. Because all the files in the build directory are uploaded to the daemon, if it contains many large files and the daemon isn't running locally, the upload may take a little longer. During the build process, Docker will first pull the base image, that is node 7, from the public image repository Docker Hub, unless the image has already been pulled and is stored on your machine. So an image isn't, a single big binary blob, but it is definitely composed of multiple layers, which you may have noticed already when you're running the busy box example. So if you're pulling the images from Docker for the first time, you'll get multiple lines. Okay, I got only one line because I pulled it already in the past before. So I just got an output hello world. But if you're pulling it for the first time, you'll see several lines, one for each layer. Different images may have different layers, which makes storing and transferring images much more efficient. So you may think that each Docker file creates only a single layer, but that's not the case. When building an image, a new layer is created for each individual command in the Docker file. During the build of your image, after pulling all the layers of the base image, Docker will create a new layer on top of them and add the app.js file into it. And then it'll create another layer that will specify the command that should be executed when the image is run. This last layer will be then tagged as Kubia latest, and it will also have a different image called other latest, which would use the same layers of the node.js image as your own image does. So once the build process is completed, you have a new image that is stored locally, and you can use it by telling Docker to list all the locally stored images. So I'm just going to execute that command. You can see that you have the Docker image Kubia, which is having the tag latest with an image ID, which is created a few seconds ago, and the size is 660 MB. Okay, you also have BusyBox that we created. This was created 10 hours ago. All of that is given here. Okay, so now that we've created our container image, let's go ahead and run it. You can run the image with the command run. So that's what we're going to do. We're going to type in the command docker run name Kubia container. So now what this does is it tells Docker to run a new container called Kubia container from the Kubia image. The container will be detached from the console, that is using the D flag, which means it will run in the background. Port 8080 on your local machine will be mapped to port 8080 inside the container using the P flag 8080 option. So you can access your application through the port 8080. Now, if you're not running the Docker daemon on your local machine, that is, if you're using a Mac or Windows, the daemon is running inside the virtual machine. You will need to use the host name or IP of the VM running the daemon instead of the local host. You can look it up through the Docker host environment variable. Now try to access your app using the HTTP localhost 8080 port. So I'm just going to use the command. So this is the response from your application. A tiny application is now running inside a container isolated from everything else. As you can see it's running on FBF3230C7AF2 as it's the host name and not the actual host name of your host machine. The hexadecimal number is the ID of the Docker container. So I'm just simply going to look for it. So the hexadecimal, as we can see, is the ID of the Docker container, and that's been displayed in the web page. Okay. So now let's list all of the running containers so you can examine the list. We are going to use the docker ps command for that. You can see that a single container is running, and for each container, Docker prints out its ID and name, the image used to run the container, and the command that's executing inside the container. So the docker ps command only shows the most basic information about the containers. If you want to really inspect, you can use the inspect command. And this will give you an entire overview on the host port, its network settings. All of that information will be given in detail using the inspect command. So now I'm just going to clear my screen. And next, what we're going to do is we are going to explore the inside of a running container. Now, what if you want to see what the environment is like inside the container? Because multiple processes can obviously run inside the same container, you can always run an additional process in it to see what's inside. You can even run a shell, provided the shell's binary executable is available in the image. Now the node.js image on which you have based your image contains the bash shell. So you can run the shell inside the container using the execution command. And what I'm going to do is I'm going to use the command execute. So this will run bash inside the existing Kubia container, and the bash process will have the same Linux namespaces as the main container process. What this allows you to do is it allows you to explore the container from within and see how Node.js and your application see the system when running inside the container. The IT option is shorthand for two options, that is I, which makes sure stdin is kept open. You need this for entering commands into the shell, and T, which allocates a pseudo terminal, that is a TTY. You need both if you want to use the shell like you're used to. Now let's see how to use the shell in the following listing to see the processes running in the container. So I'm just going to execute ps-aux command. So you can see only 3 processes. You don't see any other processes from the host OS. Now, if you open another terminal and list the processes on the host OS itself, you will, among all the host processes, also see the processes running in the container. So this proves that the processes running in the container are running in the host OS. If you have a keen eye, you may have noticed that the processes have different IDs inside the container versus the host. So you can see that they aren't the same. The container is using its own PID Linux namespace and has a completely isolated process tree with its own sequence of numbers. So like having an isolated process tree, each container also has an isolated file system. We can list the contents of the root directory inside the container, and it will show all the files in the container and will include all the files that are in the image, plus any files that are created while the container is running. Okay, so we can do that by using the ls command. I'm just going to close this window and I'm going to execute the ls command. Okay, so now you can see that it contains the app.js and other file system directories that are part of the node 7 base image you're using. Now to exit the container, you exit the shell by running the exit command, and you'll be returned immediately to your host machine. Okay, now if you want to stop and remove the container, you'll simply tell Docker to stop the Kubia container by using the docker stop command. So for this, you can just type docker stop and you can just type in your container name. So in this case, it would be Kubia container. And if you want to remove it, you can simply just use the rm command and you can remove the container. Okay, and just put the container name and it will remove the container. Okay, so stop and remove will allow you to stop and remove the container. So once you use the rm command, you need to be aware that it deletes the container and all of its contents are removed and it cannot be started again. So use this command very wisely. So now that you have created and run the container image, you can push the image to an image registry. The image you've built so far has only been available on your local machine, that is a VM machine. Now to allow it to run it on any other machine, you need to push the image to an external image registry. Okay, you don't have to really set up a private image registry, and we'll instead push the image to Docker Hub. You can simply open the web browser and you can go check out dockerhub.com. What you can do firstly is you can create your own Docker Hub ID by registering at Docker Hub ID. What we're going to do is I'm just going to search for Docker Hub on my web browser, and I'm going to click on the first link that appears on my search engine. To get started, you can sign up and get started. You can use your own ID and you can, change every occurrence with your own ID itself. So I'm going to quickly sign up and I'm going to show you how Docker Hub looks like. So once you sign in, you will be redirected to a page, something that is very similar to this page. And you can see that you can download the desktop application. And if you scroll down, you can just check out all of the container images that are present. You can explore, you can check out repositories, you can get help, all of that can be done. So what I'm going to do is I'm going to switch back to my terminal now. What I'm going to do now is once you know your ID is your unique username. It can be either that you've created a new account or you already have an existing account in Docker Hub. There'll always be a unique ID. So if you have that, you're ready to rename your image currently, which is tagged as Kubia, to anything that you'd like. So I'm going to change it from Kubia to my ID name, my username, /Kubia. Okay. So this does not rename the tag. It creates an additional tag for the same image. You can confirm this by listing the images that is stored on your system with the Docker images command. As you can see that, you can see both Kubia, my username /Kubia point to the same image ID. So there are in fact one single image with two tags. Now what we can do is, before we push the image to Docker Hub, you need to log it in. Repeat, you need to be logged in under your user ID with the Docker login command. Once you're logged in, you can push your ID into the Kubia image to Docker Hub. I'm going to clear my screen. So what we're going to do is we're just going to use the Docker login command, and you can use the U flag to enter your username, and you can use the P flag to type in your password. So once that is done, you'll be successfully logged in. Since I cannot type my password, just type in the password and execute the command, and successfully you'll be logged in too. Once that is done, what we can now do is we can successfully now push the image to Docker Hub. Okay, so what we're going to do is we're going to use the Docker push command, and this will prepare, wait, and finally push the image to Docker Hub. Now, after the push to Docker Hub is successfully completed, the image will be available to everybody. You can now run the image on any machine running Docker by executing the command docker run. So that's what I'm going to do. Now, since 8080 has been already allocated, you can use any other port, and this will allow your application to have the exact environment every time and everywhere it's run. If it ran fine for your machine, it should run well on every other Linux machine. No need to worry about whether the host machine has Node.js installed or not. In fact, even if it does, your application won't use it because it will use the one installed in the image. I'm just going to change it to 3000. And that's all you have to do. That's it. Okay. Now let's move on to the second part of this session and learn how to set up our own Kubernetes cluster. Now that we have app packaged inside a container image and made it available to Docker Hub, you can deploy it in a Kubernetes cluster instead of running it in Docker directly. But first, you have to set up the cluster yourself. Setting up a full-fledged multi-node Kubernetes cluster isn't a very simple task, especially if you're not really well versed in Linux and network administration in general. A proper Kubernetes install spans multiple physical or virtual machines and requires the networking to be set up really, really well so that all the containers running inside the Kubernetes cluster can connect to each other through the same flat networking space. A long list of methods really exists for installing a Kubernetes cluster, and these methods are described in the Kubernetes official website. So that's where we're heading. I'm just going to click on the install tool options that is present. I'm sure you must be aware that Kubernetes can be run on your own development machine, your own organization's cluster of machines, on cloud providers such as Google Compute Engine, Amazon EC2, Microsoft Azure, and so on. The list is never ending. And what we're going to do now is we'll just simply run a Kubernetes cluster. Okay, we'll see how to run a single node Kubernetes cluster on our local machine. So the simplest and the quickest path to a fully functioning Kubernetes cluster is by using Minikube. Okay, so Minikube is a tool that sets up a single node cluster that's great for both testing Kubernetes and developing applications locally. So what we're going to do now is we are going to install Minikube. The first thing that you're going to do is you will install kubectl on Linux. So the first thing that we're going to do is we're going to be installing kubectl. You can do this in many ways. You can use kubectl binary with curl on Linux. You can use native package management. You can really install them in many ways, but it's preferable if you just install the kubectl binary with curl on Linux. So the first step is to download the latest release with this command and then validate the binary using the second step. Once that is done, you install kubectl and test to ensure the version you have installed is up to date. So I'm just going to test the version. Since I've already installed kubectl on my VM, I'm just going to execute this command. And you can see the client version You can see the Git version, you can see the Go version, all of that is being displayed. That's great. So once you install kubectl, you can just test to ensure the version you've installed is up to date. Once that is done, you can move ahead and install Minikube. For this, there are some prerequisites. You'll need 2 CPUs, you'll need 2 GB of free memory, and you'll need 20 GB of free disk space, internet connection. Then you also have to have a virtual machine manager like VirtualBox or Hyper-V installed in your VM. And once that is done, you can select your OS type, the architecture, and installer type, and you can simply install Minikube on Go. Okay. Once that is done, you can start your cluster by using the Minikube start command, which is going to do that. Once that is done, your Kubernetes cluster will be up and running in no time. Now you can see that the Kubernetes cluster Minikube is up and running. So that's great. I'm just going to quickly clear my screen. So I'm just going to check my cluster info using the cluster info command. And you can see that Kubernetes control plane is running and kubedns is also running. You can also create an alias. Because you'll be using the full name of the kubectl executable, you might want to add a short alias such as k, so you don't really have to typing a kubectl all the time. If you haven't been using alias, you can just simply use the command alias. So sudo alias kubectl command. Okay. This will just create a short form for your kubectl. I won't be doing that as of now. Now let's move on to the next part of this session, the final part of this session, and run our first application on Kubernetes. So now what we're going to do is we'll be deploying our Node.js application. The simple way to deploy the application is to use the kubectl run command, which will create all the necessary components without having to deal with JSON or YAML. This way, we do not need to dive into the structure of each object yet. Try to run the image you created and push to Doc Hub earlier. So here's how we will run it on Kubernetes. I'm going to be using the create deployment command to create the deployment, and you can also scale up to 3 replicas using the scale deployment command. I just forgot to add kubectl. I'm just going to do that. So you have scaled this deployment and made 3 replicas. So I'm just going to clear my screen, and you can also now expose the deployment as a node port replica using the kubectl expose command. And that's what I'm going to do. You can see that now the service Kubia has been successfully exposed. Now what we're going to do is we are going to go to our local host and check if everything is in place, if it's working. So I'm going to switch to port 8080 and I'm just going to see if that works. You can see that you've hit the ID of the container. So we have successfully got the container image up and running. Now I'm going to switch back to my terminal. Now I just want to see all of the pods that are currently running on my cluster. So you have 3 pods that are currently running on my cluster. We had made replicas of 3, so there are 3 pods that are currently up and running. Initially, the status is on pending. After some time, you can see the status on running. So now what we're going to do is we're going to check the services that are available and are up and running by using the command get services. So I'm just going to type in kubectl get services. You can see that there are 3 services: Kubernetes, Kubia, and Nginx. Kubia is currently of type node port with a cluster IP, and the external IP is none as of now, and it's been exposed on port 8080, and its age is 3 minutes 45 seconds. That's great. Kubernetes basic interview questions. So in the basic interview questions, we'll be discussing 20 questions. And the first question is, what is container orchestration? In modern development, applications are no longer monolithic, but instead are composed of dozens or hundreds of loosely compiled, containerized components that need to work together to allow a given application to function as designed. Container orchestration refers to the process of organizing the work of individual components and application layers. While platforms like Apache, Mesos, Google Kubernetes, and Docker Swarm each have their own specific methodologies for container management, container orchestration engines allows users to control when containers start and stop, group them into clusters, and coordinate all of the processes that compose an application. Container orchestration tools allow users to guide container deployment and automate updates, health monitoring, and failover procedures. So basically, container orchestration refers to the process of organizing the work of individual components and application layers. The second question is explain the value and benefits of container orchestration. Containers are lightweight and ephemeral by nature. Running them in production can quickly become a massive effort, particularly when paired with microservices, which typically each run in their own containers. A containerized application might translate into operating hundreds or thousands of containers, especially when building and operating any large scale system. This can introduce significant complexity if managed manually. Container orchestration is what makes that operational complexity manageable for development and operations, or DevOps, because it provides a declarative way of operating because it provides a declarative way of automating a much of the work. This makes it a good fit for DevOps teams and culture, which typically strive to operate with much greater speed and agility than traditional software teams. Container orchestration is key to working with containers, and it allows organizations to unlock their full benefits. It also offers its own benefits for a containerized environment, including simplified operations, which is the most important benefit of container orchestration and the main reason for its adoption. Containers introduce a large amount of complexity that can quickly get out of control without container orchestration to manage it. The second benefit is resilience. Container orchestration tools can automatically restart or scale a container or cluster, boosting resilience. The third benefit is added security. Container orchestration's automated approach helps keep containerized applications secure by reducing or eliminating the chance of human error. The third question is what is the difference between deploying an application on hosts versus containers? Now, the left side architecture represents deploying applications on hosts. So, this kind of architecture will have an operating system, and then the operating system will have a kernel which will have various libraries installed on the operating system needed for the application. So, in this kind of framework, you can have n number of applications, and all the applications will share the libraries present in that operating system, whereas while deploying applications in containers, the architecture is slightly different. This kind of architecture will have a kernel, and that is the only thing that's going to be common between all the applications. So if there is a particular application which needs Java, then that application will get access to Java. And if there's another application which needs Python, then only that particular application will have access to Python. The individual blocks that you can see on the right side of the diagram are basically containerized, and these are isolated from other applications. So the applications have the necessary libraries and binaries isolated from the rest of the system and cannot be encroached by any other application. Moving on to the fourth question, we have what are Kubernetes or K8s? Kubernetes is an open source container orchestration system for automating computer application deployment, scaling, and management. It was originally designed by Google and is now maintained by the Cloud Native Computing Foundation. Moving on to the fifth and most important question, how is Kubernetes different from Docker Swarm? There are several features that you can compare Kubernetes and Docker Swarm with. The first one is based on its installation and cluster configuration. The setup in Kubernetes is extremely complicated, whereas the setup to install Docker Swarm is extremely easy. Moving on to the second feature, we have graphical user interface. Kubernetes has its own graphical user interface, which is known as Kubernetes dashboard, whereas Docker Swarm has no graphical user interface. The third feature is scalability. Kubernetes is highly scalable. You can scale as much as you'd like to, whereas Docker Swarm scales even faster than Kubernetes. Moving on to the fourth feature, we have auto scaling. Kubernetes can perform auto scaling, but Docker Swarm cannot perform auto scaling. Now, moving on to the fifth feature, we have load balancing. Kubernetes expects manual intervention when it comes to load balancing, whereas Docker Swarm has the advantage on this side, that is, it can support auto load balancing. The sixth feature is rolling updates and rollbacks. Kubernetes can deploy rolling updates and does automatic rollbacks, whereas Docker Swarm can deploy rolling updates but not automatic rollback. The comparison for the seventh feature is based on data volumes. Kubernetes can definitely share storage volumes only with the other containers of the same pod, whereas Docker Swarm can share storage volumes with any other container. The last feature that we'll be comparing both of these technologies with is based on logging and monitoring. Kubernetes has some inbuilt tools for logging and monitoring, whereas Docker Swarm has some third-party tools like ELK Stack, which should be used for logging and monitoring. Moving on to the sixth question, we have how is Kubernetes related to Docker? Although Kubernetes and Docker are distinct technologies, they are highly complementary and make a very powerful combination. Docker provides the containerization piece, enabling developers to easily package applications into small, isolated containers via the command line. Here, developers can then run those applications across the IT environment without really having to worry about compatibility issues. If an application runs on a single node during testing, it will run anywhere. When demand surges, Kubernetes provides orchestration of Docker containers, scheduling and automatically deploying them across IT environments to ensure high availability. In addition to running containers, Kubernetes provides the benefits of load balancing, self-healing, and automated rollouts and rollbacks. Plus, it has a graphical user interface for ease of use. For companies that really anticipate scaling their infrastructure in the future, it might make sense to use Kubernetes from the very start. And for those already using Docker, Kubernetes make use of existing containers and workloads while taking on the complex issues involved in moving to scale. Moving on to the seventh question, we have what are the features of Kubernetes? There are four important features of Kubernetes that I would like to address. The first one is automated scheduling. Kubernetes provides advanced scheduler to launch container on cluster nodes. The second feature is self-healing capabilities, which will allow you to reschedule, replace, and restart the containers which are dead. The third feature is automated rollouts and rollback. Kubernetes supports rollouts and rollbacks for the desired state of the containerized application. The fourth feature is it supports horizontal scaling and load balancing. Kubernetes can scale up and scale down the application as per the requirements. Moving on to the eighth question, we have how does Kubernetes simplify containerized deployment? As a typical application would have a cluster of containers running across multiple hosts, all these containers would definitely need to talk to each other. So to do this, you need something big that would allow load balance, scale, and monitor the containers. Since Kubernetes is cloud agnostic and can run on any public or private providers, it must be your choice to simplify containerized deployment. Moving on to the ninth question, we have what is Google Container Engine? Google Container Engine is a management and orchestration system for Docker container and container clusters that run within Google's public cloud services. Google Container Engine is based on Kubernetes, Google's open source container management system. The 10th question is, what is Heapster? Heapster is a cluster-wide aggregator of data provided by Kubelet running on each node. This container management tool is supported natively on Kubernetes cluster and runs as a pod just like any other pod in the cluster. So it basically discovers all nodes in the cluster and queries usage information from the Kubernetes nodes in the cluster via an on-machine Kubernetes agent. Moving on to the 11th question, we have what is a node in Kubernetes? A node is a worker machine in Kubernetes and may be either a virtual or a physical machine depending on the cluster. Each node is managed by the master. A node can have multiple pods and the Kubernetes master automatically handles scheduling the pods across the nodes in the cluster. In the next question, we'll understand what is Minikube. Minikube is a tool that lets you run Kubernetes locally. Minikube runs a single node Kubernetes cluster on your personal computer, that is Windows or Mac OS or Linux PCs, so you can try out Kubernetes or for daily development work. So basically, Minikube is a utility that you can use to run Kubernetes on your local machine. Creates a single node cluster contained in a virtual machine. This cluster lets you work on Kubernetes operations without really requiring the time and resource consuming installation of full blown Kubernetes. In the 13th question, we will address what is kubectl. The Kubernetes command line tool is known as the kubectl, which will allow you to run commands against Kubernetes clusters. You can use kubectl to deploy applications, inspect and manage cluster resources, and even view logs. The 14th question will address what is kubelet. The kubelet is the primary node agent that runs on each node. It can register the node with the API server using one of the host name, a flag to override the host name, or specific logic for a cloud provider. The kubelet works in terms of a pod spec. A pod spec is a YML or JSON object that really describes a pod. The 15th question addresses what is kubeadm. Kubeadm is a tool built to provide kubeadm init and kubeadm join as best practice fast paths for creating Kubernetes clusters. Kubeadm performs the actions necessary to get a minimum viable cluster up and running. By design, it cares only about bootstrapping, not about provisioning machines. In the 16th questions, we will understand what are daemon sets. A daemon set ensures that all or some nodes run a copy of a pod. As nodes are added to the cluster, pods are added to them. As nodes are removed from the cluster, those pods are garbage collected. The daemon set feature is used to ensure that some or all of your pods are scheduled and running on every single available node. This essentially runs a copy of the desired pod across all the nodes. So when a new node is added to a Kubernetes cluster, a new pod will be added to that newly attached node. In the 17th question, we will understand what is the init container and when can it be used. In Kubernetes, an init container is the one that starts and executes before other containers in the same pod. It is meant to perform initialization logic for the main application hosted on the pod. For example, create the necessary user accounts, perform database migrations, create database schemas, and so on. Init containers can contain utilities or custom code for setup that are not present in an application image. For example, there is no need to make an image from another image just to use a tool like sed, awk, Python, or dig during setup. Moving on to the 18th question, we will understand how to monitor the Kubernetes cluster. There are several tools to monitor the cluster. For example, we could use kubelet. So in a Kubernetes cluster, kubelet acts as a bridge between the master and the nodes. It is the primary node agent that runs on each node and maintains a set of pods. Kubelet watches for pod specs via the Kubernetes API server and collects resource utilization statistics and pod and event status. Kubelet fetches individual container usage statistics from Docker's Container Advisor, but Kubelet also accepts pod specs provided through different mechanisms and ensures that the containers described in those pod specs are up and running. These aggregated pod resource usage statistics are exposed via a REST API. The second one could be a container advisor, that is a C advisor, which is basically a container resource usage and performance analysis agent. It is integrated into the kubelet binary. C advisor auto discovers all containers in a machine and collects statistics about memory, network usage, file system, and CPU. C advisor has native support for Docker containers. It does not operate at the pod level but on each node. Be advised, however, C advisor is a simple to use but limited tool. So if you are looking to store metrics for long-term use or perform complex monitoring actions, C advisor will definitely not fit your needs. You can also use the Kubernetes dashboard, which is a web-based user interface add-on for Kubernetes clusters. It has many features that allow users to create and manage workloads as well as do discovery, load balancing, configuration, storage, and monitoring. It is helpful for small clusters and for people starting to learn Kubernetes. This tool offers different views for CPU and memory usage metrics aggregated across all the nodes. It can also be used to monitor the health status of workloads. Installing Kubernetes dashboard is quite easy and can be done using ready-to-use YML files. Another really important tool that can be used is Prometheus, which is one of the most popular monitoring tools used with Kubernetes. It is community driven and a member of the Cloud Native Computing Foundation. This project, developed first by SoundCloud and afterward donated to the CNCF, is inspired by Google Bog Monitor. Prometheus stores all its data as a time series. This data can be queried via the PromQL query language and visualized with a built-in expression browser. Since Prometheus is not a dashboard, it relies on Grafana for visualizing data. Version 1.0 of this tool was released in 2016, and it is becoming one of the most used Kubernetes monitoring tools. Other tools from Kubernetes ecosystem, including STO, include a built-in Prometheus adapter that exposes generated metrics. Prometheus can be installed directly as a single binary that you can run on your host or as a Docker container. Running Prometheus on top of Kubernetes can be easily accomplished with the Prometheus operator. We also have KubeWatch, which is basically a Kubernetes watcher that publishes event notification in a Slack channel. This tool allows you to specify the resources you want to monitor. It is written in Golang and uses a Kubernetes client library to interact with the Kubernetes API server. Using a simple YML file, you can choose the resources to watch, including daemon sets, deployments, pods, replica sets, replication controllers, services, secrets, and configuration maps. Moving on to the 19th question, how to get the central logs from pod. The architecture depends upon the application and many other factors. Some of the common logging patterns are node level logging agent, streaming sidecar container with the logging agent, export logs directly from the application. In the setup, journal beat and file beat are running as daemon set. Logs collected by these are dumped into the Kafka topic, which is eventually dumped to the ELK stack. The same can be achieved using EFK stack and Fluent dbit. The 20th question is, how do we control the resource usage of pod? With the use of limit and request, resource usage of a pod can be controlled. The request could be the number of resources being requested for a container. If a container exceeds its request for resources, it can be throttled back down to its request. The limit is an upper cap on the resources a single container can use. If it tries to exceed this predefined limit, it can be terminated if K8s decides that another container needs these resources. Now, if you are sensitive towards pod restarts, it makes much sense to have the sum of all container resource limits equal to or less than the total resource capacity for your cluster. In the next part of the session, we'll discuss Kubernetes intermediate questions. The first question is, what are the different components of Kubernetes architecture? When you deploy Kubernetes, you get a cluster. A Kubernetes cluster consists of a set of worker machines called nodes that run containerized applications. Every cluster has at least one worker node. The worker node hosts the pods that are the components of the application workload. The control plane manages the worker nodes and the pods in the cluster. In production environments, the control plane usually runs across multiple computers, and a cluster usually runs multiple nodes, providing fault tolerance and high availability. So here the control plane components make global decisions about the cluster, for example, scheduling, as well as detecting and responding to cluster events. For example, starting up a new pod when a deployment's replicas field is unsatisfied. Control plane components can be run on any machine in the cluster. However, for simplicity, setup scripts typically start all control plane components on the same machine and do not run user containers on this machine. Node components, on the other hand, run on every node, maintaining running pods and providing the Kubernetes runtime environment. Moving on to the second question of the intermediate questions, we have, what do you understand by kube proxy? Kube proxy is a network proxy that runs on each node in your cluster, implementing part of the Kubernetes service concept. Kube proxy maintains network rules on nodes, and these network rules allow network communication to your pods from network sessions inside or outside of your cluster. Kubeproxy uses the operating system packet filtering a layer if there is one and it's available. Otherwise, Kubeproxy forwards the traffic itself. What is the role of Kube API Server and Kube Scheduler? The API Server is a component of the Kubernetes control plane that exposes the Kubernetes API. The API Server is the front end for the Kubernetes control plane. The main implementation of a Kubernetes API Server is Kube API Server. Kube API Server is designed to scale horizontally, that is, it scales by deploying more instances. You can run several instances of Kube API Server and balance traffic between those instances. Kube Scheduler, on the other hand, is the control plane component that watches for newly created pods with no assigned node and selects a node for them to run on. Factors taken into account for scheduling decisions include individual and collective resource requirements, hardware or software or policy constraints, affinity and anti-affinity specifications, data locality, inter-workload interference, and deadlines. Moving on to the fourth question, we have, can you explain Kubernetes Controller Manager and Cloud Controller Manager? Firstly, I will explain Kube Controller Manager. It is a control plane component that runs controller processes. Logically, each controller is a separate process, but to reduce complexity, they are all combined into a single binary and run in a single process. Some types of these controllers are a node controller, which is responsible for noticing and responding when nodes go down. Job controller, which watches for job objects that represent one-off tasks, then creates pods to run those tasks to completion. Moving on, we have endpoints controller, which populates the endpoints object, that is, joins services and pods. Then we have service account and token controllers, which creates default accounts and API access tokens for new namespaces. The Cloud Controller Manager, on the other hand, is a Kubernetes control plane component that embeds cloud-specific control logic. The Cloud Controller Manager lets you link your cluster into your cloud provider's API and separates out the components that interact with that cloud platform from components that only interact with your cluster. The Cloud Controller Manager only runs controllers that are specific to your cloud provider. Now, if you're running Kubernetes on your own premises or in a learning environment inside your PC, the cluster does not have a Cloud Controller Manager. As with the Kube Controller Manager, the Cloud Controller Manager combines several logically independent control loops into a single binary that you run as a single process. You can scale horizontally, that is, run more than one copy to improve performance or to help tolerate failures. So there are some containers that can have cloud provider dependencies. That is node controller. This is for checking the cloud provider to determine if a node has been deleted in the cloud after it stops responding. Route controller for setting up routes in the underlying cloud infrastructure. Service controller for creating, updating, and deleting cloud provider load balancers. Now we have the fifth question, what is etcd? etcd is an open source distributed key value store that serves as the backbone of distributed systems by providing a canonical hub for cluster coordination. It was built specifically for running clusters on Core OS, but works on OS X, Linux, as well as BSD operating systems. etcd is used by many companies in their production system. It is written in Go and uses the Raft consensus algorithm to manage a highly available replicated log. etcd was basically designed to be the backbone of any distributed system, which is why projects like Google Kubernetes, Cloud Foundry, and Fleet rely on etcd. etcd is the primary data store of Kubernetes, storing and replicating all Kubernetes cluster state. So this is used as distributed key value store for Kubernetes, Google's cluster container management. Moving on to the sixth question, we have what are the various K8s services running on nodes and describe the role of each service. Firstly, we have cluster IP, which exposes the service on a cluster internal IP. It makes the service only reachable from within the cluster. This is basically the default service type. Then we have the node port, which exposes the service on each node's IP at a static port. A cluster IP service to which node port service will route is automatically created. The fourth type of service is the load balancer, which exposes the service externally using a cloud provider's load balancer. Services to which the external load balancer will route are automatically created. The last type of service is the external name, which maps the service to the contents of the external name field by returning a CNAME record with its value. No proxying of any kind is set up. Moving on to the seventh question, we have, what do you understand about load balancers in Kubernetes? Load balancing is a critical strategy for maximizing availability and scalability. It is basically the process of distributing network traffic efficiently among multiple backend services. A number of Kubernetes load balancer strategies and algorithms for managing external traffic to pods exist. In the eighth question, we're going to understand what is ingress network and how does it work. Ingress network is a collection of rules that acts as an entry point to the Kubernetes cluster. This allows inbound connections, which can be configured to give services externally through reachable URLs, load balanced traffic, or by offering a name-based virtual hosting. So, ingress is an API object that manages external access to the services in a cluster, usually by HTTP, and is the most powerful way of exposing service. Now let us understand the working of ingress network with an example. There are two nodes having the pod and root network namespaces with a Linux bridge. In addition to this, there is also a new virtual Ethernet device called Fanel0, that is network plugin added to the root network. Now suppose we want the packet to run from pod 1 to pod 4. So the packet leaves pod 1's network at Ethernet 0 and enters the root network at VETS 0. Then it is passed to CBR0, which makes the ARP request to find out the destination, and it is found out that nobody on this node has the destination IP address. So the bridge sends the packet to Fanel0 as the node's route table is configured with Fanel0. Now the Fanel daemon talks to the API server of Kubernetes to know all the pod IPs and their respective nodes to create mappings for pods IPs to node IPs. The network plugin wraps this packet in a UDP packet with extra headers, changing the source and destination IPs to their respective nodes, and sends this packet out via Ethernet 0. Now, since the route table already knows how to route traffic between nodes, it sends the packet to the destination node 2. Packet arrives at Ethernet 0 of node 2 and goes back to Fennel 0 to decapsulate and emits it back to the route network namespace. Again, the packet is forwarded to the Linux bridge to make an ARP request to find out the IP address that belongs to VET1. The packet finally crosses the root network and reaches the destination pod 4. Now that we've understood what is ingress network and how does it work, moving on to the next question we have, what do you understand from the Cloud Controller Manager? Cloud infrastructure technologies let you run Kubernetes on public, private, and hybrid clouds. Kubernetes believes in automated, API-driven infrastructure without tight coupling between components. The Cloud Controller manages the Kubernetes control plane component that embeds cloud-specific control logic. The Cloud Control Manager lets you link your cluster into your cloud provider's API and separates out the components that interact with that cloud platform from components that only interact with your cluster. By decoupling the interoperability logic between Kubernetes and the underlying cloud infrastructure, the Cloud Controller Manager component enables cloud providers to release features at a different pace compared to the main Kubernetes project. The Cloud Controller Manager is structured using a plugin mechanism that allows different cloud providers to integrate their platforms with Kubernetes. The Cloud Controller Manager runs in the control plane as a replicated set of processes. Usually there are containers and pods. Each Cloud Controller Manager implements multiple controllers in a single process. With this, we reach to the 10th question, what is container resource monitoring? As for users, it is really important to understand the performance of the application and resource utilization at all the different abstraction layers. Kubernetes factor the management of the cluster by creating abstraction at different levels like container, pods, services, and the entire cluster. Now, each level can be monitored, and this is nothing but container resource monitoring. The various container resource monitoring tools are Grafana, Heapster, C-Advisor, InfluxDB, and Prometheus. Grafana is a time series database to store the data captured by all Heapster pods, whereas Heapster gathers data in events from the containers and pods within the cluster. C-Advisor, on the other hand, is an inbuilt tool in a kubelet that automatically discovers all the active containers and monitors them. InfluxDB is a database that is used along with Heapster for visualizing data within the Kubernetes environment. Prometheus, on the other hand, is a project of CNCF which provides a powerful querying, alerting, and visualization capabilities. Moving on to the 11th question, what is the difference between a replica set and a replication controller? Replica set and replication controller do almost the same thing. Both of them ensure that a specified number of pod replicas are running at a given time. The difference comes with the usage of selectors to replicate pods. Replica set use set-based selectors while replication controllers use equity-based selectors. Now let's discuss about equity-based selectors. This type of selector allows filtering by label key and values. So in layman terms, the equity-based selector will only look for the pods which will have the exact same phrase as that of the label. For example, suppose your label key says app is equal to ngx, then with this selector you can only look for those pods with label app equal to nginx. Selector-based selectors, on the other hand, is a type of selector which allows filtering keys according to a set of values. So in other words, the selector-based selector will look for pods whose labels have been mentioned in the set. For example, say your label key says app in nginx, nps, apache. Then with this selector, if your app is equal to any of nginx, nps, or apache, then the selector will take it as a true result. Moving on to the 12th question, we have what is a headless service? A headless service is a service with a service IP, but instead of load balancing, it will return the IPs of our associated pods. This allows us to interact directly with the pods instead of a proxy. Headless service is similar to that of normal services, but does not have a cluster IP. The service enables you to directly reach out the pods without the need of accessing it through a proxy. Moving on to the 13th question, we have what are the best security measures that you can take while using Kubernetes? Firstly, you can enable role-based access control. You can also use a third-party authentication for API server. You can protect etcd with TLS and firewall. You can also isolate Kubernetes nodes. You can monitor network traffic to limit communications. You can use process whitelisting, turn on audit logging, and also remember to keep Kubernetes version up to date. There is also Lockdown Kubelet, which will allow you to secure your cluster. Moving on to the 14th question, we have what are federated clusters? Multiple Kubernetes clusters can be managed as a single cluster with the help of federated clusters. So you can create multiple Kubernetes clusters within a data center or cloud and use federation to control and manage them all at one place. The federated clusters can achieve this by doing the following things. That is, cross-cluster discovery and sync resources across clusters. Cross-cluster discovery provides the ability to have DNS and load balancer with backend from all the participating clusters, whereas sync resources across clusters keeps the resource sync across multiple clusters to deploy same deployment set across multiple clusters. Moving on to the 15th question, we have what is pod distribution budget? Pod distribution budgets specify the number of concurrent disruptions that you allow for your pods. Disruptions may be caused by deliberate or accidental pod deletion. When a Kubernetes node runs out of RAM or disk space, it will evict pods in an attempt to keep the node running properly. Moving on, we have why use namespaces. What is the problem with using default namespace? Namespaces are intended for use in environments with many users spread across multiple teams or projects. For clusters with a few to 10 of users, you should not need to create or think about namespaces at all. Start using namespaces when you need the features they provide. Namespaces provide a scope for names. Names of resources need to be unique within a namespace, but not across namespaces. Namespaces cannot be nested inside one another, and each Kubernetes resource can only be in one namespace. There are ways to divide cluster resources between multiple users via resource quota. It is not at all necessary to use multiple namespaces to separate slightly different resources, such as different versions of the same software. Use labels to distinguish resources within the same namespace. So while using the default namespace alone, it becomes really hard over time to get an overview of all the applications you can manage in your cluster. Namespaces can make it easier to organize the applications into groups that really make sense, like a namespace of all the monitoring applications and a namespace for all the security applications, etc. In the 17th question, we will understand what is ingress default backend. Ingress default backend specifies what to do with an incoming request to the Kubernetes cluster that isn't mapped to any backend. That is, what do we do when no rules being defined for the incoming HTTP request if the default backend service is not defined? It is recommended to define it so that users still see some kind of message instead of an unclear error. The default backend is a service which handles all URL paths and hosts the Nginx controller doesn't understand. That is, all the requests that are not mapped with the ingress. Basically, a default backend exposes two URLs, health Z that returns 200, that returns 404. In the 18th question, let us understand how to run a pod on a particular node. There are various methods that are able to achieve this. Firstly, we can use node name, which specifies the name of a node in a pod spec configuration. It will try to run the pod on a specific node. Node selector, on the other hand, assigns a specific label to the node which has special resources and use the same label in pod spec so that pod will run only on that node. Node affinities, on the other hand, require during scheduling, ignore during execution, and prefer during scheduling, ignore during execution are hard and soft requirements for running the pod on specific nodes. This will be replacing node selector in the future. That is, it depends on the node labels. Moving on to the 19th question, we have what are the different ways to provide external network connectivity to K8s. By default, pod should be able to reach the external network, but in terms of vice versa, we need to make some changes. There are some options to connect with pod from the outer world. Firstly, we can use a node port, which will expose one port on each node to communicate with it. We can use load balancers, which have L4 layer of TCP IP protocols. We can also use ngress, which is L7 layer of TCP IP protocol. The last question of the intermediate questions part, we have how can we forward the port 8080 container to 8080 service to 8080 ingress to AT browser, and how can this be done? The ingress is exposing port 80 externally for the browser to access and connecting to a service that listens on 8080. The ingress will listen on port 80 by default. An ingress controller is a pod that receives external traffic and handles the ingress and is configured by an ingress resource. For this, you need to configure the ingress selector, and if no ingress controller select is mentioned, then no ingress controller will manage the ingress. Now let's move ahead and discuss some important Kubernetes MCQs. So the first question is, what is the basic operational unit of Kubernetes? We have pod, task, nodes, and none of the above. So the answer here is pod. Moving on to the second question, we have Dash can be considered as the primary data store of Kubernetes. The options are pod, etcd, node, and all of the above. The answer here is etcd. In the third question, we have which of the following ensures containers are running in a pod. The options are pod, etcd, kubelet, and all of the above. Here the answer is kubelet. In the fourth question, we have replication controllers and deployment controllers are a part of Dash. Here we have options kubeadm, API controller manager, master controller manager, and none of the above. The answer here is master controller manager. Moving on to the fifth question, we have who developed Kubernetes? A. Google, B. Apple Incorporation, C. IBM, and D. Microsoft. The answer here is Google. Moving on to the sixth question, we have Kubernetes is a Dash platform. The options are portable, extensible, open source, and all of the above. The answer is all of the above. In the seventh question, we have which of the following manages the assigning nodes to pods depending on resource availability? The options are etcd, kubectl, scheduler, and none of the above. The answer here is scheduler. In the eighth question, we have Kubernetes is written in what programming languages? The options are Go, HTML, PHP, and Python. The answer here is Go. In the ninth question, we have to create a new deployment Kubernetes, use the command dash. That is kubectl run, Kubernetes git deployment, Kubernetes set deployment, and none of the above. The answer here is kubectl run. The last MCQ is what is the use of Google Kubernetes engine? Option 1 says resize application controllers. Option B says debug container clusters. Option C says update and upgrade container clusters, and D says all of the above. The answer is all of the above. Now let's move on to the last part of this session and talk about Kubernetes certification. Kubernetes training by Edureka is curated by top industry experts. This Kubernetes certification course helps you in clearing the Certified Kubernetes Administrator exam in the first attempt. This interactive Kubernetes certification training is created to help you learn how to set up your own Kubernetes cluster, configure networking between pods, and secure the cluster against unauthorized access. This Kubernetes training course is live, instructor led, and helps you master key Kubernetes concepts with hands on demonstration. So, what are you waiting for? Enroll now in this Kubernetes certification training and be a certified Kubernetes professional with Edureka. With this, we come to the end of today's session on Kubernetes interview questions. I hope you had a great time understanding and learning the various questions that can be asked in a Kubernetes interview. If you have any queries, feel free to leave them in the comment section below, and we will get back to you as soon as possible. Until next time, thank you.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!